Hello, I'm Herbie Lee, Professor of Statistics at the University of California, Santa Cruz. Welcome to this course on Bayesian statistics. There are two main philosophies of probability and statistics, Bayesian and Frequentist. Most existing classes focus on the Frequentist approach. Here, we will learn the Bayesian approach and some of its benefits. In particular, the Bayesian approach is better for dealing with uncertainty, both in terms of being able to quantify uncertainty and also for being able to combine uncertainties in a coherent manner. The interpretations of intervals make much more sense in the Bayesian paradigm. This course is meant to be largely self-contained. Thus, it starts with a brief review of some key concepts of probability, Bayes' theorem, and distributions. We will then have a quick review of frequentist inference, and then start on Bayesian inference, with comparisons and connections between the two. In the third module, we will learn more about priors and posteriors for discrete distributions, the Bernoulli, binomial, and Poisson distributions. Finally, in the fourth module, we will discuss continuous distributions, especially the normal or Gaussian distribution, and apply it to linear regression. In this course, you will learn the difference between Bayesian and frequentist inference, the key concepts of Bayesian inference, and how to perform Bayesian inference in simple cases. Some calculations can be done by hand, others will be done on the computer. You will have the choice of using R or Excel. You're expected to choose one of R or Excel, but you can do both if that interests you. Otherwise, you can pick from the available computer demonstrations, which are listed as lectures. You don't need to watch both the R and Excel lectures, just the ones for the software you have chosen. The format of this class is a little different from a conventional class. We'll have less in the video and more in the exercises, because learning by doing is more effective than just watching a video of mathematical concepts. These are what would be homework assignments in an in-person course, but there isn't a label in Coursera for homework, so they are labeled as quizzes. But do think of them as homework assignments. We've tried to include a lot of additional explanation in the feedback, both for correct and incorrect responses. So you may need to try these homework assignments several times to get a passing grade, and the feedback is provided to assist you in learning the material. Items labeled background material should be read before watching the video lecture. Items labeled supplementary material follow the lecture and are more optional. One note on video resolution. We recommend that you watch at the highest resolution. You can see this from the settings, the gear icon in the lower right. Under video quality, choose high. You may need to watch a video more than once. If you're confused after the first watching, check the background and supplemental materials again, and then try watching the video again. You may even attempt some of the exercises, and then go back and watch the video. Learning is an iterative process, and so trying to work the exercises may provide context that helps make the video more understandable. In terms of prerequisites and expectations, I expect that you've taken an introductory statistics course and a calculus course. In both cases that you've seen the concepts before, but don't necessarily remember everything. I'll give refreshers for the statistical concepts, such as probability, the central limit theorem, confidence intervals, and regression, but I won't be providing a complete introduction. Similarly, I expect that you understand the concept of an integral and a derivative, and I will be using them as calculations, but none of the mandatory exercises will require you to integrate or differentiate, although some may require finding a simple area under curve, like finding the area of a rectangle. A few of the honors exercises will require calculus for those people who do remember how to integrate and differentiate. So my basic expectation is that you've taken calculus in an introductory statistics course at some point in your life, but it may be a long time ago and you've forgotten all the details. That's fine. I just need you to have seen it before so that when I use some of these, that will trigger some memories about the concepts and the bigger picture, so that the exact calculations aren't totally foreign for you. Statistics is the study of uncertainty. How do we measure it? And how do we make good decisions in the presence of it? One of the ways to deal with uncertainty in a more quantified way is to think about probabilities. Let's think about some examples of probabilities. Suppose we're rolling a fair six-sided die and we want to ask, what's the probability that the die shows a 4? We could ask other questions. For example, is this a fair die? Does it make sense to ask, what is the probability that the die is fair? We could ask questions such as, what's the probability that it rains tomorrow? If we're dealing with the internet, we may have a router that's passing through information, and we can ask, what's the probability that it drops a packet? We might be comparing routers from two different companies, and we can ask, what's the probability that a router from one company is more reliable than a router from another company? We can ask more existential questions, such as, what's the probability that the universe goes on expanding forever? There are three different frameworks under which we can define probabilities. We'll talk about all of them briefly here. The first one is a classical framework. The second is a frequentist framework. And the third one is a Bayesian framework. Under the classical framework, outcomes that are equally likely have equal probabilities. So in the case of rolling a fair die, there are 6 possible outcomes. They're all equally likely. So the probability of rolling a 4 on a fair 6-sided die is just 1 in 6. We could ask a related question, which is, what is the probability of getting a sum of 4 on a pair of rolls? If we roll 2 dice, 2 fair 6-sided dice, then what's the probability that their sum shows a 4? Well, if we think about this, how many equally likely outcomes are possible on a pair of dice? There are 6 equally likely outcomes on the first die. There are 6 equally likely outcomes on the second die. So there are a total of 6 times 6, or 36 possible equally likely outcomes on the pair. Of those outcomes, how many will have a sum of 4? We could roll a 1 on the first die and a 3 on the second, a 2 on the first and a 2 on the second, or a 3 on the first and a 1 on the second. So there are a total of 3 possible outcomes out of 36 equally likely outcomes, and so that's a probability of 1 in 12. This classical approach works really well when we have equally likely outcomes, or a way to define equally likely outcomes, but it's very difficult to apply in any of these other cases. We can then move on to a frequentist definition. Frequentist definition requires us to have a hypothetical sequence, infinite sequence of events, and then we look at the relative frequency in that hypothetical infinite sequence. In the case of rolling a die, a fair 6-sided die, we can think about rolling the die an infinite number of times. This is pretty straightforward. If it's a fair die, if we roll an infinite number of times, then 1/6 of the time we'll get a 4 showing up, and so we can continue to define the probability of rolling a 4 on a fair 6-sided die as 1 in 6. This also applies to situations such as internet traffic going through a router. If we lose 1 in 10,000 packets, then we can define the probability as 1 in 10,000. This approach works great when we can define a hypothetical infinite sequence. But then we can ask other questions, and they become more complicated under this approach. For example, what is the probability that it rains tomorrow? In this case, we need to think about a hypothetical infinite sequence of tomorrow and see what fraction of these infinite possible tomorrows have rain, which is a bit strange to think about. Or in the case of asking, is this a fair die? Well, if we have a particular physical die, and we're asking, is it a fair die, then we can roll it a lot of times, but that's not going to change whether or not it's a fair die. And so either it is fair or it isn't fair. All these rolls are not going to change that. And so under the frequentist paradigm, this probability is either 0 or 1. It's 0 if it's not a fair die, and it's 1 if it is a fair die. This is not exactly an intuitive answer. In the case of the universe expanding forever, we can ask, if this is a deterministic universe and the same thing happens, then again, the answer is going to be either 0 or 1, because every time we play forward the expansion of the universe, either it will expand forever or it won't. On the other hand, we might subscribe to something like a multiverse theory, where there are an infinite number of parallel universes that can exist. In that case, we can consider this infinite collection and ask what fraction of this infinite collection have universes that expand forever. Depending upon what we know about the universe, we might get different answers. The frequentist approach tries to be objective in how it defines probabilities, but as you can see, it can run into some deep philosophical issues. Sometimes the objectivity is just illusory. Sometimes we also get interpretations that are not particularly intuitive. Another way to define probabilities is under the Bayesian perspective. The Bayesian perspective is one of personal perspective. Your probability represents your own perspective. It's your measure of uncertainty, and it takes into account what you know about a particular problem. But in this case, it's your personal one, and so what you see may be different than what somebody else believes. For example, we want to ask, is this a fair die? If you have different information than somebody else, then your probability the die is fair may be different than that person's probability. It's inherently a subjective approach to probability, but it can work well in a mathematically rigorous foundation, and it leads to much more intuitive results in many cases than the frequentist approach. We can quantify probabilities by thinking about what is a fair bet. So for example, we want to ask what's the probability it rains tomorrow? And then we can ask about a bet that you might be willing to take if you think it's fair. Suppose you'd be willing to take the bet that if it rains tomorrow, you win $4. If it doesn't rain tomorrow, you lose $1, or whatever your local currency is. We can think of this as odds of 4 to 1. If you think that bet's a fair bet, you should be willing to take it in either direction, which would also mean if it rains, you lose $4, and if no rain, you win $1. If you think these are both fair, then you're defining a probability of rain as 1 over 1 plus 4, which equals 1 in 5. We can see this is fair by looking at your expected return. Under the first bet, your expected return is you win 4 with probability 1 in 5, and you lose 1 with probability 4 in 5. And you can see that that's a fair bet of 0. In the second case, you win 1 with probability 4 in 5, and you lose 4 with probability 1 in 5, and that also is 0. So it balances out. It only balances out if your probabilities match. So you can use this betting framework to think about what is your personal probability based on what bets you'd be willing to take. In most cases, it's fairly easy to bracket it. You'd take a bet that was 1,000 to 1 in favor, but you wouldn't take a bet that was 1,000 to 1 against. And so your personal probability is somewhere in between. Finally, I want to mention the concept of coherence. Probabilities must follow all the standard rules of probability, those that were defined in the supplementary material for this lecture. If you don't follow all of the rules for probability, then you can be incoherent, which leads to a case where someone can construct a series of bets where you're guaranteed to lose money. This is referred to as Dutch book. If you do follow all the rules, and you follow the framework of Bayesian statistics, then you can be guaranteed to be coherent. In this segment, I will discuss conditional probability and Bayes' theorem. Bayes' theorem is the theoretical underpinning of most of what we do within the Bayesian statistical framework. Conditional probability is when we're trying to consider two events that are related to each other. So we can ask, what is the probability of event A given that we know event B happened? This is defined as the probability that both events A and B happen divided by the probability that event B happens. For example, consider a class of 30 students. Suppose within this class there are 9 female students. Suppose also we have 12 computer science majors, and of which 4 are female. So then we can ask questions about probabilities of this segment of population. We can say the probability that someone is female is 9 in 30, or 3 in 10. The probability someone is a computer science major is 12 over 30, or 2 in 5. The probability that someone is both female and a computer science major, we have the 4 out of 30. So now we can ask conditional probability questions. What's the probability that someone is female given they're a computer science major? So if we think about the definition, we can work with that. This is the probability that someone is female and they're a computer science major divided by the probability they're a computer science major. Probability that someone is female and computer science is right up here. This is 2 out of 15. And the probability they're a computer science major is 2 in 5. We can simplify this down to get that this probability is 1 in 3. We can also think about that in the original framework here. Of the 12 computer science majors, what fraction are female? That's exactly what this probability is saying. The probability that they're female given their computer science. And so there we could just look at the 4 over 12. That would give us the same answer of 1/3. That's an intuitive way to think about a conditional probability, is that we're looking at a subsegment of the original population and asking a probability question within that segment. We can also look in the other direction. Suppose we want to know what's the probability someone's female given they're not a computer science major, or I might denote that as CS complement. In this case, we can say it's the probability female and not computer science over the probability of not computer science. And this is 5 in 30 over 18 in 30, or 5 over 18. There's a concept of independence, which is when one event doesn't depend on the other. When two events are independent, we have that the probability of A given B is equal to just the probability of A. It doesn't matter whether or not B occurred. When this is true, we also get that the probability of A and B happening is just the probability of A times the probability of B. This is a useful equality that we'll use throughout this course. In this case, we can see that the probability of being female, given they're a computer scientist, is not equal to the marginal probability that they're female. And so being female and being computer science are not independent. Bayes' theorem is used to reverse the direction of conditioning. Suppose we want to ask, what's the probability of A given B, but we know it in terms of probabilities of B given A. So we can write the probability of A given B as the probability of B given A times the probability of A divided by the probability of B given A times the probability of A plus the probability of B given not A times the probability of not A. This does work out back to be the same as the probability of A and B over the probability of B. So to work this out in the context of the example of the computer science and females in the class, we can say the probability that someone's a computer scientist given they're female is the probability they're female given they're a computer scientist times the probability they're a computer scientist divided by the probability they're female given their computer science times the probability of computer science, same thing as there, plus the probability they're female given they're not a computer scientist times the probability they're not a computer scientist. Plugging in the numbers, we get 1/3 times 2/5 over 1/3 times 2/5 plus 5/18 times 3/5. Working this all out, this ends up as 4/9. We can compare this to the direct answer. Probability of computer science given female, if we were to compute this as probability of computer science and female divided by the probability of female, that one would have worked out to be 4/30 over 9/30, which gives us the same 4/9. In this case, it's straightforward to get the answer either way. But here we're moving from a direct definition. Here, it's where we have it in terms of one direction of conditioning, and we flip it to the other direction of conditioning. This is particularly useful in a lot of problems where it's posed in that direction. Another example was an early test for HIV antibodies known as the ELISA test. In that case, the probability that someone would test positive, given that they had the HIV virus, was 0.977. The probability that they test negative, given they don't have the virus, was 0.926. So this is a pretty accurate test. Over 90% of the time, it'll give you an accurate result. Today's tests are much more accurate, but in the early days, this was still pretty good. At that point, a study found that among North Americans, the probability that a North American would have HIV was about 0.0026. So then we could ask, if we randomly selected someone from North America and we tested them and they tested positive for HIV, what's the probability that they actually have HIV given they've tested positive? In this case, we don't have all the information to compute it directly as easily, but we have the information in the reverse direction of conditioning. And so this is a perfect time to use Bayes' theorem. Probably they have HIV given they test positive is the probability they test positive given they have HIV times the probability they have HIV divided by probability they test positive given they have HIV times the probability they have HIV plus the probability they test positive given they don't have HIV times the probability they don't have HIV. And now we can fill these pieces in. Before we go any further, I ask you to stop and think briefly. This is over 90% accurate. What sort of number do you expect to get in this case? All right. Let's do the calculation. Probably they test positive given they have HIV is 0.977. The probability that they have HIV is 0.0026. We repeat the same thing in the bottom of the denominator. And then the second term, the probability they test positive given they don't have HIV, that's 1 minus this. And the probability they don't have HIV, if we now plug that into a calculator, we get this probability to be 0.033. The probability they have HIV is less than 4%, even though they've tested positive on a test that is nominally quite accurate. Is this surprising? It is for most people. Why is this so? It's because this is a rare disease, and this is actually a fairly common problem for rare diseases. The number of false positives greatly outnumbers the true positives because it's a rare disease. So even though the test is very accurate, we get more false positives than we get true positives. This obviously has important policy implications for things like mandatory testing. It makes much more sense to test in a subpopulation where the prevalence of HIV is higher, rather than in a general population where it's quite rare. To conclude, Bayes' theorem is an important part of our approach to Bayesian statistics. We can use it to update our information. We start with prior beliefs, we'll collect data, we'll then condition on the data to lead to our posterior beliefs. Bayes' theorem is a coherent way to do this updating.
In this segment, we will review some basic probability distributions, both discrete and continuous. The first one is the Bernoulli distribution. It's used when we have two possible outcomes, such as flipping a coin, where it could be heads and tails, or the cases where we have a success or a failure. We'll denote this as saying a random variable x follows a Bernoulli distribution with probability p, where p is the probability of success, or the probability of heads. The little squiggle refers to is distributed as, saying it follows this distribution. In this case, the probability of a success, or heads, we'll say is p, and we'll denote that sometimes as x equals 1, and a failure, or tails, x equals 0, as probability 1 minus p. We can write this as a function for all the different possible outcomes and say, what's the probability that the random variable x takes a value little x given a specific value of p? So the notation here is that the capital letters refer to a random variable, the lowercase letters refer to a possible value it might take. And then over here we have a probability specified for it. Later, when these probabilities are unknown, we'll represent that with a Greek letter rather than a Roman letter. We may write this in shorthand as just the f of little x given p, and dropping the big X from the notation. In the case of a Bernoulli, mathematically this works out to be p to the x, 1 minus p to the 1 minus x, for the case that x's are either 0 or 1. One way to write this is with an indicator function, that x is either 0 or 1. This indicator function we could write as a function of x, and it's a step function, or sometimes referred to as a heaviside function. It takes value 1 when its argument is true, and it takes value 0 when its argument is false. This will be really useful notation for us in the rest of this course. The indicator function takes precedence in the order of operations, so we always evaluate it first. This is a way we can avoid doing things such as taking the log or the square root of a negative number. In basic textbooks, this is referred to as the probability mass function. It gives the probability of different outcomes of the random variable. In some textbooks, they make a strong distinction between discrete variables, where these are probably mass functions, and continuous variables, where these are probably density functions. Turns out if you get far enough along in math and you get up to the measure theory level, you can view everything as a density. And so I'm going to refer to this as a density function in a measure theoretic sense. One more concept is that of an expected value. This is the theoretical average, or theoretical mean. We write it with a capital E, and the expected value of x is we sum over all possible outcomes, little x. We sum up x times the probability the random variable takes that value little x. In this case, it's really simple. One possible outcome is 1, and it takes that with probability p. Another possible outcome is 0, and it takes that with probability 1 minus p. So the expected value for Bernoulli is just the probability p. Similarly, we can talk about the variance, which is the square of the standard deviation. For Bernoulli, the variance works out to be p times 1 minus p. The generalization of the Bernoulli, when we have n repeated trials, is a binomial. Binomial is just the sum of n independent Bernoullis. We can say x follows a binomial distribution with parameters n and p. In this case, the probability function, probably that x takes some value little x given p, is n choose x times p to the x times 1 minus p to the n minus x. N choose x is the combinatoric term, n factorial over x factorial times n minus x factorial. And this is all for x taking values 1, 0, 1, up to n. The expected value for a binomial is n times p, And the variance for a binomial is n times p times 1 minus p. Other distributions that we may encounter include the multinomial, a further generalization, and the Poisson distribution. As we move over to continuous random variables, the math gets a little bit more complicated and requires a little bit of calculus. We can define a continuous random variable based on its probability density function, or PDF for short. The PDF is sort of proportional to the probability that the random variable will take a particular value in a differential calculus sense, because it can take an infinite number of possible values. The key idea is that if you integrate the PDF over an interval, it gives you the probability that the random variable will be in that interval. As a specific example, let's consider a uniform distribution. X is uniformly distributed between 0 and 1, so it can take any value between 0 and 1, and they're all equally likely. In this case, we can write the density, f of x, as being 1 if x is in the interval 0, 1, and 0 otherwise. We could also represent this as an indicator function, and it's just the indicator function that x is between 0 and 1. We can then think about how we might plot this as a function of x. So as x goes from 0 to 1, what does this look like? Well, it's 1 in that region, and it's 0 otherwise. Very simple. The most simple probability density function we have. We can then ask questions about probabilities. What's the probability that x will be between 0 and 1/2? Well, in order to get this probability, we can just integrate the density function. So this is the integral from 0 to 1/2 of f of x dx, the integral from 0 to 1/2 of just dx, because it's 1 in that range. And so this is just 1/2. If we look at the picture, we could see the picture here. And it's the area there. We could ask a similar question. What's the probability x is between 0 and 1/2 inclusive versus not including the endpoints? Well, the integral doesn't really depend on the endpoints being in or not. You're going to get the same answer. So this is 1/2. From a calculus sense, we can also ask what's the probability that x is equal to 1/2. Well, if we integrate from 1/2 to 1/2, we're just going to get a 0. Because there are an infinite number of possible outcomes, the probability of taking any particular one is going to be 0. Some key rules for probability density functions. It is going to be always true that the integral from -infinity to infinity of f of x dx has to add up to 1. Be probability 1 that something happens. Also has to be true that densities are non-negative for all possible values of x. We can write the expected value for a continuous random variable as the integral of x times f of x dx. So this is analogous to the sum that we had for a discrete variable. In general, the expected value of some function of x, g of x, we can write as the integral of g of x, f of x dx. If we take the expectation of some constant times our random variable x, that's just the constant times the expected value of x. We can pull the constant out. Similarly, if we're looking at the expectation of a sum of two random variables, that's the sum of the two expectations. Finally, if we have independence if x is independent of y, that symbol means independent, then the expected value of x times y is just the product of the expected values. Some particular examples of continuous distributions are next. Let's start with the exponential distribution. We can write x follows an exponential distribution with the rate parameter lambda. So these are events that are occurring at a particular rate, and the exponential is the waiting time in between events. For example, you're waiting for a bus. The bus comes once every 10 minutes, and then the exponential is your waiting time. This is particularly true for events coming from a Poisson process. The density function for x given lambda is lambda times e to the minus lambda x. This is for non-negative values of x. The expected value is 1 over lambda, and the variance is 1 over lambda squared. So in the case of a bus that comes once every 10 minutes, the rate is 1/10. Another example is the uniform distribution. We saw this already in the case where it's a uniform on 0, 1, but it could be on a larger interval. In fact, the endpoints could be unknown. It could be uniform between endpoints theta 1 and theta 2. This case, we'll write its density, x given theta 1 and theta 2, as 1 over theta 2 minus theta 1 times the indicator function that x is between theta 1 and theta 2. Final example I want to mention right now is the normal distribution, also known as the Gaussian distribution. We say that x follows a normal distribution with mean mu and variance sigma squared. In this case, its density function is 1 over the square root of 2 pi sigma squared times e to the minus 1 over 2 sigma squared x minus mu squared. This has mean mu and variance sigma squared. In the supplemental material are some additional important distributions, such as the gamma distribution and the beta distribution. Next, let's do a brief review of the frequentist approach to inference, which will be useful for contrasting with the Bayesian approach. Under the frequentist paradigm, we view the data as a random sample from some larger, potentially hypothetical population. We can then make probability statements, i.e. long-run frequency statements, based on this larger population. As an example, let's suppose we flip a coin 100 times, and we get 44 heads and 56 tails. We can view these 100 flips as a random sample from a much larger, infinite hypothetical population of flips from this coin. In this case, we can say that each flip x sub I follows a Bernoulli distribution with some probability p. In this case, p may be unknown, but we're assuming it's fixed because we have a particular physical coin. We can ask what's our best estimate of the probability of getting a head, our estimate of p. We can also ask how confident are we in that estimate. We can start down the mathematical approach by applying the central limit theorem. Appealing the central limit theorem says that the sum of the 100 flips, sum of the x sub i's, will follow approximately a normal distribution with mean 100 times p and variance 100 times p times 1 minus p. Here I'm writing the squiggle with the dot above and below to mean approximately follows the distribution. By the central limit theorem, we have this distribution, and so by properties of normals, 95% of the time, we'll get a result within 1.96 standard deviations of the mean. Thus, we can say 95% of the time, we expect to observe between 100p minus 1.96 times the square root of 100p 1 minus p, and 100p plus 1.96 times the square root of 100 times p times 1 minus p. In this case, we've observed 44 heads. So then we can estimate the probability of getting a head and write that p hat, our estimate of p, as 44 over 100. We can then go back and plug this value into our theoretical quantity. This is what's referred to as a confidence interval in this case. Confidence interval we may abbreviate CI. The confidence interval is then going to be 44 plus or minus 1.96 times the square root of 44 times 0.56. Or in this case, this is 44 plus or minus 9.7, or the interval that goes from 34.3 to 53.7. So we can say that we're 95% confident that p is in the interval 0.343 to 0.537. We're 95% confident that the true probability of getting ahead is in this interval. So if we want to ask the question, do we think this is a fair coin, then it is reasonable that this is a fair coin because 1/2 is in this interval. But we can also step back and say, what does this interval really mean? What does it mean when I say we're 95% confident? Under the frequentist paradigm, what this means is we have to think back to our infinite hypothetical sequence of events. So if we were to repeat this trial an infinite number of times, or an arbitrary large number of times, each time we create a confidence interval in this way based on the data we observe, then on average, 95% of the intervals we make will contain the true value of p. This makes sense as a long-run frequency explanation. On the other hand, we might want to know something about this particular interval. Does this interval contain the true p? What's the probability that this interval contains the true p? Well, we don't know for this particular interval, but under the frequentist paradigm, where we're assuming that there is a fixed right answer for p, either p is in that interval or it's not in that interval. And so technically, from a frequentist perspective, the probability that p is in this interval is either 0 or 1. This is not a particularly satisfying explanation. On the other hand, when we get to the Bayesian approach, we will be able to compute an interval and actually say the probability that p is in this interval is 95%, based on a random interpretation of an unknown parameter. Let's do another example. Consider a hospital where 400 patients are admitted over a month for heart attacks, and a month later, 72 of them have died, and 328 of them have survived. We can ask, what's our estimate of the mortality rate? Under the frequentist paradigm, we must first establish our reference population. What do we think our reference population is here? One possibility is we could think about heart attack patients in the region. Another is we could think about heart attack patients that are admitted to this hospital, but over a longer period of time. Both of these might be reasonable attempts, but in this case, our actual data are not a random sample from either of those populations. We could sort of pretend they are and move on, or we could also try to think harder about what a random sample situation might be. One would be is we could think about all people in the region who might possibly have a heart attack and might possibly get admitted to this hospital. It's a bit of an odd hypothetical situation, and so there are some philosophical issues with the setup of this whole problem within the frequentist paradigm. In any case, let's forge forward and think about how we might do some estimation. We can say each patient comes from a Bernoulli distribution with unknown parameter theta. I'm now going to use the Greek letter theta because this is an unknown we're really trying to estimate. So the probability that yi equals 1 is equal to theta for all the individuals admitted. In this case, we're going to say that a success is mortality. The probability density function for the entire set of data we can write in vector form. Probably all of the y's take some value little y, given a value of theta. So this is the probability y1 takes some value little y1, y2 takes some value little y2, 0 or 1, and so on up to yn. Because we're viewing each of these as independent, then this is just the probability of each of these individual ones. So we can write this in product notation. And applying what we know about a Bernoulli, this then works out to be theta to the y sub I times 1 minus theta to the 1 minus y sub I. This is the probability of observing the actual data that we collected conditioned on a value of the parameter theta. We can now think about this expression as a function of theta. This is the concept of a likelihood. The likelihood function is this density function thought of as a function of theta. So we can write this L of theta given y it looks like the same function, but up here this is a function of y given theta, and now we're thinking of it as a function of theta given y. This is not a probability distribution anymore, but it is still a function for theta. One way to estimate theta is that we choose the theta that gives us the largest value of the likelihood. It makes the data the most likely to occur for the particular data we observed. This is referred to as the maximum likelihood estimate, or MLE, maximum likelihood estimate. It's the theta that maximizes the likelihood. In practice, it's usually easier to maximize the natural logarithm of the likelihood, referred to as the log likelihood. At this point, we usually drop the conditional notation on y as well. Since the logarithm is a monotone function, if we maximize the logarithm of the function, we also maximize the original function. In this case, we're dealing with data that are independent and identically distributed. Sometimes we write that then as y sub I, independent and identically distributed, IID, Bernoulli's theta. With independent identically distributed data, the likelihood is a product because they're independent. And therefore, when we take the log of a product, we get a sum, and sums are much easier to work with. So in this case, the log likelihood is the log of the product of theta to the y sub I, 1 minus theta to the 1 minus y sub I. The log of a product is the sum of the logs. And when we take the log of the inside, the log of theta to the y sub I, we'll get simplification there as well. So that becomes y sub I times the log of theta plus 1 minus y sub I times the log of 1 minus theta. Now we can pull the thetas out because they don't change with I as we take the sum. And so this turns into the sum of the y sub i's times the log of theta plus the sum of 1 minus y sub I times the log of 1 minus theta. How do we find the theta that maximizes this function? If you recall from calculus, we can maximize a function by taking the derivative and setting it equal to 0. So we take the derivative of the log likelihood, which I'm going to denote L prime of theta. Taking the derivative here, the derivative of log of theta is 1 over theta. And then we subtract from that 1 over 1 minus theta times the sum of the 1 minus y sub i's. We then set this equal to 0 and solve for theta. This gives us the sum of the y sub i's over theta hat equals the sum of 1 minus y sub I over 1 minus theta hat, where I'm plugging in now the theta hat that will make this set equal to 0. This results in a theta hat value of 1 over n times the sum of the y sub i's. This is in fact the same p hat that we got earlier from the other approach, or in this case 72 over 400 gives us a 0.18. And so that's our maximum likelihood estimate of the probability. You can see we got the same estimate as before, and this is one of the reasons that we use the obvious estimator. Maximum likelihood estimators have many desirable mathematical properties. They're unbiased, they're consistent, and they're invariant. In this case, we can also use the central limit theorem to give us an approximate confidence interval. From the central limit theorem, we get a confidence interval of theta hat plus or minus 1.96 times the square root of theta hat times 1 minus theta hat over n. In general, under certain regularity conditions, we can say that the MLE is approximately normally distributed with mean at the true value of theta and variance 1 over the Fisher information evaluated at theta hat. We'll return to the Fisher information later. The Fisher information is a measure of how much information about theta is in each data point. It's a function of theta. For a Bernoulli random variable, the Fisher information turns out to be 1 over theta times 1 minus theta. So the information is larger when theta is near 0 or near 1, and it's the smallest when theta is near 1/2. This makes sense because if you're flipping a coin and you're getting a mix of heads and tails, that tells you a little bit less than if you're getting nearly all heads or nearly all tails. That's a lot more informative about the value of theta. We'll return to the calculation of the information later in this course. Some more examples of maximum likelihood estimators. The exponential distribution. Suppose that we have samples from an exponential distribution with parameter lambda. Recall that the density is the product of lambda e to the minus lambda x sub I. Working on this product, we can actually collapse it so that this is lambda to the n times e to the minus lambda times the sum of the x sub i's. Thus the likelihood function as a function of lambda given x is lambda to the n, e to the minus lambda, sum of the x sub i's. If we take the log of this, we get the log likelihood, which is n log lambda minus lambda times the sum of the x sub i's. If we take the first derivative of this, we get n over lambda minus the sum of the x sub i's. We set that equal to 0. This gives us a maximum likelihood estimate lambda hat of n over the sum of the x sub i's or 1 over the average. This makes sense because the mean for an exponential distribution is 1 over lambda. And so if we take 1 over the sample average, we get a maximum likelihood estimate for lambda. Another example would be a uniform distribution. Suppose the x sub i's are IID from a uniform distribution where we know it starts at 0, but the upper endpoint theta is unknown. In this case, our density function is the product from I goes from 1 to n of 1 over theta, the density, times an indicator function that all of the observations are between 0 and theta. The likelihood then we can rewrite as L of theta given x. The product of these 1 over thetas is just theta to the minus n. Combining all the indicator functions, for this to be a 1, each of these has to be true. These are each going to be true if all of the observations are bigger than 0, as in the minimum of the x's is bigger than or equal to 0, and then the maximum of the x's is less than or equal to theta. In this particular case, we don't have a need for a logarithm. It's not actually going to help us. This is one of the few exceptions where the logarithm is not so helpful. So we'll look directly at the derivative of the likelihood itself. Derivative of theta to the minus n is minus n to the theta to the n minus 1, or minus n plus 1. And then this indicator function hangs around. They don't go away when you take derivatives, they just hang around. So now we can ask, can we set this equal to 0 and solve for theta? Well, it turns out this is not equal to 0 for any theta positive value. We need theta to be strictly larger than 0. This will never be 0 in that interval. However, we can also note that for theta positive, this will always be negative. If the derivative is negative, that says this is a decreasing function. So this function will be maximized when we pick theta as small as possible. What's the smallest possible value of theta we can pick? Well, we need, in particular, for theta to be larger than all of the x sub i's. And so the maximum likelihood estimate is the maximum of the x sub i's. We find the largest value of our data, and that's the smallest possible value theta could be, and that's our maximum likelihood estimate.
R is an open source statistical software package. It can be freely downloaded at rproject.org. There are other Coursera courses that provide detailed lessons on using R. Here I will just provide a short introduction to try to get you using R for the tasks needed in this course. First, launch R. R will do basic arithmetic. You can just type in an expression and hit enter. For example, 1 plus 2 times 3. As you can see, R knows the correct order of operations. R is an object-oriented environment, meaning that almost everything it does revolves around objects. Objects have names, and you can assign values to objects. For example, assigning a number. We can have an object x and assign the value 6 to it by typing in x equals 6. If we want to see the value, we can then enter the name of the object, and R will display the value. We can also use descriptive names. For example, total revenue, and assign that a value of 18.4. We can copy an object by assigning it to another name. If I have expenses, and that has a value of 6, but I already have 6 in x, I can just say expenses equals x. You can also assign the result of an operation to an object. For example, net profit would be total revenue minus expenses. We type in just the name of the object and it will give us the value in it. And you can see here that it's done the subtraction and saved to the result. You have some flexibility with names, but you can't use certain characters such as spaces in a name. R also has functions. To run a function, you type its name followed by parentheses with any arguments in the parentheses. For example, the C function will store a column of data, or it will concatenate data. We might want to assign to a variable z the set of data that goes 2, 3, 4, 5, and 6. You can see this data set is now stored in the object z. It stores it as a vector. We can then use functions to get more information or do analysis on these objects. We can ask, what's the mean or average of the values in z? We can ask, what's the variance of z? Or what's the standard deviation of z, which is the square root of the variance? We can use a function to create a sequence. The seq function creates a sequence, and we tell it what the starting point is, the from value, what the ending point is, the to value, and what increment we want to use, the by variable. This gives us a sequence that goes from point 1 to point 9, going in increments of point 1. Here we specified 3 arguments, and we've given them all by name. If we don't name the arguments, we can just specify numbers, and R will fill them in order. Any arguments we don't specify will get the default value, assuming they're at the end of the list. So for example, if we say sequence from 1 to 10, it's filling them in order. The first number we give is the from, the second number is the to, and then we haven't specified a by, and it will use the default, which in this case is by once at a time. And so this will give us a sequence that goes from 1 to 10. Let's take a brief look at one of the built-in data sets in R. This is the trees data set. This is a set of trees, and it gives us the diameter, the height, and the volume of the tree. We can learn some more by using the help function. This opens up a new window and gives us information about the data set, including references and some examples of analysis. It gives us some more definition showing that, indeed, this is a diameter, a height, and a volume. As you see here, there are labels for each of these columns. They're named. We can access these names in R by using the attach command. This says to look in the trees object for other additional names. We can ask what are the names by using the names command. And these are the same ones that we see when we look at the data set itself. We can then use these names to directly access these variables. For example, we want to make a histogram of the girth or diameter of these trees. When we say hist, it's a histogram function, and it automatically pops up a new window for us. From the histogram, we can see that most of the trees have diameters between 8 and 18 inches, with one larger tree. We can also make scatter plots, putting the girth on the x-axis and the height on the y-axis to see how height relates to diameter. As you can see here, in general, the wider the tree, the taller the tree. There's a function in R called pairs, which allows us to make all possible pairwise scatter plots for the data set. So if we say pairs of trees, we have each of the 3 variables plotted against each of the other ones. So for example, in this box here, we have girth on the x-axis and height on the y-axis. And this is exactly the plot that we just had previously. In the lower left here, we have girth on the x-axis and volume on the y-axis. And we can see there's a very strong relationship between total volume of timber in the tree and how wide the tree is. Similarly, there's a strong relationship between the height of the tree and the volume of the tree. In the upper corner, we have the mirror images of these plots with the variables on the opposite axes. And so this plot here in the upper right has volume on the x-axis and girth on the y-axis. Finally, we can get numerical summaries using the summary command. For each of the variables, this will give us the mean, the median, the range, and the quantiles. In the video lecture,
we talked about a hospital with 400 heart attack patients, of whom 72 die within 30 days and 328 are still alive. Let's plot the likelihood function for this example. We could use either a binomial likelihood or a Bernoulli likelihood. These are actually the same other than a constant term in the front, the combinatoric term for the binomial. It does not depend on theta. So we'll be getting the same answers. It's just a little rescaling on the vertical axis. It's much simpler to stick with the Bernoulli likelihood that doesn't have the combinatoric terms. The likelihood is a function of the mortality rate theta. So we'll create a function in R. We can use the function command and store our function in an object. We can call this object likelihood. Use the function command, and we specify what arguments this function will have. We'll need total sample size n, the number of deaths y, and the value of the parameter theta. We specify the function inside of curly braces. In this case, all we needed to do is return a computed value. So we'll use the return function to return that value, and here we just put in the likelihood formula, which in this case is theta to the y times 1 minus theta to the n minus y. To plot the likelihood, we'll create a sequence of points with mortality rates between 0 and 1, and then plot the likelihood values over that sequence. So I'll define a sequence of values for theta using the sequence command. Here we go from 0.01 to 0.99 in increments of 0.01. We can now plot this. We're going to call the likelihood function over this sequence using n equals 400, y equals 72, and our vector theta. This pops up a plot. And if we look carefully, we can see that the likelihood is maximized at the value 72 over 400, or 0.18. This might be a little bit difficult to see in the plot, and so one thing that can help is we can add a vertical line using the AB line command and say vertical line at 0.18. Adding that in makes it really clear that this likelihood is maximized at 72 over 400. We can also do the same with the log likelihood, which in many cases is easier and more stable numerically to compute. We can define a function for the log likelihood, say log like, which again is a function of n, y, and theta. Here, we'll return the value from the log likelihood, which is y times the log of theta plus n minus y times the log of 1 minus theta. Now we can plot the sequence against the log likelihood of that sequence. It's a smoother function, a little bit more difficult to see where the maximum is. Again, adding a vertical line helps us see the maximum at 0.18. Plotting this as a series of points doesn't give us necessarily the best picture. We could actually do this as a line plot instead. In R, we can use the up arrow to go back to a previous command we've run. So if I hit up 3 times, I can get back to the function or to one of the plots. Here I can add another argument. The plot command has many, many possible optional arguments. One of them is the type of plot. If I say type equals double quotation lowercase l, that tells R to make a line plot. In the video lecture, we talked about a hospital with 400 heart attack patients, of whom 72 die within 30 days and 328 are still alive. Let's plot the likelihood function for this example. The likelihood is a function of the mortality rate theta. We could use either a binomial likelihood or a Bernoulli likelihood. They are the same other than a constant term in the front the combinatoric term for the binomial that does not depend on theta. So we'll get the same answer either way, and it's easier to use the Bernoulli likelihood. We can plot this in Excel. We'll need to create a column of theta values and a column of likelihood values. For the theta values, we'll want it to go from 0.01 up to 0.99 in increments of 0.01. We can create this column by using the fill command. Edit, fill, series. We want to put the series in a column. We'll grow linearly, have a step value of 0.01, and go all the way up to the value of 0.99. So now Excel has filled it in from 0.01 up to 0.99. For the likelihood, we'll create a function. So we start with the equal sign to create a function. And this is theta to the y times 1 minus theta to the n minus y. The value of theta we're going to plug in is the value in the adjacent column. We take this to the y power, in this case y is 72. We'll multiply this by 1 minus theta to the n minus y, where n is 400 and y is 72. We have this formula now defined for the first row. What we can do is we can copy this formula and then paste it in to all the remaining cells. Excel has now filled in the likelihood values for us and recomputed them for each of the possible theta values. In order to make a plot of this, we'll use a chart. So I'll highlight the column with the likelihood values. Go to Charts, choose a line chart, and do a basic line chart. If you look carefully, you may be able to see that the likelihood function is maximized at 0.18, or 72 over 400. This is the maximum likelihood estimate. We could also do the same with the log likelihood. This formula is going to be y times the log of theta plus n minus y times the log of 1 minus theta. So we can enter this as a formula in Excel with equals y is 72 times the log of the theta value from this column, this row, plus n minus y times the log of 1 minus the theta value. Again, we can copy that into the remaining cells. Paste. We highlight this column and create a line chart for the log likelihood. It's a little bit harder to see, but the log likelihood is also maximized at 0.18. Let's look at another simple example. This one just has two possible outcomes. This way we can compare both the frequentist and the Bayesian approaches to inference. Suppose your brother has a coin which you know to be loaded so that it comes up heads 70% of the time. He then comes to you with some coin, you're not sure which one, and he wants to make a bet with you, betting money that it's going to come up heads. You're not sure if it's the loaded coin or if it's just a fair one, so he gives you a chance to flip it 5 times and just check it out. You flip it 5 times and you get 2 heads and 3 tails. And now you have a decision point to make. Which coin do you think it is? And how sure are you about that? So in order to perform inference, we need to define a likelihood. In this case, we'll start by defining the unknown parameter theta. And this is either the coin is fair or it's a loaded coin. So our unknown parameter is which coin it is. Is it a fair coin or is it the loaded coin? Our data are going to be 5 flips of this coin. It's a binomial with 5 flips, and the question is, what's that probability? So we can write a likelihood, f of x given theta, as if it's the fair coin, this will be 5 choose x, 1/2 to the 5th. If it's the loaded coin, this will be 5 choose x, 0.7 to the x, 0.3 to the 5 minus x. We can rearrange this also to write it with indicator functions. Now in this case, we've observed x equals 2. What's our likelihood? We can write f of theta given x equals 2. In this case, I'm just going to switch back to using f instead of using a capital L for likelihood. On the frequentist paradigm, we're typically using capital L's. As we move over to the Bayesian paradigm, we're just going to use f's everywhere. It's really just a notational thing. We can now plug in x equals 2, and we get 0.3125 if theta equals fair, and 0.1323 if theta equals loaded. So we see that having observed 2 heads, the likelihood is higher for theta equals fair than for theta equals loaded. Thus we can say the maximum likelihood estimate, theta hat, is that this is a fair coin. That's our maximum likelihood estimate. Given the data, it is most likely that the coin is fair. That's a good point estimate, but then how do we answer the question, how sure are you? This is not a question that's easily answered in the frequentist paradigm. Another question is that we might like to know, what is the probability that theta equals fair given we observed 2 heads? In the frequentist paradigm, the coin is a physical quantity. It's a fixed coin, and therefore it has a fixed probability of coming up heads. It either is the fair coin or it's not the loaded, or it's the loaded coin. In this case, the probability it's fair given x equals 2 is just the probability that it's fair because it's a fixed coin. And this probability is either 0 or 1. This is not a particularly satisfying answer. As a result, let's take a look at how we'd solve this problem under Bayesian inference and see what type of answer we get there. Now let's take a look at the Bayesian approach. An advantage of the Bayesian approach is it allows you to easily incorporate prior information when you know something in advance of looking at the data. This is difficult to do under the frequentist paradigm. In this case, we're talking about your brother. You probably know him pretty well. Because you've been around him a bunch, and this isn't the first time he's come to you with a coin, you may have some information on this that you want to incorporate into the problem. So suppose you think that before you've looked at the coin, there's a 60% probability that this is the loaded coin. In this case, we put this into our prior. Our prior is that the probability the coin is loaded is 0.6. We can now update our prior with the data to get our posterior beliefs, and we do this using Bayes' theorem. F of theta given x is going to be f of x given theta times f of theta over all possibilities for theta of f of x given theta, f of theta. In this case, the only two possibilities for theta are that it's fair or loaded. So this likelihood is the same as what we saw before, but this time we'll be adding in the prior. One half to the fifth times the prior probability that the coin is fair, plus 0.7 to the x, 0.3 to the 5 minus x, times the prior probability it's loaded, if we plug in our observed data x equals 2, this will work out to be 0.0125 theta equals fair, plus 0.0079 theta equals loaded, over 0.0125 plus 0.0079. Simplifying this, we get 0.612 theta equals fair, plus 0.388 theta equals loaded. As you can see in the calculation here, we have the likelihood times the prior in the numerator, and in the denominator, we have a normalizing constant, so that when we divide by this, we'll get answers that add up to 1. These numbers match exactly in this case because it's a very simple problem. But this is the concept that goes on. What's in the denominator here is always a normalizing constant, so that in the end of the day, we get probabilities. And so we can say at the end of the day here, the probability theta equals loaded given x equals 2. So our posterior probability that this is the loaded coin works out to be 0.388. Isn't that a much more satisfying answer under the Bayesian approach, where we get a probability, and we can interpret this probability? We can say, what is the probability that we think this coin is loaded after we've observed some data? This is a much more intuitive answer than we get under the frequentist paradigm. We can also examine what would happen under different choices of prior. We did this calculation with a prior probability of 0.6 for the coin being loaded, but we might have a different idea. We want to use a different probability. We can use anything between 0 and 1. Or maybe somebody else is coming in with a different perspective, and they want to see what their answer is using a different prior. One possibility is that we could say the probability the coin is loaded in prior is 1/2. This might represent an attempt to say, we're not sure what's going on. It's equally likely that it's the loaded coin or the fair coin. Not that these are necessarily equally likely outcomes. Taking a prior probability of 1/2, we can put it through Bayesian machinery, and that will lead us to get a posterior probability, theta equals loaded, given we observe 2 data points. That works out to be 0.297. We might have a different idea. We might think, because this is our brother and we know him well, that the prior probability it's going to be the loaded coin is 0.9. He really likes to use the loaded coin. If this is the case, then when we go through the calculations, we'll get a posterior probability that this is a loaded coin of 0.792. In this case, the Bayesian approach is inherently subjective. It represents your own personal perspective. And this is an important part of the paradigm. If you have a different perspective, you will get different answers. And that's okay. It's all done in a mathematically rigorous framework, and it's all mathematically consistent and coherent. In the end, we get results that are interpretable. It makes sense. We want to ask, what is the probability the coin is loaded after we've looked at some data, incorporating our beliefs about our past experiences with our brother? This way, we get intuitive answers. We can say the probability it's loaded is 0.3, or the probability it's loaded is 0.8. Under the frequentist paradigm, we can't get a good answer for what is the probability the coin is loaded. The machinery just is not set up that way. It's not possible to get a good confidence interval. What would it even mean to have a confidence interval for is the coin loaded? The frequentist approach has a number of buried assumptions. We need to make a choice, which is inherently subjective, about what is our reference population. about what is our likelihood. These are assumptions that are inherently subjective that are buried deeper into the frequentist paradigm. And so there's an attempt to pretend that everything is objective. Under the Bayesian paradigm, we're explicit that this is a subjective and personal approach, but we can also be explicit about what all of our assumptions are, and then see how our answers depend on our assumptions. Let's take a look at a more general case. Continuous version of Bayes' theorem is that f of theta given y is equal to f of y given theta times f of theta over f of y, or we can write that of f of y given theta times f of theta over the integral of f of y given theta times f of theta d theta. We can see that this is the likelihood times the prior divided by a normalizing constant. Likelihood times the prior, and then this is just a constant that will make sure that this integrates to 1, because we need this at the end of the day to be a proper probability density function. And it's clear that this will integrate to 1 because we're dividing by exactly what it is on top. In practice, sometimes this integral can be a pain to compute. And so we may work with looking at saying this is proportional to the likelihood times the prior. And if we can figure out what this looks like and just put the appropriate normalizing constant on at the end, we don't necessarily have to compute this integral. So for example, suppose we're looking at a coin and it has unknown probability theta of coming up heads. Suppose we express ignorance about the value of theta by assigning it a uniform distribution. So we can write f of theta is just the indicator function that theta is between 0 and 1. Now we flip the coin and we get one head. We want to say, having observed one flip of the coin, what's our posterior probability distribution for theta? So f of theta given y is this expression here. In practice, trying to compute this in more general form, we can do it, but it'll be a little bit more work. Let's go ahead and plug in f of theta given we've observed a head, given y equals 1. So this will be theta to the 1 minus theta to the 0, times the indicator function that theta is between 0 and 1, divided by the integral of all of this. D theta. So this simplifies on top to theta times the indicator function. In the bottom, this will be the integral now from 0 to 1 of theta d theta. The integral of theta d theta is going to be 1/2 theta squared. We evaluate that on 0, 1, and we just get 1/2. So this whole thing simplifies to 2 theta times the indicator function that theta is between 0 and 1. As a side note, we could do this whole thing in terms of proportionality. F of theta given y is proportional to f of y given theta times f of theta. And so we can say that's proportional to theta times the indicator function, that theta is between 0 and 1. And then we just need to normalize this so that it will integrate to 1. And as we saw earlier, then, taking the integral of this, the correct normalizing constant is that we just stick a 2 on this. So this is the same type of approach. We get to the same answer if we stick the normalizing constant on at the end, if we can recognize what this is at the end. In some cases later, this will turn out to be much easier to just use the proportionality approach rather than a full equality approach and trying to work out the integral. Let's take a look at plotting the prior and the posterior. So plotting the prior density for theta, it looks like this. It's uniform on 0, 1. The posterior density is a little bit different. We saw that is now 2 theta, and so that looks like this. So graphically, we can see that under the posterior, theta is much more likely to be close to 1 than to 0 because we saw one head. We can look at posterior and prior interval estimates. Under the prior, the probability that theta is between 0.025 and 0.975 is 0.95. It's a 95% prior probability interval. We can also say the probability theta is greater than 0.05 is 0.95. Graphically, we can think about that as thinking about integrating regions under the density. But because it's uniform, it's really simple to compute. We can then think about posterior interval estimates. Under the posterior density, we can ask, what's the probability that theta is between 0.025 and 0.975? In this case, we have a little integral to do. So we integrate from 0.025 to 0.975 the density of 2 theta d theta. The integral of 2 theta is going to be theta squared. And so this works out to be 0.975 squared minus 0.025 squared. And this happens to be 0.95. And so it turns out in this case to be the same as under the prior. You can look at the picture and think about just moving some of the pieces around. If you're chopping off both ends, we still end up with the same amount in the middle. However, if we ask the second question under the posterior, what's the probability theta is bigger than 0.05? This is now, when we run through the integral, 1 minus 0.05 squared, and this turns out to be 0.9975. There's very little chance now that theta is less than 0.05, having observed a head. This is a big change now from the prior to the posterior. Now these we're looking at sort of intervals we would get from the prior and saying what's their posterior probability. In other cases, we may want to ask, what is a posterior interval of interest? What's an interval that contains 95% of posterior probability in some meaningful way? This would be equivalent then to a frequentist confidence interval in a concept. We can do this in several different ways. The two main ways that we make Bayesian posterior intervals, or credible intervals, are equal-tailed intervals and highest posterior density intervals. In the case of an equal-tailed interval, we put an equal amount of probability in each tail. So to make a 95% interval, we'll put 0.025 in each tail. To be able to do this, we're going to have to figure out what the quantiles are. So we're going to need some value q. Say the probability theta is less than q in posterior, given y equals 1. Here we can get this by integrating from 0 to q, 2 theta d theta. And again, we'll see that's just q squared. So we can say an interval that goes from the square root of 0.025 to the square root of 0.975, and plugging in those numbers, is going to be 0.158 to 0.987. Under the posterior, that will have probability 0.95. This is an equal-tailed interval in that the probability that theta is less than 0.158 is the same as the probability that theta is greater than 0.987. And we can say, under the posterior, there's a 95% probability that theta is in this interval. Another approach is what's referred to as highest posterior density, or HPD. Here we want to ask, where in the density is it highest? And so in this case, we want to say, well, about here are the highest levels, and so this interval is going to go between these 2 points. Theoretically, this will be the shortest possible interval that contains a given probability, in this case a 95% probability. We can see here that it's going to go all the way up to 1 just from the graph. So we're asking, what's the probability theta is bigger than some value? And looking at the quantiles again, that value is going to be the square root of 0.05. I should write that this is a posterior. And so we can say the probability theta is greater than 0.224 is 0.95. So this is the shortest possible interval that under the posterior has probability 0.95. It's theta going from 0.224 up to 1. Let's think about what we have here. The posterior distribution describes our understanding of our uncertainty, combining our prior beliefs and the data. We have a probability density function, so at the end of the day, we can make intervals and talk about probabilities of theta being in the interval. This is a much more satisfying approach than the frequentist approach, where we get confidence intervals, but we can't say a whole lot about the actual parameter relative to this confidence interval. We can only make long-run frequency statements about a lot of hypothetical intervals. In this case, we can legitimately say the posterior probability theta is bigger than 0.05 is 0.9975, or we believe there's a 95% probability that theta is in between 0.158 and 0.987. Frequentists can't do this. Bayesians represent uncertainty with probabilities. So the coin itself is a physical quantity. It may have a particular value for theta. It may be fixed, but because we don't know what that value is, we represent our uncertainty about that value with a distribution. And at the end of the day, we can represent our uncertainty, collect it with the data, and get a posterior distribution and make intuitive statements. How do we choose a prior? Our prior needs to represent our personal perspective, our beliefs, and our uncertainties. Theoretically, we're defining a cumulative distribution function for the parameter. So in particular, we're defining probability that theta is less than or equal to some value c for all possible c on the real line. So this is true for an infinite number of possible sets. We're defining probabilities. This isn't practical to do, and it would be very difficult to do coherently so that all the probabilities were consistent. In practice, we work with a convenient family that's sufficiently flexible such that a member of the family will represent our beliefs, and we can build in external information if available, such as previous experiments. Generally, if one has enough data, the information in the data will overwhelm the information in the prior, and so the prior is not particularly important in terms of what you get for the posterior. Any reasonable choice of prior will lead to approximately the same posterior. However, there are some things that can go wrong. Suppose we choose a prior that says the probability theta equals 1/2 equals 1, and thus the probability theta equals any other value is 0. If we do this, we'll see our posterior, f of theta given y, which is proportional to f of y given theta, f of theta, turns out to be just f of theta. Our data won't factor in if we only put probability 1 on a single point in our prior. We can also think of this prior as a point mass at 1/2, such as a Dirac delta function. So in the Bayesian context, events with prior probability 0 have posterior probability 0. Events with prior probability 1 have posterior probability 1. Thus, a good Bayesian will not assign probability 0 or 1 to any event that has already occurred or already known not to occur. A useful concept in terms of choosing priors is that of calibration, calibration of predictive intervals. So if we make an interval where we're saying we predict 95% of new data points will occur in this interval, it would be good if, in reality, 95% of new data points actually did fall in that interval. How do we calibrate to reality? This is actually more of a frequentist concept, but it is important for practical statistical purposes that our results do reflect reality. So we can compute a predictive interval. This is an interval such that 95% of new observations are expected to fall into it. So it's an interval for the data, for y or x, rather than an interval for theta, like we've been looking at. In particular, we can write this as f of y is the integral of f of y given theta times the prior f of theta d theta. We can also see this as integrating the joint density of y and theta, integrating out theta to get the marginal for y. So this is our prior predictive before we observe any data. Suppose we're going to flip a coin 10 times and count the number of heads we see. We're thinking about this in advance of actually doing it, so we're interested in the predictive distribution. How many heads do we predict we're going to see? This, of course, will depend on the coin itself. What's the probability it shows up heads? So we'll need to choose a prior. In terms of the number of heads, I can write x for the number of heads as x being the sum, as I goes from 1 to 10, of y sub I, where y is each individual coin flip, y1 through y10. If we think that all possible coins or all possible probabilities are equally likely, then we can put a prior for theta that's flat over the interval from 0 to 1. So now we can ask, what's our predictive distribution for the number of heads we'll see? X can take possible values 0, 1, 2, 3, up to 10. The predictive distribution, f of x, is going to be the integral of the likelihood, f of x given theta, times the prior, f of theta, d theta. So writing this out, we have a binomial likelihood. So we're going to integrate theta from 0 to 1. Binomial likelihood is 10 factorial over x factorial 10 minus x factorial times theta to the x, 1 minus theta to the 10 minus x, times our prior, 1 d theta. Note that because we're interested in x at the end, it's important that we distinguish between a binomial density and a Bernoulli density. So here we just care about the total count rather than the exact ordering, which would be Bernoulli's. For most of the analyses we're doing, where we're interested in theta rather than x, the binomial and the Bernoulli are interchangeable because the part in here that depends on theta is the same. But here we care about x for a predictive distribution, so we do need to specify that we're looking at a binomial because we're looking at counts. All right, how do we simplify this? This is an integral that might be sort of difficult to see immediately how to do. Let's recall some interesting pieces of math. First, recall that for an integer n, we can write n factorial is equal to gamma of n plus 1. The gamma function is a generalization of the factorial function and can be used for non-integers. The other thing is that if z follows a beta distribution with parameters alpha and beta, then the density for z, f of z, we can write as gamma of alpha plus beta over gamma of alpha times gamma of beta times z to the alpha minus 1 times 1 minus z to the beta minus 1. All right, so we're interested in a beta distribution here because we can simplify this piece to look like a beta distribution, or beta density. So let's do a little simplification. We can write this 10 factorial as gamma of 11, and then write that as gamma of x plus 1 times gamma of 11 minus x, and then theta to the x plus 1 minus 1 times 1 minus theta to the 11 minus x minus 1 d theta. This may not look that much simpler, but it is closer to the beta density. Now if I just rearrange a little bit with the gamma terms, I can pull out this gamma of 11 and replace it with a gamma of 12. Now what I have inside the integral here is exactly a beta density, where the alpha parameter is x plus 1, and the beta parameter is 11 minus x. Because it's a beta density, we know all densities integrate up to 1. So this whole integral here is just 1. So we can write this as gamma of 11 over gamma of 12 times 1. Much easier way to do integrals. And then switching back to a factorial notation, gamma of 11 is 10 factorial, gamma of 12 is 11 factorial. So this whole thing simplifies to 1 over 11 for possible x values of 0, 1, 2, and so on up to 10. Thus we see that if we start with a uniform prior, we then end up with a discrete uniform predictive density for x. If all possible coins, or all possible probabilities, are equally likely, then all possible x outcomes are equally likely. What about after we've observed data? What's our posterior predictive distribution? So in this case, we can think about flipping a coin. We don't know what the probability comes up heads is. But suppose we observe after one flip, we got a head the first time. We want to ask, what's our predictive distribution for the second flip, given that we saw a head on the first flip? So in this case, we can think about a posterior predictive distribution, f of y2 given y1. And so we can write that as the integral of f of y2 given theta and y1 times f of theta given y1 d theta. Again, we're integrating out theta, but this time we're going to use the posterior distribution for theta instead of the prior distribution for theta. In most cases, y2 we're treating as independent from y1, so that will imply that we can simplify this expression and just say it's y2 given theta times f of theta given y1 d theta. So again, you can see this looks very much like the prior predictive, except we're using the posterior distribution for theta instead of the prior distribution. As a particular example, again, suppose we're thinking of a uniform distribution for theta, and we observe the first flip, y1 equals 1. We get a heads. What do we predict for the second flip? This is no longer going to be a uniform distribution like it was in the first case, because we have some data. We have one head coming up on the first flip. So this gives us some information about the coin. We're now going to think it's more likely we're going to get a second head, because it's more likely that theta is at least 1/2 and possibly larger than 1/2. So let's compute this. f of y2 given y1 equals 1 is equal to the integral. In this case, integral goes from 0 to 1 of theta to the y2, 1 minus theta to the 1 minus y2, times the posterior, which is 2 theta d theta. We can simplify this a bit to be 2 times theta to the y2 plus 1 times 1 minus theta to the 1 minus y2 d theta. We could work this out in a more general form, but in this case, y2 has to take the value 0 or 1. The next flip is either going to be heads or tails. So it's easier to just plop in a particular example. We can compute the probability y2 equals 1 given y1 equals 1. And so here we can just plug in a 1 for y2, and we get the integral from 0 to 1 of 2 theta squared d theta. And so doing that integration, we get a theta cubed, and this just works out to be 2/3. Thus, the complement, probability of getting a head, given we saw a tail the first time, is going to be 1/3. So we can see here that the posterior is a combination of the information in the prior and the information in the data. In this case, our prior is like having two data points, one head and one tail. Saying we have a uniform prior for theta is actually equivalent, in an information sense, to saying we have observed one head and one tail. And so then, when we do go ahead and observe one head, it's like we now have seen two heads and one tail. And so our predictive distribution, our posterior predictive distribution for the second flip says, well, if we have two heads and one tail, then we have probably 2/3 of getting another head, and probably 1/3 of getting a tail. When we use a uniform prior for a Bernoulli likelihood, we get a beta posterior. Likelihood y given theta is sum of theta to the sum of the y sub i's, 1 minus theta to the n minus sum of the y sub i's. Our prior for theta is just a uniform, and thus our posterior for theta is the likelihood times the prior over the integral of the likelihood times the prior d theta, so that it integrates up to 1. So the likelihood, again, is theta to the sum of the y sub i's, 1 minus theta, n minus the sum of the y sub i's, times the indicator function for the prior. And then in the denominator, we just make sure that this integrates up to 1. Rather than try to work out this integral, we use the common trick of recognizing it as the kernel of a beta distribution. And so we'll rearrange the terms in here to make it be exactly a beta distribution so that this integral will be 1 and it will go away. Beta distributions have these gamma functions in them. And so here's what we're going to need to put in to make this all work out correctly. And so this integral now is going to be gamma of n plus 2 over gamma of sum of the y sub i's plus 1 times gamma n minus the sum of the y sub i's plus 1 times theta to the sum of the y sub i's, 1 minus theta, n minus the sum of the y sub i's, d theta. What we have here now is a beta distribution, and so it integrates up to 1. And thus, this whole expression simplifies to gamma n plus 2 over gamma sum of the y sub i's plus 1 times gamma n minus the sum of the y sub i's plus 1 times theta to the sum of the y sub i's, 1 minus theta to the n minus the sum of the y sub i's, times the indicator function that theta is between 0 and 1. Thus we see the posterior for theta, given y, follows a beta distribution with parameters sum of the y sub I plus 1 and n minus the sum of the y sub i's plus 1. In fact, the uniform distribution is a beta 1, 1, and any beta distribution is conjugate for the Bernoulli distribution. Any beta prior will give a beta posterior. Recall the beta prior looks like f of theta is gamma of alpha plus beta over gamma of alpha, gamma of beta, times theta to the alpha minus 1, 1 minus theta to the beta minus 1, over the interval from 0 to 1. Thus we can look at the posterior for theta given y. This is proportional to the likelihood times the prior, which is theta to the sum of the y sub i's, 1 minus theta to the n minus sum of the y sub i's times this prior, gamma of alpha plus beta over gamma of alpha, gamma of beta, theta to the alpha minus 1, 1 minus theta to the beta minus 1 over the interval as theta goes from 0 to 1. In terms of proportionality, we only need to keep the things that have thetas in them, so we can drop this normalizing constant and collect the theta terms. Theta plus sum of the y sub i's minus 1, 1 minus theta to the beta plus n minus sum of the y sub i's minus 1 over the interval from 0 to 1. We thus see this is a beta distribution, so theta given y follows a beta distribution with parameters alpha plus sum of the y sub i's and beta plus n minus the sum of the y sub i's. When alpha and beta are both 1, as in the uniform distribution, we get the result that we had earlier. This whole concept now of starting with the beta prior and getting a beta posterior is a really convenient one. This whole process, where we choose a particular form of prior that works with the likelihood, is called using a conjugate family. A family of distributions is referred to as conjugate if when you use a member of that family as a prior, you get another member of that family as your posterior. The beta distribution is conjugate for the Bernoulli distribution. It's also conjugate for the binomial distribution. The only difference in the binomial likelihood is that there's an n choose x combinatoric term. Since that does not depend on theta, then we get the same posterior. We often use conjugate priors because they make life much more simple. As we're working out posteriors, if we can't recognize this form, we get some intractable integral in the denominator, and trying to work out that integral can be problematic. It can get complicated really quickly. So sticking to conjugate families allows us to get closed form solutions. If the family is flexible enough, then you can find a member of that family that closely enough represents your beliefs. We can represent this model as a hierarchy. The observations y1 through yn follow a Bernoulli likelihood. Theta is our primary parameter. It depends on alpha and beta, and we give theta a beta prior. Alpha and beta, we might give particular values, alpha naught and beta naught. We refer to alpha and beta as hyperparameters. Typically, what we'll be doing here is we'll set these equal to particular values. But in a more complicated problem, you might also want to have more flexibility by putting priors on alpha and or beta. We can thus extend this hierarchy to more levels. In complicated problems, this may provide some added value and added flexibility. In simple problems, this tends to be more work without providing much additional value. So these sorts of hierarchical models will be beyond the scope of this course. Returning to the model where we have a Bernoulli likelihood with n observations, or a binomial likelihood, and using a beta prior, we get a posterior, which is beta alpha plus sum of the y sub i's, beta plus n minus sum of the y sub i's. Here it is clear how both the prior and the data contribute to the posterior. For a prior, which is a beta alpha beta, this is equivalent to having alpha plus beta additional observations. We can say this is the effective sample size of the prior. And we'll see how this is so in the next calculation. recall that the expected value, or mean of a beta, is its first parameter over the sum of the parameters. So in the case of our posterior here, its posterior mean is alpha plus sum of the y sub i's divided by alpha plus sum of the y sub i's plus beta plus n minus sum of the y sub i's. We can then write this, simplifying as alpha plus sum of the y sub i's over alpha plus beta plus n. This can further be decomposed as alpha plus beta over alpha plus beta plus n times alpha over alpha plus beta plus n over alpha plus beta plus n times sum of the y sub i's over n. What we see here is that we get the posterior mean is equal to a prior weight times the prior mean plus a data weight times the data mean. So the mean of the data is the sum of the y sub i's over n. The prior mean is alpha over alpha plus beta. The weight for the prior and the weight for the data add up to 1. So they are weights. And so the posterior mean is a weighted average of the prior mean and the data mean. We can also see here, here's the n for our sample size. And so the corresponding term over here tells us the effective sample size of the prior. Thus, the effective sample size of the prior for a beta prior on a Bernoulli or binomial likelihood is alpha plus beta. This effective sample size also gives you an idea of how much data you would need to make sure that your prior doesn't have much influence on your posterior. If alpha plus beta is small compared to n, then the posterior will largely just be driven by the data. If alpha plus beta is large relative to n, then your posterior will be largely driven by the prior. Thinking about intervals, recall that a frequentist 95% confidence interval for theta is theta hat plus or minus 1.96 times the square root of theta hat 1 minus theta hat over n. Now as a Bayesian, we can make a 95% credible interval using our posterior distribution for theta. We would use a computer package, such as R, to numerically find the values for the interval. We can find an interval that actually has 95% probability of containing theta, and this is a true probability statement. For a confidence interval, we can't make a probability statement that theta is in the interval. Sequential analysis is also straightforward in Bayesian statistics. Suppose we start with a prior, f of theta, and we observe n data points. We observe y1 through yn. We then update our prior. We get a posterior theta given y1 through yn. So far, so good. Then suppose you come in the next day and you observe more data. We observe m more data points, yn plus 1 through yn plus m. Now that we have more data, can we update again? And indeed we can. We treat yesterday's posterior as today's prior. So we now use theta given y1 through yn as our prior, update it with data, and get a new posterior, theta given y1 through yn plus m, all of the data. And so we can just chain these together, doing a sequential update every time we get new data. We can get a new posterior, and we just use our previous posterior as the prior to do another update using Bayes' theorem. In this way, we actually get the same answer mathematically as if we started with the prior and then all the data came at once and we did a single update with Bayes' theorem. We will get the exact same posterior. So in the Bayesian paradigm, this is consistent whether we're doing sequential updates or we do a single batch update. This is very different from the frequentist scenario where you can't do sequential updates in this way, and you get different answers depending upon when you observe your data and how you combine them. One of the earlier areas where Bayesian statistics was accepted under government regulation was in the medical device testing area, and this is because of its ability to do sequential updates. With medical devices, you often have very small sample sizes, but you're only making minor updates to devices and you're doing new trials. The ability of Bayesian statistics to do easy sequential updates made it very practical and appealing for the medical device testing industry.
This segment will look at using R for exploring the beta binomial conjugate analysis and working with binomial and beta distributions in R. Suppose we were giving two students a multiple choice exam with 40 questions, where each question has 4 choices. We don't know how much the students have studied for this exam, but we think that they will do better than just guessing randomly. So here up in the comments section, I'm giving you the background and we'll pose 7 questions. First, what are our parameters of interest? Next, what is our likelihood? What prior should we use? For this prior, for theta, we can ask what's the prior probability that theta is greater than 1/4, which would be guessing randomly, theta is greater than 1/2, or theta is greater than 0.8. Now suppose the first student takes the test and gets 33 of the 40 questions right. Calling their parameter theta1, we can ask what's the posterior distribution for their parameter, and what's the posterior probabilities that will be greater than 1/4, 1/2, or 0.8. What's a 95% posterior credible interval for this parameter? Now thinking about the second student, suppose they get 24 questions right. What's the posterior distribution for that parameter? What's the posterior probability it's greater than 1/4, 1/2, or 0.8? And what's a 95% credible interval for it? Finally, what's the posterior probability that theta1 is greater than theta2? That the first student has a better chance of getting a question right than the second student. All right, we'll move on to solutions. The first two are more just theory. Our parameters of interest are theta1 being the true probability that the first student will answer a question correctly, and theta2 being the true probability the second student will answer a question correctly. We're going to use a binomial likelihood with n equals 40, and then probabilities theta, either theta1 or theta2. And this is assuming that each question is independent and that the probability a student gets each question right is the same for all questions for that student. What prior should we use? The conjugate prior for a binomial likelihood is a beta prior. The information we have is that we think they will do better than just guessing randomly, so the prior mass should be largely above 0.25. We'll want a prior mean bigger than 1/2, maybe say 2/3. So what I'm going to do is I'm going to make a sequence of possible theta values that goes from 0 to 1 in increments of 1/100th. And then we can plot some different beta priors. We can start by plotting the default prior, which is a uniform, or a beta 1,1. So here's our default uniform prior. All values, probabilities between 0 and 1 are equally likely, but this does not encode our belief that we think they're going to do better than just guessing randomly. So let's try a beta distribution that has prior mean 2/3. For example, a beta distribution with parameters 4 and 2. So now we can see we're moving most of the mass higher.
although there's still some mass down here below 0.25. As we increase the parameter values, that increases the effective sample size and concentrates the distribution. So let's try a beta distribution with parameters 8 and 4, which still maintains a prior mean of 2/3. This distribution now is more concentrated, and you can see pretty much all the mass is between 0.25 and 1. So this seems like a reasonable distribution to use as a prior for this problem. We can now ask, what are the prior probabilities that the parameter will be bigger than 1/4, 1/2, or 0.8? We can use the p-beta function. P-beta gives us the cumulative distribution function for the beta distribution. That's a probability it's less than or equal to that value. So because we're asking probably it's greater than, we'll take 1 minus the p-beta function. We can see the probability it's greater than 0.25 is 0.9988, almost 1. The probability it's greater than 1/2 is 0.887. The probability it's greater than 0.8 is 0.16. Okay, those are prior probabilities. Now suppose we collect some data and the student gets 33 of the 40 questions right. What's our posterior distribution? The posterior distribution will be beta with parameters 8 plus 33 and 4 plus 40 minus 33, or a beta 4111. The posterior mean is alpha over alpha plus beta. We can also compare that to the maximum likelihood estimate. Posterior mean is 0.788, and the maximum likelihood estimate is 0.825. So the posterior mean is somewhere in between the maximum likelihood estimate and the prior mean of 2/3. We can plot this. Let's add to the plot of the prior, we'll add in the posterior distribution, posterior density. As we try to do that, we see that the posterior density is on a different scale and it goes off the top of the chart. So if we plot that one first, R will make the y-axis appropriately sized, and we can put them both on the same plot. So we'll do that in the other order. We'll plot the posterior first, and then we'll add lines with the prior. In this case, I'm going to change the line type to make it a dashed line. LTY2 gives us a dashed line for the prior. So here the dashed line shows the prior, and the solid line shows the posterior. As we get more information, the distribution gets more concentrated. We could also add the likelihood to this. LTY3 will be a dotted line. We'll add a dotted line for the likelihood. Turns out the likelihood is on a different scale. We're going to need to rescale it because it doesn't have the same type of normalizing constant to make it a density. So it doesn't have to be on the same scale. So we're going to rescale it just so we can plot it on the same plot. In this particular case, I've tried this in advance, and the number 44 works as a good scaling factor. So I'm just going to multiply it by 44 in order to have a pretty plot here. So now the dotted line is the likelihood, the solid line is the posterior, and the dashed line is the prior. You can see that posterior is in between the prior and the likelihood. It's closer to the likelihood because in this case there's more information in the likelihood. Recall that we have 40 samples in the likelihood, and we have a prior with an effective sample size of 8 plus 4 is 12. And so it makes sense that the posterior will be closer to the likelihood than to the prior. How about posterior probabilities? Posterior probability that theta will be greater than 1/4, 1/2, or 0.8. Posterior probability that theta 1 is greater than 1/4 is 1 to double precision. And the probability it's greater than 1/2 is almost 1. Probability it's greater than 0.8 is now up to 0.4444. Given that our data had a value bigger than 0.8, we have a fair amount of confidence that theta 1 is a larger value now. what would be an equal-tailed 95% credible interval? We can use the Q beta function, get the quantiles from the beta distribution, and see that there's a 95% posterior probability that theta 1 is in between 0.669 and 0.887. And that's consistent with the plot here. Most of the mass is between 0.669 and 0.887. All right, now thinking about a second student. Second student gets 24 out of 40 questions right. Their theta 2 now will have a posterior that has a beta distribution with parameters 32 and 20. Get the posterior mean and the maximum likelihood. Again, our prior mean was 2/3. The maximum likelihood estimate is 0.6, and the posterior mean is somewhere in between at 0.615. We see a similar story when we plot these. Here the prior is this dashed line, centered at 2/3. The likelihood is the dotted line at 0.6. And then the posterior is the solid line in between the two, closer to the likelihood. You can see the posterior mass is all sort of between 0.45 and 0.8. Indeed, if we ask what's the posterior probabilities of it being greater than a quarter, a half, or 0.8, we see that posterior probability close to 1 of being greater than a quarter, probability of 0.95 of being greater than a half, but probability very small, 0.00125 of being greater than 0.8. Again, consistent with the plot. A 95% equal-tailed credible interval for theta 2. That goes from 0.48 to 0.74. So this is smaller values than for the first student, which makes sense because the second student didn't get as many questions right. Now this interval here does in fact overlap with the 95% credible interval for the first student. So there is some overlap, but they're centered very differently. So our final question was, what's the probability that theta 1 is greater than theta 2? This would be difficult to do in closed form, so we're going to do it by simulation. We're going to draw 1,000 samples from each posterior distribution and see how often we observe theta 1 greater than theta 2. So I'll use the R beta function to generate random samples from the first beta distribution and from the second beta distribution, and then we'll look at whether theta 1 is greater than theta 2. R will evaluate this statement as an indicator function, so it will be 1 when it's true and 0 when it's false. So if we take the average of those indicator functions, that will give us an empirical probability that theta 1 is greater than theta 2. So we can see here our empirical probability came out to be 0.967. So the probability is close to 1, but not completely certain that theta 1 is greater than theta 2. In some of the exercises later in this course, you'll be asked to work with other distributions, including gamma distributions and normal distributions. And you can see that there are equivalent functions in R for the gamma distribution and the normal distribution. This segment will look at a binomial beta conjugate analysis using Excel and looking at using Excel for questions about distributions. Up at the top of this file, I've posed a scenario and some questions. Suppose we're giving two students a multiple choice exam with 40 questions, where each question has 4 choices. We don't know how much students have studied for this exam, but we think that they will do better than just guessing randomly. Based on the scenario, we can ask a number of questions. What are the parameters of interest? What is our likelihood? What prior should we use? What is the prior probability that theta parameter would be greater than 1/4, 1/2, or 0.8? Suppose the first student gets 33 of 40 questions right. If they have parameter theta 1, what's the posterior distribution for this parameter? What's the posterior probability that it's greater than 1/4, 1/2, or 0.8? And what's the 95% credible interval for it? Suppose the second student gets only 24 questions right. What's the posterior distribution for their parameter? What's the posterior probability it's greater than 0.25, 0.5, or 0.8? And what's the 95% posterior credible interval for it? And finally, what's the posterior probability that theta 1 is greater than theta 2? That is, the first student has a better chance of getting a question right than the second student. First two questions are more theoretical questions. Our parameters of interest are theta 1 being the true probability the first student will answer a question correctly, and theta 2 being the true probability the second student will answer a question correctly. We're going to use a binomial likelihood with parameters n equals 40 and the probability given by the appropriate theta. Here we're assuming that each question is independent and that the probability a student gets each question right is the same for all questions for that student. Now, how do we decide what prior we should use? For a binomial likelihood, the conjugate prior is a beta prior. Let's explore some possible beta priors. I'm going to set up some columns here in the spreadsheet so then we can look at plots of possible beta priors. So in column B, I'm going to have possible values for theta. We'll look at the prior distribution, f of theta. We'll be looking at the likelihood for theta 1, the posterior for theta 1, the likelihood for theta 2, and the posterior for theta 2. For theta, we're going to have values going from 0.01 up to 0.99. We can use the fill function, edit fill series, to go down the column in increments of 0.01, going up to a value of 0.99. I'm going to set this up so that we've got some flexibility in the formula, and the two parameters for the beta distribution are often called alpha and beta. And let's start with the standard uniform distribution, the default prior, so that's values 1 and 1 in our prior beta distribution. Prior density we can stick into column C. There isn't a built-in function in Excel for a beta density, so we'll write this out by hand using the factorial function to get the gamma functions. We'll paste this in to the first cell, and then we'll copy it to the remaining cells. We can now plot this using a line plot. This is a uniform distribution. All probabilities between 0 and 1 are equally likely. It's a standard default distribution for a prior, but it doesn't encode our information, in this case, that we think they will do better than just guessing randomly. So we need a prior that will put its mass above 0.25. For example, we might think that our prior probability should be 2/3. So let's consider some possibilities for priors with prior mean 2/3. One example would be an alpha of 4 and a beta of 2. So now, because I've set it up as a formula, Excel automatically updates it and updates the plot. You can see here the mass has moved to higher probabilities. But at 0.25, there's still a fair amount of probability that's below 0.25. So the larger we make these parameter values, the more concentrated the distribution gets. Let's try something a little more concentrated, for example, 8 and 4. This is now looking good, because at 0.25 there's very little probability that this distribution is below 0.25, and it's fairly nicely spread between 0.25 and 1. So for the rest of this piece, we'll use a prior distribution that's a beta with parameters 8 and 4. Let's find the probabilities that the prior distribution will be above 0.25, 0.5, or 0.8. We can use the beta dist function. This is the cumulative distribution function for a beta distribution. Recall that cumulative distribution is the probability that the distribution is less than or equal to that value. So if we want a greater than, we'll take 1 minus. So the prior probability that a theta will be greater than 1/4 is 0.9988, almost 1. Probability that it's greater than a half is 0.887, and the probability that it's greater than 0.8 is 0.16. Now suppose the first student takes the exam and gets 33 of 40 questions right. The posterior distribution will be a beta distribution with parameters 8 plus 33 and 4 plus 40 minus 33, or 41 and 11. We can think about what are the posterior mean and maximum likelihood estimates. Posterior mean for theta 1 is 0.788. The maximum likelihood estimate is 0.825. Recall the prior mean is 2/3, and so you can see that the posterior mean is in between the prior mean and the data estimate, or maximum likelihood estimate. Let's go ahead and plot the likelihood and the posterior. The likelihood, we can get the binomial distribution, and in Excel, we can get the density by setting the cumulative equals false. The posterior density is another beta distribution, and that one we'll need to calculate by hand. I'll now take these two values and copy them down into the rest of the chart. So now I can plot the likelihood and plot the posterior. I'm putting them on different charts because they're on different scales, and so they don't show up well all in the same chart. But we can line them up nicely here and see that in fact the posterior is close to the likelihood and in between the likelihood and the prior. The posterior is closer in shape and location to the likelihood because the likelihood has more information in it. Recall here we have 40 data points in the likelihood, and the prior has an effective sample size of 8 plus 4, or 12. So there's more information in the likelihood than there is in the prior, and thus the posterior looks more like the likelihood than it looks like the prior, but is somewhere in between. The posterior probabilities that theta 1 is greater than 1/4, a half, or 0.8 those are essentially 1, 0.99999, and 0.4444. You can see that the mass is accumulated up here between 0.6 and 0.9 or so. And so we're almost certain that theta 1 is greater than a half, and there's a reasonable chance it's greater than 0.8, which is a big change from the prior. We can look at an equal-tailed 95% credible interval. Using the beta inverse function, and we can see that there's a 95% posterior probability that the true value of theta 1 is in between 0.669 and 0.887. And that makes sense relative to this plot. Now let's consider a second student. Second student got only 24 of 40 questions right, and so their posterior distribution will be a beta with parameters 32 and 20. We can look at the posterior mean and the maximum likelihood estimate for theta 2. Recall the prior mean is 2/3. The posterior mean is 0.615. The maximum likelihood estimate is 0.6. So again, here they're all closer, but the posterior mean is in between the likelihood or data estimate and the prior estimate. We can put the likelihood for theta 2 into column F here, and put the posterior for theta 2 in column G. Now take these, and we'll paste it down in the spreadsheet, and we'll make plots of them as well. The likelihood for theta 2 and the posterior for theta 2. So in this case, the posterior is a little bit lower than it was for theta 1, which makes sense because the second student didn't get as many questions right. Again, it's much closer to the likelihood than it is to the prior, but the posterior is in between. And you can see that it's going roughly from about 0.45 to 0.8. So we can again ask questions, what are the posterior probabilities that theta 2 is greater than 1/4, 1/2, or 0.8? As well as what's a 95% credible interval for theta 2. We can see posterior probability it's greater than 1/4 is essentially 1. There's a 95% probability that it's greater than 1/2, but the probability that theta 2 is greater than 0.8 is very small, 0.00125. That makes sense from the picture. Theta 2 is not likely to be as large as theta 1. 95% credible interval goes from 0.48 to 0.74. It is worth noting that this credible interval does overlap with the credible interval for theta 1. So what is the posterior probability that theta 1 is greater than theta 2? Well, we can do this by drawing random samples from each of them and see how often we observe theta 1 greater than theta 2. So let's put theta 1 in column H and theta 2 in column I. We'll draw some random samples here. Oops. I'm going to draw samples using the inverse CDF method for drawing random values. So I'm going to draw a random uniform, put it into the beta inverse function, and that will give me a draw from the beta distribution. For theta 2, same idea except with different beta parameters. And finally, I'm going to ask, is theta 1 larger than theta 2? So I'm going to set up an indicator function for theta 1 larger than theta 2 and put that into column J. Now we can take this and copy this formula down and fill up 500 rows of this. And we'll use that to estimate by simulation. So this is a Monte Carlo experiment, and we'll just estimate using the empirical probability that theta 1 is greater than theta 2. So we'll get 500 samples, and then for the indicator functions, we'll add up all 500 of them, divide by 500, and that will give us an empirical estimate of the probability that theta 1 is bigger than theta 2. So here we have 500 theta 1 values, 500 theta 2 values, and then our indicator functions. And you can see in almost all cases, theta 1 is greater than theta 2, but there are some cases where theta 1 is less than theta 2. So this number is going to be close, this probability will be close to 1, but it won't be exactly 1. So we'll scroll down, stick in a sum, divide that by 500, and see we get
an empirical estimate of 0.98. And so we can say that we think the posterior probability theta 1 is greater than theta 2 is approximately 0.98. In some of the exercises later in this course, you'll be asked to work with other distributions besides the binomial and the beta. And so in Excel, there are functions for the gamma distributions and for normal distributions as well.
Let's consider Poisson data. For example, think about chocolate chip cookies. In mass-produced chocolate chip cookies, they make a large amount of dough, they mix in a large number of chips, mix it up really well, and then chunk out individual cookies. In this process, the number of chips per cookie approximately follows a Poisson distribution. If we were to assume that chips have nose volume, then this would be exactly a Poisson process and follow exactly a Poisson distribution. But in practice, chips are not that big, and so they follow approximately a Poisson distribution for number of chips per cookie. So if we model the number of chips per cookie, y sub I, as Poisson with mean lambda, we can have a likelihood for a bunch of observations y, given lambda, to be lambda to the sum of the y sub i's times e to the minus n lambda over the product of y sub I factorial. For this, we need lambda to be positive valued. Okay, now our parameter has to be positive valued. What type of prior should we put on lambda? It would be convenient if we could use a conjugate prior. So we can ask, what distribution looks like lambda to the something e to the minus something lambda? That distribution is the gamma distribution. So a gamma prior for lambda is going to look like lambda being a gamma prior with parameters alpha and beta. F of lambda is beta to the alpha over gamma of alpha times lambda to the alpha minus 1 e to the minus beta lambda for lambda greater than 0. Thus the posterior, f of lambda given y, will be proportional to the likelihood, f of y given lambda, times the prior, f of lambda. And this is proportional to lambda to the sum of the y sub i's, e to the minus n lambda, times lambda to the alpha minus 1, e to the minus beta lambda. Under the proportionality, we only need to focus on the terms that contain lambda, so we can drop these normalizing constants. This then simplifies to lambda to the alpha plus sum of y sub i's minus 1, e to the minus beta plus n lambda. Thus we can see the posterior is a gamma distribution with parameters alpha plus sum of the y sub i's and beta plus n. Recall that the mean of the gamma of a gamma random variable is its first parameter over its second parameter under this parameterization. Do note that there are a lot of different parameterizations of gamma random variables out there, and they may have different parameterizations of the mean as a result. So in this case, we can see the posterior mean is going to be alpha plus sum of the y sub i's over beta plus n. We can then rewrite this as beta over beta plus n times alpha over beta plus n over beta plus n times sum of the y sub i's over n. So we can see that in this case as well, our posterior mean is a weighted average of the prior mean and the data mean. The weights add up to 1. With the n here, this is clearly the sample size for the data, and so the effective sample size for the prior in this case is beta. We can now ask, how would we choose our parameters, our hyperparameters alpha and beta. If we're trying to specify a prior for this, and we're thinking about something concrete like cookies, how would we choose values for alpha and beta in order to be able to do this problem and get a posterior after we've observed data? How would we choose a particular prior, in particular alpha and beta, we need to specify values for? In the case of something concrete like chocolate chip cookies, we may have some ideas about what is in our prior and how to specify information for our prior. What type of strategies would we use to put that information in, then collect data and update it to get a posterior? Let me present two strategies. Under the first strategy, we want to include information into our prior based on our personal knowledge. We can start by thinking about what does the prior mean. The prior mean in this case is alpha over beta. And so we can think, what do we think our prior mean is for the number of chips per cookie? What do we think the number of chips per cookie on average is? That would be our prior mean. The strategy now involves we have to specify a second thing because there are two parameters. So if we specify two things, we can solve for alpha and beta. One possible second thing we could specify is our prior standard deviation or our prior variance. This is how sure are we about our information in our prior mean? If we think the prior mean is that there are 12 chips per cookie, do we think there's a standard deviation of 3, standard deviation of 4, of 6? How sure are we? We can specify a prior standard deviation, and that would be square root of alpha over beta. Given these two quantities, we can solve for alpha and beta, and that will give us our gamma prior. Another way of specifying our confidence or our uncertainty in our prior is to think about the effective sample size. As we see here, the effective sample size is beta. And so we can specify how many units of information we think we have in our prior, how sure we are in that sense, versus how confident we'll be when we have n more data points. And so we can specify a value for beta, and we can specify a prior mean and solve for alpha. This would be a way, two different ways, to specify alpha and beta, and to get a prior to move forward. Another approach is that we can represent ignorance with a vague prior. In Bayesian statistics, a vague prior refers to one that's relatively flat across much of the space. In this case, we can think about some small epsilon. So epsilon is some small number that is strictly positive, and then we can have a gamma prior with parameters epsilon and epsilon. As long as these are both strictly positive, this is a proper prior, it's a proper distribution. In this case, then, the mean will be epsilon over epsilon, which is 1, but its variance will be huge, essentially 1 over epsilon. If epsilon's small, there'll be a really big variance, and so this will be a very diffuse prior across the whole space. If we think about what the posterior mean looks like under this prior, the posterior mean would be epsilon plus the sum of the y sub i's over epsilon plus n. If epsilon is really small, then this is approximately the sum of the y sub i's over n, just the data mean. And thus, the posterior will be largely driven by the data, and the prior will have very little influence. Let's consider the case of exponential data. For example, suppose you're waiting for a bus that you think comes on average once every 10 minutes, but you're not sure exactly how often it comes. We'll say y follows an exponential distribution with rate lambda. Your waiting time has a prior expectation of 1 over lambda. It turns out the gamma distribution is conjugate for an exponential likelihood. Gamma is actually our conjugate for a number of different things. We need to specify a prior, so a particular gamma, in this case. If we think that the buses come on average every 10 minutes, that's a rate of 1 over 10. So our prior mean should be 1/10. Thus, we'll want to specify a gamma distribution whose first parameter divided by second parameter is 1/10. We can think then about our variability, perhaps we want to specify a prior, which is a gamma 100, 1000. This will indeed have prior mean of 1/10, and it'll have a prior standard deviation of 1/100. Thus, if we think as a rough approximate of a mean plus or minus 2 standard deviations as a rough interval for our prior, we would say we're looking at 0.1 plus or minus 0.02 as a possible range for this rate parameter. So here's a particular prior we could specify. Suppose that we wait for 12 minutes and a bus arrives. Now you want to update your posterior for lambda about how often this bus will arrive. Posterior for lambda given y is proportional to the likelihood times the prior. In this case, that's lambda e to the minus lambda y, lambda to the alpha minus 1, e to the minus beta lambda. Doing a little bit of simplification, we get lambda to the alpha plus 1 minus 1, e to the beta plus y lambda, negative. I'm writing this as alpha plus 1 minus 1 so that it is in the form of a gamma distribution. We can now say that lambda given y, the posterior, follows a gamma distribution with parameters alpha plus 1 and beta plus y. Plugging in our particular prior thus gives us a posterior for lambda, which is a gamma with parameters 101 and 1012. Thus, our posterior mean is going to be 101 over 1012. This is equal to 0.0998, or approximately 1 over 10.02. This one observation doesn't contain a lot of data under this likelihood. Our prior has a fair amount of information in it, and so our posterior doesn't shift a whole lot. When the bus comes and it takes 12 minutes instead of 10, it barely shifts our posterior mean up. It shifts it up a little bit, so we now think our expected waiting time is slightly more than 10 minutes, but not much more. One data point doesn't have a big impact here. The last distribution I'll talk about is the normal distribution, also known as the Gaussian distribution. The normal distribution arises in a wide variety of contexts, including heights of people, manufacturing industrial processes, and as a result of the central limit theorem. For now, let's suppose the standard deviation or variance is known and we're only interested in learning about the mean. This is a situation that often arises in monitoring of industrial production processes. So we'll say the x sub i's are IID normal with unknown mean mu and known variance sigma naught squared. How would we choose a prior for mu? We'd like to use a conjugate prior. It would be convenient. It turns out the normal is conjugate for itself, for its mean parameter. So we'll specify a prior for mu, which is normally distributed with some mean m naught and some variance s naught squared. I'm putting on naughts to specify particular values in this case, that these are not parameters. The posterior then, mu, given data x, that will be proportional to the likelihood times the prior. I'm not going to go through all the calculations here. I'll leave that to the supplementary material because it's fairly extensive and involves completing the square. At this point, I will just jump to the final result, which is that the posterior for mu given x follows a normal distribution, and its mean is nx bar over sigma naught squared plus m naught over s naught squared all over n over sigma naught squared plus 1 over s naught squared. And it has variance 1 over n over sigma naught squared plus 1 over s naught squared. This is a somewhat complicated expression, but let's take a little closer look at the posterior mean. This posterior mean we can rewrite as n over sigma naught squared over n over sigma naught squared plus 1 over s naught squared times x bar plus 1 over s naught squared over n over sigma naught squared plus 1 over s naught squared times m. A little bit of simplification will give us n over n plus sigma naught squared over s naught squared times x bar plus sigma naught squared over s naught squared over n plus sigma naught squared over s naught squared times m. Thus we see that the posterior mean is a weighted average of the prior mean and the data mean, and indeed that the effective sample size for this prior is the ratio of the variance for the data to the variance in the prior. This makes sense because the larger the variance of the prior, the less information that's in it. The smaller the variation of the prior, the more information that's in it. We can also consider the case that both mu and sigma squared are unknown. If both mu and sigma squared are unknown, we can specify a conjugate prior in a hierarchical fashion. The data, x sub I, given mu and sigma squared, we represent as independent identically distributed normals with mean mu and variance sigma squared. We then specify a prior for mu conditional on a value for sigma squared to be normal with mean m and variance sigma squared over w. It depends on sigma squared. In this case here, w is going to be the ratio of sigma squared and some variance for the normal distribution. This is the effective sample size of the prior. Finally, the last step is to specify a prior for sigma squared. The conjugate prior here is an inverse gamma distribution, and we give it parameters alpha and beta. Lots of calculations later, we can get a posterior. Sigma squared, given x, follows an inverse gamma distribution with parameters alpha plus n over 2 and beta plus 1/2 times the sum of x sub I minus x bar squared plus n times w over 2 times n plus w times x bar minus m squared. The posterior distribution for mu, given sigma squared, follows a normal distribution with mean n x bar plus wm over n plus w and variance sigma squared over n plus w. So it explicitly depends on sigma squared. Note that this posterior mean can be written as the weighted average of the prior mean and the data mean. Again, we see that W is the effective sample size in this prior. In some cases, we really only care about mu at the end of the day. We want inference on mu, and we may want it such that it doesn't depend on sigma squared. We can marginalize out sigma squared, integrating it out, and at the end of the day, we get a posterior for mu, marginally, that follows a t-distribution. Similarly, the posterior predictive distribution also is a t-distribution. Finally, I note that we can extend this in various directions. This is going to be extended to the multivariate normal case that requires vector and matrix notation. This can also be extended in a hierarchical fashion if we want to specify priors for any of m, w, alpha, and beta. So far, we've seen examples of choosing priors that contain a significant amount of information. We've also seen some examples of choosing priors where we're attempting to not put too much information in, to keep them vague. Another approach is referred to as objective Bayesian statistics, or inference, where we explicitly try to minimize the amount of information that goes into the prior. This is an attempt to have the data have maximal influence on the posterior. We sometimes refer to these as non-informative priors. For example, let's go back to coin flipping, where our data come from a Bernoulli distribution with unknown parameter theta. How do we minimize our prior information in theta? One obvious intuitive approach is to say that all values of theta are equally likely. So we could have a prior for theta, which follows a uniform distribution on the interval 0, 1. Saying all values of theta are equally likely seems like it would have no information in it. Recall, however, that a uniform 0, 1 is the same as a beta 1, 1. The effective sample size of a beta prior is the sum of its two parameters. So in this case, it has an effective sample size of 2. This is equivalent to data with one head and one tail already in it. So this is not a completely non-informative prior. We could think about a prior that has less information. For example, a beta 1/2, 1/2. This would have only half as much information, has an effective sample size of just 1. We can take this even further. Think about something like a beta 0.001, 0.001. This would have much less information, have a sample size fairly close to 0. In this case, the data would determine the posterior, and there would be very little influence from the prior. Can we go even further? In fact, we can. We can think of the limiting case. Something that we could think of as a beta 0, 0. What would that look like? Well, in this case, we could say its density is proportional to theta to the minus 1, 1 minus theta to the minus 1. This is not a proper density. If you integrate this over 0 to 1, you'll get an infinite integral. So it's not a true density in the sense of integrating to 1. There's no way to normalize it. It has an infinite integral. This is what we refer to as an improper prior. It's improper in the sense that it doesn't have a proper density, but it's not necessarily improper in the sense that we can't use it. If we collect data, we use this prior, and as long as we observe at least one head and at least one tail, or one success and one failure, then we can get a posterior, f of theta given y, which is proportional to theta to the y minus 1, 1 minus theta, to the n minus y minus 1. This you'll recognize as a beta distribution with parameters y and n minus y. Its posterior mean will be y over n. This you should recognize as theta hat the maximum likelihood estimate, the MLE. So by using this improper prior, we get a posterior which gives us point estimates exactly the same as the frequentist approach. But in this case, we can also think of having a full posterior. And so if we want to make interval statements, probability statements, we can actually find an interval and say that there's 95% probability that theta is in this interval, which is not something you can do under the frequentist approach, even though we may get the exact same interval. Key concepts here that I want to state in terms of using improper priors. The first is that improper priors are okay as long as the posterior itself is proper. There may be some mathematical things that need to be checked, and you may need to have certain restrictions on the data. In this case, we need to make sure that we observe at least one head and one tail to get a proper posterior. But as long as the posterior is proper, we can go forward and do Bayesian inference even with an improper prior. The second point is that for many problems, there does exist a prior, typically an improper prior, that will lead to the same point estimates as you would get under the frequentist paradigm. So we can get very similar results that are fully dependent on the data, under the Bayesian approach. But in this case, we can also continue to have a posterior and make posterior interval estimates and talk about posterior probabilities of the parameter. Another example is thinking about the normal case. So think about y sub I being IID, normal with mean mu and variance sigma squared. Let's start off by assuming that sigma squared is known, and we'll just focus on the mean mu. We could think about a vague prior. Say mu is normally distributed with mean 0 and variance 1,000,000 squared. That would just spread things out across the line, the real line. You can take a wide variety of possible values. That would be fairly non-informative across a lot of possibilities. We can then think about taking the limit. What happens if we let the variance go to infinity? In that case, we're basically spreading out this distribution across the entire real line. And so we could say we have a density which is proportional to 1. It's just constant across the whole real line. Clearly, this is an improper prior, because if you integrate the real line, you get an infinite answer. However, if we go ahead and plug this into finding a posterior, f of mu given y is proportional to f of y given mu, f of y. The likelihood here is proportional to e to the minus 1 over 2 sigma squared, sum of y sub I minus mu squared, and our prior is just 1. So this is just the likelihood that we recover here, which we can simplify to be e to the minus 1 over 2 sigma squared over n, mu minus y bar quantity squared. Thus we see that the posterior for mu, given y, follows a normal distribution with mean y bar and variance sigma squared over n. This should look just like the maximum likelihood estimate. In the case that sigma squared is unknown, the standard non-informative prior is f of sigma squared is proportional to 1 over sigma squared. This is equivalent to an inverse gamma with both parameters equal to 0. This is an improper prior, and it's uniform on the log scale of sigma squared. In this case, we'll end up with a posterior for sigma squared, which is an inverse gamma with parameters n minus 1 over 2 and 1/2 the sum of y sub I minus y bar squared. This should also look reminiscent of quantities we get as a frequentist, for example, the sample standard deviation. Choosing a uniform prior depends upon the particular parameterization. For example, thinking about the normal distribution, suppose I use a prior which is uniform on the log scale for sigma squared. So f of sigma squared is proportional to 1 over sigma squared. Suppose somebody else decides they just want to put a uniform prior on sigma squared itself. F of sigma squared is proportional to 1. These are both uniform on certain scales or certain parameterizations, but they are different priors. And so when we compute the posteriors, we will get different posteriors. The key thing is that uniform priors are not invariant with respect to transformation. Depending upon how you parameterize the problem, you can get different answers by using a uniform prior. One attempt around this is the Jeffreys prior. Jeffreys prior is defined as the prior proportional to the square root of the Fisher information. In most cases, this will be an improper prior. For the example of normal data, the Jeffreys prior is exactly the prior we've seen before. It's uniform for mu, and then for sigma squared, it's uniform on the log scale. This prior will then be invariant transformation. We'll be putting the same information into the prior, even if we use a different parameterization for the normal. in the example of a Bernoulli or binomial, the Jeffreys prior turns out to be theta to the minus 1/2, 1 minus theta to the minus 1/2, which is a beta distribution with parameters 1/2 and 1/2. This is a rare example where the Jeffreys prior turns out to be a proper prior. You'll note that this prior actually does have some information in it. It's equivalent to an effective sample size of 1 data point. However, this information will then be the same not depending upon the parameterization we use. In this case, we have theta as a probability, but another alternative used in probabilities calculations, sometimes we model things on a logistic scale. And in that case, we can transform everything, and using the Jeffreys prior, we'll maintain the exact same information. Other possible approaches to objective Bayesian inference include priors such as reference priors and maximum entropy priors. Finally, I'd like to mention a related concept, which is empirical Bayesian analysis. The idea in empirical Bayes is that you use the data to help inform your prior, such as using the mean of the data to set the mean of the prior distribution. This approach often leads to reasonable point estimates in your posterior. However, it's sort of cheating because you're using the data twice, and as a result, it may lead to improper uncertainty estimates.
This demonstration is on fitting linear regressions in R. We'll look at 2 examples, one simple linear regression with just one explanatory variable, and one case of multiple regression. We'll do this using data sets that are freely available online. The first one is looking at space shuttle damage. So this is thinking back to the time that the Challenger shuttle was launched and we had the Challenger disaster. There were 23 previous launches before Challenger disaster. What we'll look at is the temperature at the time of launch in degrees Fahrenheit and an index of O-ring damage. This is labeled I in this data set. Let's go take a look at a data set. So this is hosted at the University of Alabama, Huntsville. Here's the data set. 23 previous launches, the temperature in degrees Fahrenheit, and the index of O-ring damage. You can see most flights had no damage, but some had 2, 4, or 11 units of damage. In R, we can read in a data set directly from a URL online using the read.table command. So I'll do that here, store it in an object called O-ring, and this one does have labels, and so we'll specify header equals true. Just a note here that after I tell it to paste, I have to hit the return key to get R to execute that. All right, we've read in this data set. If I want to be able to use the labels, I use the attach command to be able to access the labels. R gives me a warning because one of the labels is T. Here T is for temperature, but built into R, capital T also stands for true. So while we're using these labels, we won't be able to use capital T as a shortcut for true, but we're not going to be using that today anyway. So just to verify, we can look at, here's our data set. We read in all 23 rows. We've got temperature and damage. We can make a quick plot of this, visualize the data. Here we can see the 23 previous launches. All of the launches that had no damage were on warmer days. All of the launches on colder days had some type of damage. So there does look like there's some effect of temperature on the state of the O-rings. Let's fit a linear regression to predict damage based on temperature. I'm going to use the LM command in R. LM stands for linear model. It's a linear model of damage modeled on temperature. So here temperature is the independent or explanatory variable, and damage is the dependent variable. Now I've stored it in this object. If we want to see the results, we can use the summary command. And here's a summary of the results. There's a fair amount of information. What's most important here is here's the coefficient for the intercept, here's the coefficient for the slope. These are the standard deviations for the marginal distributions for the intercept and the slope. If we were a frequentist and we want to do a frequentist significance test, these are the t-values and the p-values associated with the t-tests. The standard error for the regression is 2.1. If we're interested, the r-square is 0.4. We can add a fitted line to the scatter plot. In R, the lines command will connect the dots and create a line. We can plot the temperatures and the fitted temperatures, and we get them out of the linear model object by using the fitted function on the linear model object. Here we can see the fitted line, and that as temperature increases, the damage goes down, or as temperature decreases, the damage goes up. This is just an approximation. It's not going to go through all the points because there's a lot of noise in the data, as is typical with real-world data. Our slope estimate is minus 0.24. So roughly, for every 4 degrees the temperature gets colder, we see a 1 unit increase in damage. We could look at a 95 posterior probability interval for the slope. Here I'm taking the fitted value for the slope, and the marginal distribution, posterior distribution, is a t-distribution with 21 degrees of freedom, and it has the scaling factor of the standard error of the coefficient, 0.06349. So plugging that in, I get a 95% posterior probability interval that goes from minus 0.375 to minus 0.111. This interval does not include 0, so we can be pretty sure that there is a negative relationship between temperature and damage. Note that these intervals are the same as the frequentist confidence intervals when we're using the standard reference prior for a Bayesian analysis. The day that Challenger was launched, the temperature was actually 31 degrees Fahrenheit. How much O-ring damage would we predict? So we're looking at the y-hat value for an x of 31, or in this case a t of 31. We can compute this by hand by pulling off appropriate elements, the intercept and the slope. So the intercept plus the slope, minus 0.24, times the value 31, and we get a predicted value of 10.82. We can see that's a fairly large amount of damage that we predicted. That makes sense because 31 is actually off the edge of this chart. The lowest value we observed was 53. 31 would be farther to the left, and we'd expect to see a fair amount of damage. We can also use the coefficient command in R to get coefficients out of a linear regression model object. In this case, it will give us a vector of all the coefficients. Here, the 18.36 and the minus 0.24, the intercept, and the slope. So we could use this to compute a fitted value, taking the intercept as the first value of the vector of coefficients, and the slope as the second value of the vector of coefficients. And you see here we get essentially the same answer. There's maybe a little bit of rounding error when I just pull the numbers off by hand. We can also think about a prediction interval, a posterior prediction interval. So if we're going to launch at 31 degrees, what's a 95% predictive interval for what we might see in damage? This is going to be a larger interval than just a fitted interval. we can use the predict command in R. It will give us also this predicted value, but it will give us a predicted interval. Predict command starts by taking the linear model object. We then have to tell it where we want to predict. We give it a data frame of the values of the independent variables, in this case, a temperature of 31. And then we tell it we want a prediction interval. So here, again, we verified that the fitted value is 10.82, but a 95% predictive interval goes from about 4.05 to 17.59. We could also verify this by hand using a formula that's in the materials posted online for this lesson, and see that we get a lower bound of, again, about 4.05. It's a little bit of rounding happening here. And the upper bound would be comparable, changing this minus to a plus. These predictive intervals are the same intervals that we get if we were a frequentist. So using the Bayesian reference prior allows us to use all the standard regression tools. One thing we can do different as a Bayesian is we can ask, what's the posterior probability that the damage is greater than 0 if we launch at 31 degrees? So here we're going to use the same predictive distribution, but use it to make a probability statement. So we can ask, what's the probability that damage will be greater than 0? So it's a t distribution. I'm going to ask, what's the probability of t with this center and this scale is bigger than 0? The pt command will give us the probability it's less than 0, and so we take 1 minus that to get the probability it's bigger than 0. Probability that the damage will be bigger than 0 is 0.998, very close to 1, so it's extremely likely that there will be damage if we are to launch at 31 degrees Fahrenheit. Now let's take a look at a multiple regression example. This example is one of the classic data sets. Galton, in the 19th century in Britain, was looking at predicting the heights of children from the heights of the parents. All these measurements are in inches. Let's take a quick look at the data set. Here we can see that there's a number of different families. Each family, they looked at all the kids in the family. They looked at the height of the father in inches, the height of the mother in inches, the gender of the child, the height of the child in inches, and how many kids are in that family. So let's read this into R. This one seems to trigger a warning message in R. R sometimes gives warning messages of things happening behind the scenes, but this won't affect any of our analyses. So let's use the headers. The labels for the variables are family, father, mother, gender, height, and kids. Let's take a quick look graphically at the data. Focusing on height as the variable we're trying to predict, we can look at this column here and see that boys in general are a little bit taller than girls. The tallest children tend to have taller parents. The shortest children tend to have shorter parents. It's not clear that there's any relationship between the number of kids in the family and the height. Let's look at regression for all these variables in predicting the height of the children. We can see that there's a clear effect for the height of the father, clear effect for the height of the mother, clear effect for the gender of the child, but that there's not such a clear effect for the number of kids in the family. The standard error is close to the size of the estimate, and so this distribution is very close to 0 and includes 0, and so we may not want to use this variable as it may not be that helpful in actually predicting, and including too many variables will increase your predictive variance. So let's take a look at what happens if we take that variable out. Here we can see that all these variables now have strong effects. There's not much change in fit. If we look at our R-square, it's roughly 0.64 and roughly 0.64. And so this is a better model for us to use. So we'll stick with this regression model where we're predicting height as a function, height of the child as a function of height of the father, height of the mother, and gender of the child. We can see that each extra inch taller a father is correlated with about a 0.4 inch increase in the height of the child. Each extra inch taller a mother is a little more than 0.3 of an inch taller in the child. And then on average, boys are about 5.2 inches taller than girls. We could ask, what's a 95% probability interval for the difference in heights between boys and girls? The marginal distribution for the slope parameter for gender is going to be a t-distribution with 894 degrees of freedom. And so we can use that to get a 95% probability interval for this slope effect of gender and see that that ranges from 4.94 to 5.51. So indeed, boys are going to be a little more than 5 inches taller than girls on average. We can also look at prediction intervals. Again, a reference Bayesian analysis will give us the same intervals as a frequentist. So we could ask, what's the predicted height and predicted 95% probability interval for a child's height when the father is 68 inches tall, the mother is 64 inches tall, and the child is either male or female? We can see that the predicted height for a male child is 68.75 inches, with a probability interval ranging from 64.5 to about 73. If it's a girl, then the predicted height is 63.5, with a prediction interval ranging from 59.3 to 67.76. This demonstration is on using Microsoft Excel 2016 with the Data Analysis Toolkit for doing linear regression. We'll take a look at two examples, one of simple linear regression with just one explanatory variable, and one example with multiple regression. The first example is looking at space shuttle launches and damage to the O-rings. This is the context of the Challenger disaster. There were 23 previous launches before the Challenger disaster. Let's take a look at that data. This is a publicly available data set that's available at the University of Alabama, Huntsville at this web address. Here we can see the 23 previous launches, the temperature in degrees Fahrenheit, and an index of damage to the O-rings. Most launches had no damage, but some of them had 2, 4, or 11 units of damage. We'll copy all of this data and paste it into Excel. Let's take a look at a plot of the data. We can do this, insert, chart, XY scatter plot. Make the chart a little bit bigger so we can see it better. We can see that all of the flights that had no damage were on warmer days. All the flights on colder days had some amount of damage. We can add chart element trend line, linear, put a linear regression line onto this chart. So here's the fitted line, and we can see that as it gets colder, we expect to see more damage. We can quantify that using a linear regression model. So we'll go to Data, Data Analysis, Regression. Our y variable, the response, or dependent variable, will be the index of O-ring damage, and that goes from I2 to B2 to B24. The explanatory variable, the x variable, is the temperature, and that goes from A2 to A24. We'll put the output into the same spreadsheet so that we can use the results. Here Excel has computed linear regression for us. An R-square of 0.64, standard error of 2.1, there's 21 degrees of freedom. The fitted intercept is 18.365, and the fitted slope is minus 0.24. The slope gives the relationship between temperature and predicted damage. It's saying approximately for every 4-degree decrease in temperature, we expect to see a 1-unit increase in damage. That makes sense with this negative slope. Excel also gives us a 95% interval for the slope. Under the Bayesian analysis, this is a posterior interval. Using a reference Bayesian analysis, we get the exact same interval as we would for a frequentist. We can see how this is computed by hand. For example, the lower portion of the interval, minus 0.375. That's going to be the fitted value minus the standard error times the value from a t distribution, a t with probably 0.975, and degrees of freedom as given by the regression. Thus, we can replicate by hand what Excel has given us in the table. Suppose we want to predict how much damage we expect to see if we launch at 31 degrees. That's pretty far below the actual data that we've seen so far, and we're going to expect to see a fair amount of damage. Predicted value, y hat, is going to be the intercept plus the slope times the x value we're predicting at, in this case 31. We get a predicted value of 10.82. So at 31 degrees Fahrenheit, we expect to see, on average, almost 11 units of damage, which is about as high as we've seen in the data set. We can ask, what's a predictive interval for this launch at 31 degrees? So thinking about a posterior predictive interval. These, under a reference Bayesian analysis, will be the same, again, as the frequentist predictive intervals. And so this is thinking about a new observation when we launch at 31 degrees. I'm going to copy and paste in a formula. This formula is in the materials associated with this lecture online. This will give us the lower end of the interval, and then using a plus instead of a minus will give us the upper end of the interval. Thus, we get an interval that runs from about 4.05 to 17.59. This will be a 95% predictive interval for all future launches at 31 degrees. You can see that 0 is not included in this interval, so we're pretty confident that we'll expect to see O-ring damage if we launch at 31 degrees. So far, we've gotten pretty much the same answers
if we're using a Bayesian analysis or frequentist analysis. A question we can ask as a Bayesian that's difficult to answer as a frequentist would be, what's the posterior probability that the damage index is greater than 0 for a launch at 31 degrees Fahrenheit? Here we'll use the marginal predictive distribution, posterior predictive distribution, and that's a t-distribution. T-distribution with center 10.82 and scaling factor 2.1. The t-dist function will give us the probability of it being less, and so if we want the probability it's greater than 0, we'll take 1 minus that value. Plugging this in, Excel gives us a probability of 0.998. Thus, we have extremely high probability of seeing O-ring damage if we launch at 31 degrees Fahrenheit. Now let's move on to a second example. This example is a classic data set on predicting the heights of children from the heights of the parents. This was done by Galton in 19th century Britain. All these height measurements are in inches. Let's take a look at the data set. So he measured heights of children in a number of different families, measured the height of the father in inches, the height of the mother in inches, the gender of the child, male or female, the height of the child in inches, and how many children were in that family. So we'll copy this into a new Excel spreadsheet. In order to fit a regression in Excel, a multiple regression, it wants us to have all of the explanatory variables, all the independent variables, together in one block. Because height is somewhere in the middle, we'll make a new block over here with all the explanatory variables. So kids is a potential explanatory variable, height of father, height of mother, and gender of child. I'm going to start by copying father and mother and put them over here in columns G and H. So now I've got kids, father, and mother together. Gender, Excel is going to want me to have numbers, not labels of male and female. So I'm going to create a new variable called gender m. This will take a value 1 if the child is male and a value 0 if the child is female. So in particular, we can use the if function in Excel. And so I can say if the value in column D is equal to male, then I want the value 1, and otherwise I want the value 0. With this formula now, I'll cut and paste it into all the rest of the column. This is a fairly large data set, and so we'll see it goes down to row 899. So now I've created a contiguous block of my explanatory variables, and I can use this to make a regression. My y range is going to be height. It's going to be going from E2 to E899. My x range is going to be kids, number of kids in the family, the height of the father, the height of the mother, and the gender. And this is going to go from F2 to I899. The output range will need to move over compared to where it was last time. And so here Excel gives us a response. R squared, 0.64, 893 degrees of freedom, and some coefficients here. Variable 1 is the kids, variable 2
is the height of the father, variable 3 is the height of the mother, and variable 4 is the gender. We can see that for parents' heights and for gender, these are highly significant and important variables. The coefficient is much larger than the standard error. On the other hand, for the size of the family, the coefficient is not much larger than the standard error. So this is a slope that's very close to 0. And we might say for a frequentist that it's not statistically significant. In general, we don't want to include extra variables that are not helpful with prediction because they tend to increase the predictive error. So let's fit this again, but without the number of kids in the family. Here I'll change the x input range to start in column G. And we'll overwrite. Now we can see our R-square is almost the same, still about 0.64, but that all of our coefficients are important for the model. All the values are much larger than their standard errors in absolute value. We can see that on average, each extra inch of height of a father results in about 4/10 of an inch of height in the child. Each extra inch of height in the mother results in a little over 3/10 of an inch of height for the child. And that on average, boys are 5.2 inches taller than girls. Excel gives us a 95% posterior interval for this difference in height by gender. It goes from 4.94 to 5.51. This would be a 95% posterior probability interval if we're doing a Bayesian reference analysis, but it is also the same as the frequentist confidence interval. This segment will demonstrate linear regression using Excel plus Stat+, the free extra software. This is for versions of Excel where the data analysis toolkit is not available. We'll look at two examples of linear regression. The first is a simple linear regression where we only have one explanatory variable, and the second is a multiple regression. This first one is looking at space shuttle data, and so this is going back to the Challenger disaster. This is freely available data currently hosted at the University of Alabama, Huntsville. What this data shows is before the Challenger fatal flight, there were 23 other flights. It has the temperature in degrees Fahrenheit and an index of the amount of O-ring damage for that flight. You can see that with most flights, there was no damage, but in some flights there were 2, 4, or 11 units of O-ring damage. You can also see that the damage tends to be bigger for colder temperatures, and that there tends to be less damage at warmer temperatures. We'll highlight all of the data and copy it here into Stat+. Stat+ will allow us to do a regression. We want to predict the damage index, so that's our dependent variable, or our response variable, and predicting it from the temperature, that's our independent variable, or explanatory variable. Stat+ gives us a new sheet with all the linear regression results. We can see we have an R-square of 0.41, a standard error of regression of 2.1, there's 21 degrees of freedom, the estimated intercept is 18.365, and the estimated slope is minus 0.243. This estimated slope says that approximately for every 4 degrees colder at launch, we expect to see 1 additional unit of damage to the O-rings. We can look at what's a 95% posterior probability for the slope. Stat+ gives us this actual interval. The interval goes from minus 0.375 to minus 0.111. We could also compute this by hand. Let's just look at the lower limit of this 95% interval.
we could see this as the fitted value minus the standard error times the value from a t-distribution with probability 0.975 and degrees of freedom, the degrees of freedom from the regression, in this case 21. Here we can see that doing this by hand gets us the same answer as in the table. This is a 95% posterior probability interval using a reference Bayesian analysis, or reference prior. This turns out to be the same interval as we get as a frequentist, creating a 95% confidence interval. But using a reference Bayesian analysis, we can give this a full probability interpretation, saying that we have a 95% posterior probability that the true value of the slope will be in this interval. Suppose we want to predict the actual temperature at launch for Challenger that day was 31 degrees Fahrenheit. That's much colder than the coldest flight previously. We'd like to predict how much damage do we expect to see at 31 degrees Fahrenheit. So this predicted value is going to be the fitted intercept plus the fitted slope times this input value, in this case 31 degrees. We can see then that the predicted amount of damage is 10.82 units. This is relatively large, about as big as anything else we've seen in the data set. We can ask, what's a 95% posterior predictive interval? So we're thinking about the posterior predictive distribution, looking at a new observation. I want to ask, what's an interval such that there's 95% posterior probability that the new observation will fall in that interval? This will be a t-distribution that's centered at our prediction of 10.82. And we'll have a scale based on the standard error of regression and the rest of the formula that's available in the notes online associated with this lesson. This formula uses partly the distance from this new point to the rest of the data. So our new value of 31 relative to the other data. So we're going to go back to the first sheet where we have the rest of this data, and so we can access that. Here's the lower interval, and here's the upper end of the interval. So we can see that a 95% posterior predictive interval runs from about 4.05 to 17.59. Thus we say we have a 95% posterior predictive probability of getting an observation between 4.05 and 17.59 units of O-ring damage. It seems pretty likely that there will be a significant amount of damage to the O-rings if we were to launch at 31 degrees Fahrenheit. Note that again, under a reference Bayesian analysis, this is the same interval as we get as being a frequentist and asking what's a predictive frequentist interval. One thing we can do differently as a Bayesian that's difficult to do as a frequentist is we can ask about posterior probabilities. For example, we can ask what's the posterior probability that the damage index will be greater than 0 for a new observation of a launch at 31 degrees Fahrenheit. So again, we're going to use the posterior predictive distribution, which is a t-distribution. It's a t-distribution with center 10.82 and this somewhat complicated scale factor. So we paste this formula in, and in this case, some versions of Stat Plus might work, and other versions this may throw an error code. Apparently with some versions of Stat Plus, it gets cranky if we have a negative number going into this t-distribution function. T-distribution is symmetric, and it should work for a negative number, but in this case it doesn't seem to be working. So instead of taking 1 minus the cumulative at the negative value, we'll look at the value up to 10.82 in this case because it's a symmetric distribution. So we'll just flip this around. We'll get the same answer in this case.
So here we can see the posterior probability of getting a damage index greater than 0 at 31 degrees Fahrenheit is 0.998. Probability is almost 1 that we'll have damage if we launch at 31 degrees Fahrenheit. All right, let's move on to a second example of regression. This one is a classic data set back to the 19th century where Galton was trying to predict the heights of children from the heights of the parents. Here we have data from a bunch of different families. Some families have more kids than others. This first family had 4 kids. This family had 4. This family had 2. We can see for each child, we have the height of the father in inches, the height of the mother in inches, the gender of the child, and the eventual height of the child in inches, as well as the number of kids in the family. So we want to be predicting the height of the children from the heights of the parents, and potentially also the gender and the number of kids in the family. We're going to need to do a little manipulation to this data set before we can stick into the regression. So I'm going to do that first in Excel. In particular, the issue is that gender is coded as M and F for male and female. But in terms of running a regression, we're going to need numerical values. So I'm going to create a new variable called gender M, and I'm going to make this have the code of 1 if the gender is M, and a code of 0 if the gender is F. So I pasted in this formula using the if command in Excel. And now I can copy and paste this into the rest of the data set. Turns out there are 899 rows in this file, so we'll go down, we'll paste this into the rest. But the key is we need to translate the M's and the F's into 1s and 0s so that then Excel or Stat Plus can do the regression, because they're both expecting numerical values and they can't deal with the categorical variables of M and F. Okay, so now I have 0s and 1s. And I'm going to do my regression again in Stat Plus. So I will open up a new sheet. In Stat Plus, I can paste in this data set. I can now do a regression. I want to predict the height of the children based on the father's height, the mother's height, my numerically coded gender variable, and the number of kids in the family. So here we've run our multiple regression. We get an R-square of 0.64, standard error regression of 2.15, 893 degrees of freedom, and here are our coefficients. An intercept of 16.18, slope coefficients for each of the explanatory variables, the standard errors for each of those slopes. You can see that for most of them, the coefficient is much larger than the standard error. But in the case of the size of the family, the number of kids in the family, the coefficient is not much larger than the standard error. In fact, if we were frequentist, we might do a t-test and say, is this variable significant? In this case, we'd fail to reject it, say this variable is not particularly significant. As a Bayesian, we might just look at the coefficient relative to the standard error and see that its posterior interval includes 0. We generally try not to include variables that are not adding much to the regression because they don't help with prediction and they actually increase the variability of our prediction. So in this case, I'm going to go back and I'm going to fit the regression again without using the number of kids in the family. So predicting the height of the children based on the height of the father, the height of the mother, and the numerically coded gender variable. So now I get basically the same R-square of 0.64, same standard error regression, 2.15. We have one more degree of freedom because we have one fewer explanatory variables. Now, the intercept and all the slope coefficients are all much larger than their standard errors. We can see that the fitted slope for the father's height is 0.4. This says that for every extra inch taller a father is, that is correlated with another 0.4 inches of height in the child. Each extra inch of height in a mother is correlated with a little more than 0.3 of an inch of height in the child. And then on average, boys grow up to be 5.2 inches taller than girls do. The table gives us a 95% posterior probability interval for the difference in heights by gender. We can see that this interval goes from 4.94 to 5.51. So we can say there's a 95% posterior probability that the difference in height by gender is in this interval under a standard reference Bayesian analysis. This is also then going to be the same interval we'd get under a frequentist confidence interval. This is the conclusion of this course. As you've seen, both frequentist and Bayesian approaches offer coherent methods for understanding of uncertainty and for data analysis. I hope that I've convinced you that the Bayesian approach better matches our intuition of uncertainty and provides answers that are more easily interpreted. No approach to statistics is completely objective. The Bayesian approach makes our assumptions more explicit. Both Bayesian and frequentist approaches are valuable for a whole range of data analysis as well as scientific discovery. The Bayesian approach provides better quantification of uncertainty. If you do want to go farther with Bayesian statistics, the next topics to explore would be hierarchical modeling and the fitting of non-conjugate models with Markov chain Monte Carlo, or MCMC. I hope you've enjoyed this course and that you've gained an understanding of the Bayesian approach to statistics, and I hope that you find it useful in what you do.
Hello, I'm Matt Heiner, a doctoral student of Statistics and Applied Mathematics at the University of California, Santa Cruz. After assisting Professor Herbie Lee in bringing you the first course in this series, I'm excited to present to you the second course on Bayesian statistics. Welcome to the class. The next step in your development as a Bayesian statistician is a crucial one. Real-world data involving multiple variables often require more complex models to reach realistic conclusions. As we encounter more widely applicable models, we will need advanced computational techniques to fit them. This course will introduce Markov chain Monte Carlo, often referred to as MCMC methods, which allow sampling from posterior distributions that have no analytical solution. These methods have revolutionized Bayesian statistics because they vastly expand the possibilities of models that are available to us. In this course, we will build on the fundamentals that were introduced in Professor Lee's course. We will assume that you have completed that course using R for your calculations, or that you have a basic familiarity with Bayesian concepts and can do some basic programming in R. If you're out of practice in these, or in calculus-based probability, don't worry. We'll review important skills as they become necessary in our work. The course is organized into 5 modules. In the first module, we will discuss statistical modeling and review how to approach a problem from a Bayesian perspective. We will also introduce the concept of using probabilistic simulation to approximate quantities that are difficult to compute directly. The second module is dedicated to introducing MCMC. We will describe and demonstrate 2 algorithms that have brought Bayesian statistics into the mainstream. We will also introduce Jags, an open source software which implements MCMC for you so that you can focus on modeling rather than coding intricate algorithms. In the third module, we'll begin modeling real data. We'll demonstrate some of the most common statistical models, including linear and logistic regression. In the fourth module, we'll look at regression for count data, and we'll introduce hierarchical modeling as a way to account for correlated data. Throughout these demonstrations, we'll explore different techniques to address challenges that often arise in data analysis. The last module contains only an assignment. This assignment puts you in the driver's seat. It's your opportunity to bring together all the pieces we've built throughout these 2 courses and conduct your own data analysis on a project that you select. This peer-reviewed assignment is also your chance to practice communicating the methods you use to solve a problem. It's also an important opportunity to get feedback on your work and help others to improve their work. Each module has about 90 minutes to 2 hours of video instruction. We recommend that you watch instructional videos at the highest screen resolution. You can set this option by clicking on the gear icon in the lower right portion of the screen. We encourage you to watch the videos multiple times. The programming demonstration videos come with code so that you can follow along. Many lessons come with required background reading or optional supplementary reading, which may make the material more accessible. Each module comes with an honors quiz if you're looking for a challenge or for extra practice. Also, the honors sections of modules 3 and 4 address additional topics you might find interesting. In order to synthesize and solidify what you learn, it's necessary to get plenty of practice. In an ordinary course, we would give you regular homework assignments. In the Coursera framework, we present the homework problems as quizzes. We encourage you to approach the quizzes as homework sets, which may require reviewing the relevant material, attempting to find a solution, returning again to the material, and correcting errors. If it takes a half hour or more to complete a quiz, you're probably approaching it how we intended, and you'll get more out of this course. The problems may require several attempts, but don't be discouraged. We allow multiple quiz attempts. Also, we provide a lot of feedback in the quizzes themselves. Even if you get a problem correct, you may learn something by reading the feedback. Again, welcome to the course. We hope this will be a rewarding experience as you dive into applied Bayesian modeling and broaden your analytical skill set. What are the objectives of statistical models? What can they accomplish, and where do they fit in the broader field of data science? Statistics is concerned with the entire process of planning, collecting, and analyzing data to draw scientifically defensible conclusions. Because these objectives are important to a wide variety of disciplines, you might encounter statistics in areas ranging from business to medicine, biology to sports, social sciences to pharmacology, or agriculture to ecology. This course is about statistical modeling, which falls under the analyzing data objective. So what is a statistical model? In this course, we're going to define a statistical model A statistical model will be a mathematical structure used to imitate and approximate the data generating process. It typically describes relationships among variables while accounting for uncertainty and variability in the data. For example, let's consider an experiment where we wish to reveal a cause and effect relationship. If the relationships between variables are complicated or involve variables that we can't measure, the data we collect may appear to have random behavior. We can account for this apparent randomness or uncertainty or variability using the theory of probability. Then, hopefully a statistical model will help us identify structural, such as cause and effect, relationships hidden in the noisy data. As an example of another source of uncertainty and variability in your data, let's consider a poll conducted on a sample of likely voters. Let's say that 57% of those polled are in favor of one particular candidate. When presented with these results, it might be natural to ask, how confident am I in this 57% number? Does it mean that 57% of all people favor that candidate? Well, that depends on several other questions related to how well the poll was conducted, for example. How were the participants selected? How many people were polled? If we repeated the poll on another randomly selected sample of voters, how might that 57% number change? Using probability theory, we can account for the uncertainty surrounding this estimate. For what kinds of problems might we use a statistical model? Here are 4 common objectives. The first one we're going to talk about is to quantify uncertainty. In the polling example, we could come up with a range of reasonable estimates to put that 57% number in context. Suppose a statistician analyzes the poll data and concludes that with 99% confidence, the true percentage of all citizens who favor the candidate is between 51 and 63%. That's a little more informative. It gives us an idea of how much we can trust this estimate. The second objective we'll talk about is inference. In the polling example, we only know a percentage of people in the sample who support the candidate. A statistical model helps us extend the results and infer what percentage of the total population supports the candidate. We may also have other demographic information about each person in the poll. A statistical model might allow us to see how these other variables relate to a person's likelihood of supporting the candidate. The next objective is measuring the evidence in the data in support or against a hypothesis. In the polling example, suppose an expert hypothesizes that the candidate is more popular with men than with women. Luckily, we have further breakdown of the poll results. Let's suppose that 55% of women favor the candidate and 59% of men favor the candidate. Is this strong enough evidence to support or validate the expert's claim? A statistical model could account for the uncertainty in these estimates to help us answer that question. The fourth and final modeling objective that we're going to talk about is prediction. In the polling example, suppose we have demographic information about a particular voter, but we don't know which candidate she supports. We might employ a statistical model to use what is known about her to make an accurate prediction of her voting selection. It is clear that statistical modeling has much to contribute to data science. Another key player in this arena is machine learning. How does that relate to statistical modeling? Broadly, machine learning uses algorithms some of which are based on or can be formulated as statistical models, to produce state-of-the-art prediction. That is, machine learning specializes in and excels at this fourth objective. Often, excellent predictions come at the cost of building complicated models that are difficult to interpret. For that reason, such algorithms are frequently referred to as black boxes. Of course, who would believe a model that did not produce realistic predictions? Objective 4 is almost always important, but doesn't necessarily answer all of the questions an investigator might have about their data. Statistical models strive to balance the objectives above to answer the questions at hand. Building statistical models is a process, and each step should be taken carefully. Here we outline the general process and offer some practical advice. We'll call this the statistical modeling process. The first step in this process is to understand the problem. This may seem obvious, but understanding the problem and context is critical to success. A sophisticated model might be useless if it is applied inappropriately. For example, suppose you have revenue data from several different locations of a store chain at unknown locations. It seems reasonable to average these revenue numbers as a summary of how this store is doing. Then suppose you discover that the stores are located in different countries and reported revenues in different currencies. Now, that average doesn't seem to have much meaning unless, of course, we get the revenue numbers converted to the same scale. The second step is to plan and properly collect relevant data. There may be multiple quantities that you could potentially measure to help answer your question. In this step, you decide what information would be most useful to solving your problem, how to collect the data, and how many data points to collect. The quality of your data collection plan determines the value of your data. For example, if you conduct a survey of peers in your workplace, your results would likely not generalize to all workers in the company, especially if there are multiple work sites. If you want generalizable results, a better plan would be to select a random sample among all employees to participate in your survey. This step is addressed in detail in most introductory statistics courses. The third step in this process is to explore your data. In this step, you should ensure that the data collection plan was followed and that the data were recorded accurately. If there are major surprises in the data, verify that they're not errors. In this step, you'll often want to visualize the data to gain a basic understanding of the relationships among your variables. This can help you decide what kinds of models might be appropriate. Finally, the practice of snooping around or mining your data, looking for interesting hypotheses to test, can potentially invalidate your statistical modeling results. If you want to mine your data and test your findings, it is usually best to randomly split your data into two parts. With one part, you can look for interesting things to test and fit different potential models. With the other, you can fit the model you chose using the first part to validate or see if the results can be replicated on other data. The fourth step in this process is to postulate a model. After gaining an understanding of how your data are structured, choose a model that can appropriately approximate or summarize the interesting content of the data. This might be an off-the-shelf statistical model like a regression, or it could be based on a scientific theory, such as a growth model. It could also be multiple models. Generally, it is desirable to find a model where the parameters we estimate can be interpreted in the context of the original problem. You might also have to strike a balance between model complexity and model generalizability. This is often referred to as the bias-variance trade-off. Large, complex models might be able to fit your particular data set very well, but may fail to generalize to future data. Let's look at an example of this. Let's suppose your data look like this. X is your explanatory variable, Y is your response variable, and you have points like these. One possible model you could fit would be just a linear regression going through the points. Another possibility for a model you could fit here would be essentially an interpolator that makes sure it goes through every single point. Now, consider a future scenario where you got another data set just like this one with a new cloud of points. You can imagine that perhaps this interpolated model, which fit the original data set perfectly, might struggle on a future data set. The next step in our statistical modeling process is to fit the model. In this step, we need to estimate the parameters of the model using the data. In this particular class, we're going to take a Bayesian approach to this step. Next, we're going to check the model. Here we want to check to see if the model adequately imitates the data generating process. Are predictions from the model realistic? Does it fit well to your data, or does it completely miss some of the features? We'll look into some of the techniques for doing this, including residual analysis and predictive checks later in the course. In this step, we may also compare competing models according to some criteria. Next, we're going to iterate. That is, return possibly to steps 4 through 6. If the model you have already fit is for some reason inadequate, we should return to step 4 and proceed through step 6 again with a new and hopefully better model that would address or correct the deficiencies from your previous model. Finally, we're going to use the model. If we've iterated through this enough times and decided that the model is good, or that we have selected an appropriate model, we can use the results to answer your original research questions and arrive at conclusions. In this course, we're going to focus on steps 4 through 8. But this does not mean that steps 1 through 3 should be ignored in any analysis. In fact, the importance of steps 1 through 3 cannot be overstated. The validity of your final results depends on them. That is why most introductory statistics courses will emphasize these steps. If you have not explored these issues in an introductory statistics course, we highly recommend you do so. We hope you'll refer to this outline, the statistical modeling process, often as you begin modeling data. In Lesson 1, we defined a statistical model as a mathematical structure used to imitate or approximate the data generating process. It incorporates uncertainty and variability using the theory of probability. A model can be very simple, involving only one variable. For example, suppose our data consist of the heights of n equals 15 adult men. So we have the heights of n equals 15 men. Clearly, it would be very expensive or even impossible to collect the genetic information that fully explains the variability in these men's heights. We only have the height measurements available to us. To account for the variability, we might assume that the men's heights follow a normal distribution. So we could write the model like this. yi will represent the height for person I. I will be our index. This will be equal to a constant, a number mu, which will represent the mean for all men, plus epsilon I. This is the individual error term for individual I. We're going to assume that epsilon I comes from a normal distribution with mean 0 and variance sigma squared. We're also going to assume that these epsilons are independent and identically distributed from this normal distribution. This is also for I equals 1 up to n, which will be 15 in our case. Equivalently, we could write this model directly for the yi's themselves. So each yi comes from a normal distribution, independent and identically distributed, with a normal distribution with mean mu and variance sigma squared. This specifies a probability distribution and a model for the data. If we know the values of mu and sigma, it also suggests how we might generate more fake data that behave similarly to our original data set. A model can be as simple as the one right here, or as complicated and sophisticated as we need to capture the behavior of the data. So far, this model is the same for frequentists and Bayesians. As you may recall from the previous course, the frequentist approach to fitting this model right here would be to consider mu and sigma to be fixed but unknown constants, and then we would estimate them. To calculate our uncertainty in those estimates, a frequentist approach would consider how much the estimates of mu and sigma might change if we were to repeat the sampling process and obtain another sample of 15 men over and over. The Bayesian approach, the one we're going to take in this class, tackles our uncertainty in mu and sigma squared with probability directly by treating them as random variables with their own probability distributions. These are often called priors, and they complete a Bayesian model. In the rest of this segment, we're going to review 3 key components of Bayesian models that were used extensively in the previous course. The 3 primary components of Bayesian models that we often work with are the likelihood, the prior, and the posterior. The likelihood is the probabilistic model for the data. It describes how, given the unknown parameters, the data might be generated. It can be written like this. The probability of y, the data, given theta. We're going to call our unknown parameters theta right here. Also in this expression, you might recognize this from the previous class as describing a probability distribution. It might be, for example, the density of the distribution if y were normal, or if y were discrete, this might actually represent the probability itself. We're just going to use, for our notation, a generic p right here. The prior, the next step, is the probability distribution that characterizes our uncertainty with the parameter theta. We're going to write it as p of theta. It's not the same distribution as this one. We're just using this notation p to represent the probability distribution of theta. By specifying a likelihood and a prior, we now have a joint probability model for both the knowns, the data, and the unknowns, the parameters. We can see this by using the chain rule of probability. If we wanted the joint distribution of both the data and the parameters theta, using the chain rule of probability, we could start with the distribution of theta and multiply that by the probability or the distribution of y given theta. That gives us an expression for the joint distribution. However, if we're going to make inferences about theta and we already know the values of y, we don't need the joint distribution. What we need is the posterior distribution. The posterior distribution is the distribution of theta conditional on y, theta given y. We can obtain this expression right here using the laws of conditional probability and specifically using Bayes' theorem. If we start with the laws of conditional probability, the conditional distribution of theta given y will be the joint distribution of theta and y, the same as this one right here, divided by the marginal distribution of y by itself. How do we get the marginal distribution of y? We start with the joint distribution like we have on top. And now we're going to integrate out or marginalize over the values of theta. Finally, to make this look like the Bayes' theorem that we're familiar with, we'll notice that the joint distribution can be written as the product of the prior and the likelihood. I'm going to start with the likelihood, because that's usually how we write Bayes' theorem. Again, we have the same thing in the denominator here. But we're going to integrate over the values of theta. These integrals right here are replaced by summations if we know that theta is a discrete random variable. The marginal distribution right here of y in the denominator is another important piece which you may use if you do more advanced Bayesian modeling. The posterior distribution is our primary tool for achieving the statistical modeling objectives from Lesson 1. Before fitting any model, we first need to specify all of its components. One convenient way to do this is to write down the hierarchical form of the model. By hierarchy, we mean that the model is specified in steps or in layers. We usually start with the model for the data directly, or the likelihood. For example, let's write again the model from the previous lesson. We had the height for person I, given our parameters mu and sigma squared, so conditional on those parameters, yi came from a normal distribution that was independent and identically distributed, where the normal distribution has mean mu and variance sigma squared. And we're doing this for individuals 1 up to n, which was 15 in this example. The next level that we need is the prior distribution for mu and sigma squared. For now, we're going to say that they're independent priors, so that our prior for mu and sigma squared is going to be able to factor into the product of two independent priors. We can assume independence in the prior and still get dependence in the posterior distribution. In the previous course, we learned that the conjugate prior for mu, if we know the value of sigma squared, is a normal distribution, and that the conjugate prior for sigma squared, when mu is known, is the inverse gamma distribution. Those might seem like natural choices, so let's write them down. Let's suppose that our prior distribution for mu is a normal distribution, where mean will be mu naught. This is just some number that you're going to fill in here when you decide what the prior should be. Mean mu naught, and let's say sigma squared naught will be the variance of that prior. The prior for sigma squared will be inverse gamma. We'll write inverse gamma like that. And the inverse gamma distribution has two parameters. It has a shape parameter, we're going to call that nu naught, and a scale parameter, we'll call that beta naught. Of course, we need to choose values for these hyperparameters here, but we do now have a complete Bayesian model. We now introduce some new ideas that were not presented in the previous course. Another useful way to write out this model is using what's called a graphical representation. To write a graphical representation, we're going to do the reverse order. We'll start with the priors and finish with a likelihood. In the graphical representation, we draw what are called nodes. So this would be a node for mu. The circle means that this is a random variable that has its own distribution. So mu with its prior will be represented with that. And then we also have sigma squared. The next part of a graphical model is showing the dependence on other variables. So once we have the parameters, we can generate the data, for example. We have y1, y2, and so forth, down to yn. These are also random variables, so we'll create these as nodes. And I'm going to double up the circle here to indicate that these nodes are observed. You see them in the data. So we'll do this for all of the y's here. And to indicate the dependence of the distributions of the y's on mu and sigma squared, we're going to draw arrows. So mu influences the distribution of y for each one of these y's. The same is true for sigma squared. The distribution of each y depends on the distribution of sigma squared. Again, these nodes right here that are double circled mean that they've been observed. If they're shaded, which is the usual case, that also means that they're observed. The arrows indicate the dependence between the random variables and their distributions. Notice that in this hierarchical representation, I wrote the dependence of the distributions also. We can simplify the graphical model by writing exchangeable random variables, and I'll define exchangeable later. We're going to write this using a representative of the y's here on what's called a plate. So I'm going to redraw this hierarchical structure. We have mu and sigma squared, and we don't want to have to write all of these nodes again. So I'm going to indicate that there are n of them, and I'm just going to draw one representative, yi, and they depend on mu and sigma squared. To write a model like this, we must assume that the y's are exchangeable. That means that the distribution for the y's does not change if we were to switch the index label, like the I on the y there. So if for some reason we knew that one of the y's was different from the other y's in its distribution, and if we also know which one it is, then we would need to write a separate node for it and not use a plate like we have here. Both the hierarchical and graphical representations show how you could hypothetically simulate data from this model. You start with the variables that don't have any dependence on any other variables. You would simulate those, and then given those draws, then you would simulate for from the distributions for these other variables further down the chain. This is also how you might simulate from a prior predictive distribution. So far, we've only drawn the model with 2 levels. But in reality, there's nothing that will stop us from adding more layers. For example, instead of fixing the values for the hyperparameters in the previous segment, those hyperparameters were the mu naught, the sigma naught, the nu naught, and the beta naught, we could specify just numbers for those, or we could have specified prior distributions for those variables to make this a hierarchical model. One reason we might do this is if the data are hierarchically organized so that the observations are naturally grouped together. We will examine these types of hierarchical models in depth later in the course. Another simple example of a hierarchical model is one you saw already in the previous course. Let's write it as yi given mu and sigma squared. So this is just like the model from the previous lesson. Will be independent and identically distributed normal with a mean mu and a variance sigma squared. The next step, instead of doing independent priors for mu and sigma squared, we're going to have the prior for mu depend on the value of sigma squared. That is, given sigma squared, mu follows a normal distribution with mean mu naught, just some hyperparameter that you're going to choose. And the variance of this prior will be sigma squared, this parameter, divided by omega naught, another hyperparameter that will scale it. We now have a joint distribution of y and mu given sigma squared. So finally, we need to complete the model with a prior for sigma squared. We'll use our standard inverse gamma with the same hyperparameters as last time. This model has 3 layers, and mu depends on sigma right here. The graphical representation for this model looks like this. We start with the variables that don't depend on anything else, so that would be sigma squared, and move down the chain. So here, the next variable is mu, which depends on sigma squared. And then dependent on both, we have the yi's. We'll use a double circle because the yi's are observed, they're data. And we're going to assume that they're exchangeable, so let's put them on a plate here for I in 1 to n. The distribution of yi depends on both mu and sigma squared, so we'll draw curves connecting those pieces there. To simulate hypothetical data from this model, we would have to first draw from the distribution or the prior for sigma squared, then the distribution for mu, which depends on sigma squared, and once we've drawn both of these, then we can draw random draws from the y's, which of course depends on both of those. With multiple levels, this is an example of a hierarchical model. Once we have a model specification, we can write out what the full posterior distribution for all the parameters given the data looks like. Remember that the numerator in Bayes' theorem is the joint distribution of all random quantities, all the nodes in this graphical representation over here, from all of the layers. So for this model that we have right here, we have a joint distribution that will look like this. We're going to write the joint distribution of everything, y1 up to yn, mu, and sigma squared. Using the chain rule of probability, we're going to multiply all of the distributions in the hierarchy together. So let's start with the likelihood piece. And we'll multiply that by the next layer, the distribution of mu given sigma squared, and finally with the prior for sigma squared. So what do these expressions right here look like? The likelihood right here, this level, because they're all independent, will be a product of normal densities. So we're going to multiply the normal density for each yi given those parameters. This, again, is shorthand right here for the density of a normal distribution. So that represents this piece right here. The conditional prior of mu given sigma squared is also a normal. So we're going to multiply this by a normal distribution of mu, where its parameters are mu naught and sigma squared over omega naught. And finally, we have the prior for sigma squared. We'll multiply by the density of an inverse gamma for sigma squared, given the hyperparameters mu naught, that is given the hyperparameters mu naught and beta naught. What we have right here is the joint distribution of everything. It is the numerator in Bayes' theorem. Let's remind ourselves really fast what Bayes' theorem looks like again. We have that the posterior distribution of the parameter given the data is equal to the likelihood times the prior over the same thing again, so this gives us in the numerator the joint distribution of everything, which is what we have written right here. In Bayes' theorem, the numerator and the denominator are the exact same expression, except that we integrate or marginalize over all of the parameters. Because the denominator is a function of the y's only, which are known values, the denominator is just a constant number. So we can actually write the posterior distribution as being proportional to, this symbol right here represents proportional to, the joint distribution of the data and parameters, or the likelihood times the prior. The posterior distribution is proportional to the joint distribution, or everything we have right here. In other words, what we have already written for this particular model is proportional to the posterior distribution of mu and sigma squared given all of the data. The only thing missing in this expression right here is just some constant number that causes the expression to integrate to 1. If we can recognize this expression as being proportional to a common distribution, then our work is done and we know what our posterior distribution is. This was the case for all models in the previous course. However, if we do not use conjugate priors, or if the models are more complicated, then the posterior distribution will not have a standard form that we can recognize. We're going to explore a couple examples of this issue in the next segment. Let's talk about a couple examples of models that don't have nice, clean posterior distributions. We'll first look at an example of a one-parameter model that is not conjugate. Suppose we have values that represent the percentage change in total personnel from last year to this year for, we'll say 10 companies. These companies come from a particular industry. We're going to assume for now that these are independent measurements from a normal distribution with a known variance equal to 1, but an unknown mean. So we'll say the percentage change in the total personnel for company I, given the unknown mean mu, will be distributed normally with mean mu, and we're just going to use variance 1. In this case, the unknown mean could represent growth for this particular industry. It's the average of the growth of all the different companies. The small variance between the companies in percentage growth might be appropriate if the industry is stable. We know that the conjugate prior for mu in this case would be a normal distribution. But suppose we decide that our prior beliefs about mu are better reflected using a standard t distribution with 1 degree of freedom. So we could write that as the prior for mu is a t distribution with a location parameter 0, that's where the center of the distribution is, a scale parameter of 1 to make it the standard t distribution, similar to a standard normal, and 1 degree of freedom. This particular prior distribution has heavier tails than the conjugate normal distribution, which can more easily accommodate the possibility of extreme values for mu. It is centered on 0, so that a priori there is a 50% chance that the growth is positive and a 50% chance that the growth is negative. Recall that the posterior distribution of mu is proportional to the likelihood times the prior. Let's write the expression for that in this model. That is, the posterior distribution for mu given the data y1 through yn is going to be proportional to the likelihood, which is this piece right here. It is a product from I equals 1 to n. In this case, that's 10. Densities from a normal distribution. Let's write the density from this particular normal distribution. It is 1 over the square root of 2 pi e to the negative 1/2 yi minus the mean squared. This is the normal density for each individual yi, and we multiplied it for our likelihood. The density for this t prior looks like this. It's 1 over pi times 1 plus mu squared. This is the likelihood times the prior. If we do a little algebra here, first of all, we're doing this up to proportionality. So constants being multiplied by this expression are not important. So this square root of 2 pi being multiplied n times just creates a constant number, and this pi out here creates a constant number. We're going to drop them in our next step. So this is now proportional to, we're removing this piece, and now we're going to use properties of exponents. The product of exponents is the sum of the exponentiated pieces. So we have the exponent of negative 1/2 times the sum from I equals 1 to n of yi minus mu squared. And then we're dropping the pi over here. So times 1 plus mu squared. We're going to do a few more steps of algebra here to get a nicer expression for this piece, but we're going to skip ahead to that. We've now added these last two expressions to arrive at this expression here for the posterior, or what's proportional to the posterior distribution. This expression right here is almost proportional to a normal distribution, except we have this 1 plus mu squared term in the denominator. We know the posterior distribution up to a constant, but we don't recognize its form as a standard distribution that we can integrate or simulate from. So we'll have to do something else. Let's move on to our second example. For a 2-parameter example, we're going to return to the case where we have a normal likelihood, and we are now going to estimate mu and sigma squared because they're both unknown. Recall that if sigma squared were known, the conjugate prior for mu would be a normal distribution. And if mu were known, the conjugate prior we could choose for sigma squared would be an inverse gamma. We saw earlier that if you include sigma squared in the prior for mu and use the hierarchical model that we presented earlier, that model would be conjugate and have a closed form solution. However, in the more general case that we have right here, the posterior distribution does not appear as a distribution that we can simulate or integrate. Challenging posterior distributions like these ones, and most others that we'll encounter in this course, kept Bayesian methods from entering the mainstream of statistics for many years, since only the simplest problems were tractable. However, computational methods invented in the 1950s and implemented by statisticians decades later revolutionized the field. We do have the ability to simulate from the posterior distributions in this lesson, as well as for many other, more complicated models. How we do that is the subject of next week's lesson. Before we learn how to simulate from complicated posterior distributions, let's review some of the basics of Monte Carlo estimation. Monte Carlo estimation refers to simulating hypothetical draws from a probability distribution in order to calculate important quantities of that distribution. Some of these quantities might include the mean, the variance, the probability of some event, or the quantiles of the distribution. All of these calculations involve integration, which, except in the simplest cases, can be very difficult or even impossible to compute analytically. Let's suppose we have a random variable theta. This random variable theta is going to follow a gamma distribution with shape A and rate B. And let's suppose A equals 2 and B equals 1/3. To calculate the mean of this distribution, we would need to compute the following integral. The expected value of theta is equal to the integral over the whole space for theta, which in the case of a gamma is from 0 to infinity, theta times the density for theta. Now in the case of a gamma, this equals the integral from 0 to infinity theta times b to the power of a over a gamma function evaluated at a times theta to the a minus 1 and e to the negative b theta. This is the integral we would need to compute. And in this particular case, it is possible to compute this integral. The answer is a over b, or with these particular values, the answer is 6. However, we could verify this answer using Monte Carlo estimation. To do so, we would simulate a large number of draws. Let's call them theta star I for draw I in 1 up to some large number m. We would simulate these from this gamma distribution, and to estimate the sample, or to estimate the actual theoretical mean of this distribution, we would take the sample mean, or the average of these draws. Why can we do this? Recall from the previous course that if we have a random sample from a distribution, the average of those samples converges in probability to the true mean of that distribution by the law of large numbers. Furthermore, by the central limit theorem, this sample mean, or the sample mean of these pieces right here, we're going to call that theta bar star, which is 1 over m times the sum of our simulated values of theta star I. This sample mean right here approximately follows a normal distribution where the mean of that normal distribution is the true expected value, and the variance of that is the true variance of the distribution divided by m, the sample size. The theoretical variance of theta is the following integral. The variance of theta, just like the expected value we did up here, we're calculating the expected value of theta minus its expected value squared. And of course, multiplying by the density of theta. Just like we did with the mean, we could approximate this variance with the sample variance. This method of Monte Carlo estimation can be used to calculate many different integrals. Let's say, for example, that h of theta is some function of theta, and we want to calculate the following integral. H of theta times the density of theta d theta. This integral is precisely what is meant by the expectation of h of theta. So, conveniently, we can approximate it by taking the sample mean of h evaluated for each of these samples. That is, if we were to calculate the sample mean where we evaluate the h function on each of our simulated samples of theta, this quantity would approximate this expected value, which is this integral. So we would apply this function h to every simulated sample and then take the average of the results. One extremely useful example of such an h function is the indicator function, written like this. It's a function of theta, and a here would be some sort of logical condition about the value of theta. To demonstrate this, let's suppose that in an example, let's say that h of theta is the indicator that theta is less than 5. This function here, this indicator, will give us a 1 if theta is indeed less than 5, or it will return a 0 otherwise. So what is the expected value of h of theta here? Well, this is the integral from 0 to infinity, once again, assuming that theta is coming from a gamma distribution. The expected value of h of theta will be h of theta, this indicator function, times the density of theta. So if we evaluate this, this function will come out to be a 1 if theta is between 0 and 5. So 0 to 5, 1 times the density of theta, plus the rest of the values, 5 up to infinity, of 0 times the density. This piece right here is going to disappear, and this right here, if we integrate the density between these two values, that's simply calculating the probability that 0 is less than theta is less than 5, the probability that theta is between these two numbers. So what does this mean? It means that we can approximate this probability right here by drawing many samples, theta star I, and approximating this integral with the following. We would take the sample mean of these indicator functions where theta star is less than 5 and apply it to our simulated values. What this function does is simply counts how many of our simulated values meet this criteria and then divides by the total number of samples taken. So this approximates the probability that theta is less than 5. That's pretty convenient. Likewise, we can approximate quantiles of a distribution. If we're looking for a value z that makes it so that the probability of being less than z is 0.9, for example, we would simply arrange the samples, theta star I, in ascending order, and then we would find the smallest value of the theta stars that's greater than 90% of the others. In other words, we would take the 90th percentile of the theta stars to approximate the 0.9 quantile of the distribution. How good is an approximation by Monte Carlo sampling? Again, we can turn to the central limit theorem, which tells us that the variance of our estimate is controlled in part by m, our sample size. If we want a better estimate, we need to choose a larger m value. For example, if we're looking for the expected value of theta, then we can take the sample mean. In the last video, we called this theta star bar. By the central limit theorem, the sample mean approximately follows, I'm going to use this symbol to denote approximately distributed, normal, where the mean of this normal distribution is the true expected value of theta, and the variance of this distribution is the true variance of theta divided by our sample size m. The variance tells us how far our estimate might be from the true value. One way to approximate this variance, the theoretical variance of theta, is if we replace it with the sample variance. We could calculate the sample variance like this. Let's call it variance of theta hat. We're just approximating that integral for the variance. So this will be 1 over m. So it's just the sample mean of theta I star minus the expected value, which we're also approximating with the sample mean. So let's plug that in here. Sometimes people also divide by m minus 1, but if m is really large, then it won't matter that much. The standard deviation of our Monte Carlo estimate is the square root of that. So the square root, and if we're plugging in the value, we'll have variance hat of theta divided by m under the square root. If m is large, it is reasonable to assume that the true value will likely be within about 2 of these standard deviations from your Monte Carlo estimate. We're going to call this the standard error of your Monte Carlo estimate. We can also obtain Monte Carlo samples from hierarchical models. As a simple example, let's go ahead and consider a binomial random variable y. So y, given phi, is going to follow a binomial distribution with 10 trials, and on each trial, a probability of success that's equal to phi. Let's further assume that phi comes from its own distribution, that it's random. So this would be, for example, if we had a prior for phi. Let's say it comes from a beta distribution with parameters 2 and 2. Given any hierarchical model, we can always write out the joint distribution of y and phi. The joint distribution of y and phi using the chain rule of probability will be the distribution of phi times the distribution of y given phi. This should look familiar. It's like the prior times the likelihood. To simulate from this joint distribution, we're going to repeat the following steps for a large number of samples, m. The first step to simulate from this, the first step we're going to take to simulate would be to draw a theta star I from its beta distribution. Then the second step is, given this value that we just drew for phi, we would draw a sample from this binomial distribution. We'll call this sample y star I from this binomial distribution with 10 trials, and the success probability would be the success probability we just drew, phi I star. If we repeat this process for many samples, we're going to produce m independent pairs, yi phi I pairs. These pairs right here are drawn from their joint distribution. One major advantage of Monte Carlo simulation is that marginalizing these distributions is easy. Calculating the marginal distribution of y might be difficult here. It would require that we integrate this expression with respect to phi, to integrate out the phis. But if we have draws from the joint distribution, then we can just discard the phi I stars and use the yi stars as samples from their marginal distribution. This is also called prior predictive distributions, which was introduced in the previous course. In the next segment, we're going to demonstrate some of these principles. Remember, we don't yet know how to sample from complicated posterior distributions that were introduced in the previous lesson. But once we learn that, we're going to be able to use the principles from this lesson to make approximate inferences for those posterior distributions. Monte Carlo simulation for the most common distributions is straightforward in R. As a refresher from the previous course, let's start up R and talk a little bit about how we'll use it throughout the course. When we start up R, we first see the R console, which gives us some information about the current R session that we are running. We will always enter our code into the R console to run it. For example, if we want to know the answer of 2 plus 3, we can enter it directly in the console and press return to get the answer. It will be convenient for us to save our code for later, and one way to do that is to use R scripts. To open a new script, go to File, New Document. This opens a new script for us, where we can work over here, create and edit and save code that we can run in the R console. We also get a warning which has to do with the particular operating system of the computer I'm using. You may or may not get this warning on your computer, but we're not going to worry about it. It won't affect our session. Let's begin our session by setting the random number generator seed using the set.seed function in R. The only argument we need to give the set.seed function is some integer, positive or negative. This function initializes the random number generator so that we can replicate any results that we get. To get different random numbers, simply change the value that we enter into this function. To run this code, we have several options. One option is to select the line of code, copy it, and paste it directly into the console and press return to run it. Alternatively, we can select the line of code and go to Edit, Execute, which will also run the code. You may have also noticed that there is a keyboard shortcut associated with Execute. It is to hold down the Command key and press return. So if we want to run this line of code, we hold down the Command key and press return. Now that we've set the random seed for our session, let's start with an example from the previous segment, where our random variable theta follows a gamma distribution with parameters a equals 2 and b equals 1/3. This gamma distribution could represent the posterior distribution of theta if our data came from a Poisson distribution with mean theta and we had used a conjugate gamma prior. Let's start with Monte Carlo sample size 100. We will save that as a variable m equals 100. Let's also save the parameters for the gamma distribution. A, the shape parameter, is 2, and b, the rate parameter, is 1/3. These variables have been entered into our script, but are not currently saved in the R session. To run this code, we need to execute each of these lines. First, I'll enter M by pressing Command and Return. Now, M is saved in our workspace. We can also run multiple lines of code by selecting multiple lines of code and then executing them together. Now, M, A, and B are all in our R session. We can verify their values. To simulate M independent samples from this gamma distribution, we're going to use the R gamma function. We will save the simulated values in the variable theta, and we'll run R gamma, which creates random generations from the gamma distribution, and we want to create M of those. We also have to enter the parameters for the gamma distribution. Shape equals A, and rate equals B. To run the simulation, simply run this line of code. All 100 draws from this gamma distribution are now saved in the theta vector. We can look at this by printing it, where we see all 100 simulated values. If we don't want to see all of them, we can also use the head function, which shows us only the first 6 values. If we want to see the end of the vector, we can use the tail function. Let's plot a histogram of these generated values and compare it to the true density of a gamma distribution. To plot the histogram, let's use the hist function and give it our theta vector. We're also going to use the frequency equals false option so that it gives us a probability density rather than counts. If I run this line of code, we get the histogram for the simulated values. To compare this to the theoretical probability density function for the gamma distribution, let's use the curve function, which draws a curve on our plot. The curve we want to draw is the density of the gamma distribution, or d gamma. The first argument for this function is x, which is generic and refers to the x-axis. And then we need to give it our parameters for the gamma distribution, shape and rate. To visually distinguish this from our histogram, let's add some color We'll make it blue because it's the true value. And we'll say add equals true so that it creates a plot on top of the existing plot. So if we run this curve, we get the true probability density function for a gamma distribution with shape 2 and rate 1/3. We can see that the data are pretty good at approximating this distribution. We can now use our simulated values to find a Monte Carlo approximation to the expected value of theta. To do this, let's take an average of our simulated values. One way to do this is to sum all of the theta variables and divide by the total number that we simulated. If we run this line, we get our Monte Carlo approximation to the mean, 5.5. A faster way to calculate this would be to use the mean function directly. If we say we want the mean of the theta vector, we get the same answer. How does this compare with the true value of the expected value of theta? If theta follows this gamma distribution with shape A and rate B, the expected value will be A divided by B. For this gamma distribution, the expected value, or the mean, is 6. Our Monte Carlo approximation was okay, but not great. We can improve this Monte Carlo approximation if we simulate more values. Let's do that. We'll increase our M, the Monte Carlo sample size, up to, let's say, 10,000. We have to rerun this line of code so that M is saved as 10,000. We're not changing the parameters A and B, so we'll leave those as they are. But we do need to resimulate our theta vector. We now have 10,000 samples from this gamma distribution. Let's look at the Monte Carlo approximation of the mean. 6.02, much closer to the true theoretical value of 6. What about the variance of theta? We can calculate our Monte Carlo approximation to the variance using the var function in R, where we calculate the sample variance of theta. 18.04. Can you guess what the theoretical value for this variance would be? For this gamma distribution, the variance is A divided by B squared. The true value is 18. So our Monte Carlo approximation is actually quite close. We can also use our Monte Carlo simulation to approximate other characteristics of this gamma distribution. For example, if we want to approximate the probability that theta is less than 5, we can simply count how many of our simulated thetas are less than 5. Let's do this. First, we'll create an indicator variable that indicates whether theta is less than 5. This line of code instructs R to look at each individual draw in the theta vector and compare it to the value 5. Let's run it. And now let's look at the first few values. So, the first value of theta that we simulated was not less than 5 because we get a false value for our indicator. The same is true for the second value of theta. It was not less than 5. But the third value was less than 5. Let's just confirm that this is true. The first two values were not less than 5, but the third value is less than 5. Conveniently, if we calculate the mean of this indicator, R will convert the true-false values into zeros and ones, add them up, and take the mean for us. This creates an approximation to the probability that theta is less than 5. In our case, our Monte Carlo approximation to this probability is 0.497. If we want to compare this to the true probability, we can use the p-gamma function. That is p-gamma, which evaluates the cumulative distribution function, the CDF, for this gamma. We want to know the probability of being less than 5 if the shape is A and the rate is B. And we can see that our Monte Carlo approximation is really quite close. The true probability that this theta random variable is less than 5 is 0.496. What if we are interested in the 0.9 quantile, or the 90th percentile of this distribution, this gamma distribution for theta? We can use the quantile function in R, where we give it the theta values, and we tell it what probability we want, or which quantile we want. In this case, we want the 90th percentile, or the 0.9 quantile of theta. Let's run this line. We see that the 90th percentile of a gamma 2 1/3 is 11.74. That is our Monte Carlo approximation to the quantile. If we want to know the actual true quantile, we can use the Q-gamma function, where we want the probability of being less than this value to be 0.9. Again, we need to give it the gamma parameters. If we run this line, we get the true theoretical value, 11.669. Again, quite close to our Monte Carlo approximation. Of course, with the gamma distribution, all of these theoretical values are available as functions in R, and so Monte Carlo simulation is not as useful to us. But later in the course, we will not have functions like the d gamma or the p gamma or the q gamma available to us for the distributions we'll be using later in the course. This is where Monte Carlo estimation will be particularly useful to us. We can use the central limit theorem to approximate how accurate our Monte Carlo estimates are. For example, if we seek the expected value of theta, or the mean of this gamma distribution, then we can use the sample mean from our simulated values, the simulated theta here. The sample mean of these thetas approximately follows a normal distribution, where the mean of that normal distribution is the true expected value of theta, and the variance of that normal distribution is the true variance of theta divided by m, our Monte Carlo sample size. That means that if we increase m to be a very large number, the variance of our Monte Carlo estimate gets very small. In other words, our Monte Carlo estimate will be very accurate. To create a standard error for our Monte Carlo estimate, we will use the sample standard deviation divided by the square root of m. So let's create this variable. The standard error will be the sample standard deviation, which is the SD function in R, the sample standard deviation of our simulated values divided by the square root of m, our Monte Carlo sample size. We can run this line of code and print off the standard error. This is the standard error of our approximation to the expected value of theta. If we wanted to create a confidence interval for our Monte Carlo approximation, we could look at, for example, 2 times this standard error. That is, we are reasonably confident, about 95% confident, that the Monte Carlo estimate for the expected value of theta is no more than this far from the true value of the expected value of theta. We can create this confidence interval here. We'll start with our Monte Carlo estimate, and we can take away 2 standard errors. We'll run that. That gives us the lower edge of our confidence interval. To get the higher upper edge of our confidence interval, let's change this minus to a plus and run this line. That is, we are reasonably confident, after running our Monte Carlo simulation, that the true mean of this gamma distribution is between 5.9 and 6.1. Of course, we've already seen that the true value is 6. These standard errors give us a reasonable range for the quantity we are estimating with Monte Carlo. The same applies for other Monte Carlo estimates. For example, the probability that theta is less than 5. Let's recreate that indicator variable that theta is less than 5. We approximated the probability that theta is less than 5 by taking the mean of those indicators. And of course, the true value we can get with the CDF, or P gamma, of being less than 5, where the shape parameter is A and the rate parameter is B. Now, if we want the Monte Carlo standard error for our Monte Carlo estimate, we can calculate it as the standard error is the sample standard deviation of our indicator variables divided by the square root of m. Very similar to our standard error that we calculated before, but now we're using our new indicator variable. Let's run this and print the value of the standard error. If we look at 2 times the standard error, we can say that we are quite confident that our Monte Carlo estimate of the probability, right here, is within 0.01 of the true value, which is right here. And it looks like, in this case, our Monte Carlo estimate is within 0.01 of the true value. Let's also do the second example, where we simulate from a hierarchical model. In our example, we had a binomial random variable, where y followed a binomial distribution with 10 trials and success probability phi, and phi followed a beta distribution with parameters 2 and 2. To simulate from this joint distribution, we will repeat the following 2 steps. Here are the 2 steps. I have written them as 2 lines of code and commented them out with the pound or hashtag key. The first step is to simulate a phi variable from a beta distribution. And then given that phi variable, we will simulate the ith iteration of the y variable from its corresponding binomial, where the success probability is the phi that we just drew in step 1. We will repeat these 2 steps many times to create a Monte Carlo sample from the joint distribution of phi and y. Let's choose a Monte Carlo sample size of 100,000. That is 1 times 10 to the 5th power. That's shorthand for writing 100,000. We can run this line of code to save m in our R session. And before we simulate, let's create the variables before we populate them. The y variable will be a numeric vector with m entries. To see what we just did, let's take a look at the head of y. We initialized a vector of zeros that has 100,000 entries. We'll populate these with our simulations. Let's do the same with phi. And run that line. To follow our algorithm for this joint simulation, we're going to first write a loop in R. To perform a loop in R, we use the keyword for, and then we tell it what we're iterating over. We'll iterate over the variable I. For I in 1 to m, repeat the following. To put things inside a loop with many lines of code, we use curly braces. So we'll enter the loop code inside these two curly braces. The first step is to simulate the value of phi. So phi, the ith value of phi, will be drawn from a beta distribution. We'll take a single draw with shape 1 parameter being equal to 2, and the second shape parameter being equal to 2. Now, given that draw for phi, we can simulate a draw for y. The ith simulation for y will come from a binomial distribution, and we want to simulate, so our binomial. We'll simulate a single draw of a binomial for 10 trials and success probability phi, specifically the phi that we just drew for the ith iteration. This loop will perform this algorithm. If we select the entire loop and hold Command and press Return, that runs the code. This took about 1/2 of a second to run in R. However, we can improve on this code. R tends to be very slow with loops, and so one way to speed it up is to write vectorized code. Here is an example of doing the same simulation with vectorized code. We will first draw all of the phi variables at once from the beta distribution, but this time we will take m draws. From this beta distribution. That will create a vector of phis with those 100,000 simulations. Now we can simulate y with one line of code by running our binomial. We want m simulations again, where each simulation has 10 trials and success probability. Here we will give it the entire vector of phis. In other words, we want to draw 100,000 binomials, all with the same number of trials, but all with a different phi. These phis come from our previous simulation. Let's run both of these lines together. And they were almost instantaneous. It is good to avoid writing loops in R if we can by using vectorized code like this. If we are interested only in the marginal distribution of y, we can just ignore the draws for the phis and treat the draws of y as a sample from its marginal distribution. That distribution will not be a binomial distribution. It'll actually be a beta binomial distribution. Conditional on phi, y follows a binomial distribution, but unconditionally, the marginal distribution of y is not binomial. Let's take a look at that distribution. First, we can do a table of the values of y. This will tell us how often each of the different values of y were drawn in our simulation. So if we run this table, we can see how many of the simulations resulted in 7 successes, for example. We can divide this by the Monte Carlo sample size to get an approximation of the probabilities. So for example, under the marginal distribution of y, there is approximately 11% chance of 3 successes. Let's plot this distribution. We'll create a plot of this table and run it. Here is our Monte Carlo approximation of the distribution of y. Again, this is not a binomial distribution. It is actually a beta binomial distribution, the marginal distribution of y. If we're interested in the marginal expected value of y, again, we can just ignore the phi variables that we drew and calculate the mean of our simulated y's, approximately 5. Metropolis hastings is an algorithm that allows us to sample from a generic probability distribution, which we'll call our target distribution, even if we don't know the normalizing constant. To do this, we construct and sample from a Markov chain whose stationary distribution is the target distribution we're looking for. It consists of picking an arbitrary starting value and then iteratively accepting or rejecting candidate samples drawn from another distribution, one that is easy to sample. Let's say we want to produce samples from a target distribution. We're going to call it P of theta, but we only know it up to a normalizing constant or up to proportionality. What we have is G of theta. So we don't know the normalizing constant because perhaps this is difficult to integrate. So we only have G of theta to work with. The Metropolis hastings algorithm will proceed as follows. The first step is to select an initial value for theta. We're going to call it theta naught. The next step is for a large number of iterations. So for I from 1 up to some large number m, we're going to repeat the following. The first thing we're going to do is draw a candidate. We'll call that theta star is our candidate. And we're going to draw this from a proposal distribution. We're going to call the proposal distribution Q of theta star, given the previous iteration's value of theta. We'll talk more about this Q distribution soon. The next step is to compute the following ratio. We're going to call this alpha. It is this G function evaluated at the candidate divided by the distribution or the density here of Q evaluated at the candidate given the previous iteration. And all of this will be divided by G evaluated at the old iteration, that divided by Q evaluated at the old iteration, given the candidate value. If we rearrange this, it'll be G of the candidate times Q of the previous value given the candidate, divided by G at the previous value, and Q evaluated at the candidate given the previous value. The next step, once we've calculated alpha, is to check alpha. If it's greater than or equal to 1, then we're going to accept the candidate. So we're going to accept the candidate theta star and set our current iteration of theta, so that'll be I, will be that candidate value. If alpha is between 0 and 1, then what we're going to do is accept the candidate and set theta I equal to the candidate with probability alpha. Then the other possibility is to reject the candidate and set the current iteration of I equal to the previous iteration of I. And we do this with probability 1 minus alpha. These steps B and C act as a correction since the proposal distribution, Q, is not the target distribution, P. At each step in the chain, we draw a candidate and decide whether to move the chain there or to remain where we are. If the proposed move to the candidate is advantageous, meaning if alpha is greater than 1, we will move there for sure. If it is not advantageous, we might still move there, but only with probability alpha. Since our decision to move to the candidate only depends on where the chain currently is, this is a Markov chain. One careful choice we must make is with the candidate generating distribution Q. It may or may not depend on the previous iteration's value of theta. One example where it doesn't depend on the previous value would be if Q of theta star is always the same distribution. If we take this option, Q of theta should be similar to P of theta to approximate it. Another popular option, one that does depend on the previous iteration, is called random walk Metropolis hastings. Here, the proposal distribution is centered on the previous iteration. For instance, it might be a normal distribution where the mean is our previous iteration, theta I minus 1. Because the normal distribution is symmetric around its mean, this example comes with another really nice advantage. This Q evaluated at the candidate given the mean here, the density value for this Q will be equal to this density value of the old value where the mean is the candidate. This causes these two Q's to cancel out when we calculate alpha. So in random walk Metropolis hastings, where the candidate is drawn from a normal distribution where the mean is the previous iteration's value, and we use a constant variance in that normal distribution, the acceptance ratio, alpha, will be really easy. It'll just be G at the evaluated at the candidate divided by G evaluated at the previous iteration. Clearly, not all candidate draws are accepted. So our Markov chain sometimes stays where it is, possibly for many iterations. How often you want the chain to accept candidates depends on the type of algorithm you use. If you approximate P with Q and always draw candidates from that distribution, accepting candidates often is a good thing. It means that Q is approximating P well. However, you still may want to have Q have a larger variance than P and see some rejection of candidates to be as an assurance that Q is covering the space well. As we'll see in coming examples, a high acceptance rate for random walk Metropolis hastings samplers is not a good thing. If the random walk is taking too small of steps, it will accept candidates often, but will take a very long time to fully explore the posterior distribution. If the random walk is taking too large of steps, many of its proposals will have low probability and the acceptance rate will be low. That will cause us to waste many of the draws. Ideally, a random walk sampler should accept somewhere between 23 and 50% of the candidates proposed. In the next segment, we're going to demonstrate this algorithm in the discrete case, where we can show mathematically that the Markov chain converges to the target distribution. In the following segment after that, we will demonstrate coding a random walk Metropolis hastings algorithm in R to solve one of the problems from the end of lesson 2.
Hello, my name is Herbie Lee. You may remember me from the previous course. I'm a professor of statistics and applied math here at the University of California, Santa Cruz. Here I'm going to give you a demonstration of using Markov chain Monte Carlo to estimate posterior probabilities in a simplified case where we can actually work out the correct answer in closed form and show that the Metropolis hastings algorithm is indeed working and giving us the right answer. If you recall from the previous course, the example where your brother, or maybe your sister, has a loaded coin that you know will come up heads 70% of the time. But they come to you with some coin, you're not sure if it's the loaded coin or a fair coin. They want to make a bet with you, and you have to figure out which coin this is. Suppose you have a prior probability that it's a 60% probability that they'll bring the loaded coin to you. They let you flip it 5 times, you get 2 heads and 3 tails. And now you need to figure out what's your posterior probability that this is the loaded coin. I've written this all out in advance. Our unknown parameter, theta, can either take the values fair or loaded. Our prior for theta, its probability theta equals loaded, is 0.6, our prior probability that we think they're bringing us the loaded coin. Our likelihood will follow a binomial distribution, depending upon the value of theta. Our posterior then, we can look at posterior for theta, given we saw x equals 2 heads. Posterior is the likelihood times the prior divided by a normalizing constant. In this case, we can work out the binomial and our prior, and we see that we get these expressions at the end. We get posterior probability theta equals loaded, given we saw 2 heads, to be 0.388. This is all review from the previous course so far. But suppose we had a more complicated problem where we couldn't work this all out in closed form. We'll know the likelihood in the prior, but we may not be able to get this normalizing constant. Can we instead do this by simulation? And indeed, yes, we can. We can do this with Markov chain Monte Carlo, in particular using the Metropolis hastings algorithm. What we'll do is we'll set up a Markov chain whose equilibrium distribution has this posterior distribution. So we'll consider a Markov chain with 2 states, theta equals fair and theta equals loaded. And we'll allow the chain to move between those 2 states with certain transition probabilities. We set this up using the Metropolis hastings algorithm. So under the Metropolis hastings algorithm, step 1 is we start at an arbitrary location. And in this case, we could start at either theta naught equals fair or theta naught equals loaded. It doesn't really matter where we start. We'll be moving back and forth, and we're going to look at the long-term running average, the long-term simulations. So the key is we'll be simulating. So we'll run m simulations, and in each iteration, we'll propose a candidate and either accept it or reject it. So the first part is we're proposing a new candidate.
We'll call this candidate theta star. And we're going to propose it to be the other state compared to where we are now. So where we are now is theta sub I minus 1. And so we'll propose to move. If our current state is fair, we'll propose theta star to be loaded. If our current state is loaded, we'll propose theta star to be fair. Then we want to think about what's our acceptance probability alpha. The general form for alpha is g of theta star divided by q of theta star given theta I minus 1 over g of theta I minus 1 divided by q of theta I minus 1 given theta star. In this case, we're going to be using our unnormalized likelihood times prior, this section. So this is f of x equals 2 given theta times theta star times f of theta star divided by the q function. In this case, the q function is 1. This will be over the likelihood for theta I minus 1 times the prior for theta I minus 1. Our q function here is always going to be 1 because we have a deterministic proposal. We're proposing it to be the other thing. So with probability 1, we're going to propose theta to be the other state. And so it's really easy here. It's just a 1. So if theta star equals loaded, then we can see alpha equals this value, 0.00794, divided by this value here for fair, 0.0125. If theta star equals fair, then alpha is just the reciprocal of this. So when theta star is loaded, we get a 0.635. If it's fair, we get a 1.574. Given these probabilities, we then can do the acceptance or rejection step. The easier one is that if theta star equals fair, alpha is bigger than 1, so we always accept. And so in accepting, we then set theta I equals fair. If theta star equals loaded, alpha equals 0.635. So we accept theta star with probability 0.635. And if we accept it, set theta I equals loaded. Otherwise, set theta I equals theta I minus 1. It doesn't accept. It stays in its same old fair state. We can draw this out as a Markov chain with two states, fair and loaded. If it's in the loaded state, it will move with probability 1 to the fair state. If it's in the fair state, it will move with probability 0.635 to the loaded state, and with probability 0.365, it will stay in the fair state. And so here's a little diagram for this Markov chain with two states, in which case it will move back and forth with certain probabilities. Thus, if we wanted to find our posterior probability, f of theta equals loaded, given x equals 2, we can simulate from this Markov chain using these transition probabilities and observe the fraction of time that it spends in the state theta equals loaded, and this gives us a good estimate of the posterior probability that it's the loaded coin. In this particular case, we can also show that this gives us the theoretical right answer. If you've seen a little bit of theory of Markov chains, we can say that a Markov chain with transition probability capital P has stationary distribution pi if pi times p equals pi. That's the definition of a stationary distribution. Here we have a transition probability matrix P, where we can think about fair and loaded. Moving from the fair state, remaining in the fair state, happens with probability 365, and it moves from fair to loaded with probability 635. If it's in the loaded state, it will move to the fair state with probability 1, and it will stay in the loaded state with probability 0. In this case, we want our stationary distribution to be the posterior probabilities, which you can recall are 0.612 of being fair and 0.388 of being loaded. And so indeed, if you do just a minimal amount of matrix algebra, you can see that 0.612, 0.388 multiplied by this matrix, 0.365, 0.635, 1, 0, does indeed give you 0.612 and 0.388, at least 2 within rounding error. Thus, in this case, we can see that we do get the correct stationary distribution for the Markov chain using the Metropolis Hastings algorithm, and that when we simulate it, we do get correct estimates then of the posterior probabilities. This is a nice simple example where we can work out the posterior probabilities in closed form. We don't actually need to run Markov chain Monte Carlo. But this method is very powerful because all we need is to be able to evaluate the likelihood and the prior. We don't need to be evaluating the full posterior and getting that normalizing constant. And so this applies to a much broader range of more complicated problems where we can use Markov chain Monte Carlo to simulate to be able to get these probabilities. We'll make good use of this in the rest of this course.
Let's do an example now of a random walk Metropolis Hastings sampler for a continuous variable. Recall the model from the last segment of Lesson 2, where the data are the percentage change in total personnel from last year to this year for 10 companies. To remind us, I have the model right here. So yi represents the percent change in personnel for company I, and given mu, the mean, each of these y's is identically distributed and independent from this normal distribution with mean mu and variance 1. Our prior distribution on mu is a t-distribution with location 0, scale parameter 1, and degrees of freedom 1. This is also referred to as the Cauchy distribution. Because this model is not conjugate, the posterior distribution does not have a standard form that we can easily sample. To get posterior samples, we're going to need to set up a Markov chain whose stationary distribution is the posterior distribution we want. So, recall that the posterior distribution has this form. We derived this expression for the posterior in Lesson 2. The posterior distribution for mu is proportional to this expression on the right. This function here will be our g of mu. The first thing we can do in R is to write a function that will evaluate g of mu for us. Because posterior distributions include likelihoods, which are the product of many numbers that are potentially small because they're like probabilities, g of mu might evaluate to such a small number that the computer treats it effectively as a 0. To avoid this problem, we're going to work on the logarithmic scale, which will be more numerically stable. So instead of computing this g function, we're going to compute the log of g. If we take the log of this function, we get this expression right here. So let's write this function in R. Let's call it LG for the log of g. It'll be a function, and it will take 3 different arguments. We need to have y bar, we need to enter n, and we need to enter a value for mu for this function to evaluate. So we need mu, n, and y bar. Just like with a for loop, we need curly braces when we're defining a function. Okay, the first thing we'll calculate is mu squared, and we're going to call it mu2 as a variable inside this function. It's just the square of mu. Then we'll output this expression right here. So it needs to be n times, and then we'll do parentheses here, y bar times mu minus mu squared divided by 2. Let's actually space these out a little bit so it's easier to read. Minus the log of 1 plus mu squared. This completes the log of g function, and we can read this in to our R console. Next, let's write a function to execute the random walk Metropolis hastings sampler, and we're going to use normal proposal distributions to do this. As we write the function, let's take a look at the algorithm here to remind us how it goes. I'm going to call this function MH for Metropolis hastings. We need a few more arguments in this function. First, we need a couple of the arguments from before, n, the sample size, y bar, which is the sample mean of y. We need to choose how many iterations we're going to run this sampler for, so I'll call that n underscore iter. That represents how many iterations. We need an initial value for mu. We'll call that mu underscore init. And finally, we need a standard deviation for the candidate generating normal distribution. So let's call that candidate standard deviation. These are the arguments we'll need in our function here. Okay, so first we need to do step 1, which is to set up an initial value. Before we do that, let's initialize a vector of mu values that we will output with this function. So mu out will get a numeric vector with n.iter entries. It's useful with a Metropolis hastings algorithm to keep track of how often our candidates get accepted. So let's create a variable called accept, and we'll initialize it at 0. Now, as we iterate through, we're going to be updating our value for mu. As we update it, we need to store it somewhere. Let's call that mu underscore now. And we'll initialize it at the first value, the initial value for mu. We also need a current value for the log of g function, LG now. This is going to be an evaluation of the LG function. So we need to give it 3 arguments, mu, which will be mu now, n, which is always just n, and we'll need to give it y bar. This completes step 1 of setting initial values and initializing our random walk Metropolis hastings sampler. So now let's move on to step 2, where we need to repeat the following steps many times. This means we're going to do it in a for loop. So for I, we'll iterate over the variable I in 1 to n underscore iter. That's our number of iterations. We're going to do the following. The first thing we need to do is draw a candidate for our parameter mu from a proposal distribution. So let's draw mu candidate. We'll call our variable mu candidate. And it'll be a draw from a normal distribution. Our norm will take a single draw where the mean of this distribution is the current value of mu, and the standard deviation is the candidate standard deviation. So this is where we'll draw the candidate. The second step in the Metropolis-Hastings algorithm is to compute the acceptance ratio. In our case, the candidate generating distribution is normal, which is symmetric. So these Q distributions in the Metropolis-Hastings ratio will cancel each other out. So the ratio will actually be G evaluated at the candidate divided by G evaluated at the old value. For numerical stability, we'll calculate this on the log scale. So the first thing we want to do is get the log of G evaluated at the candidate. So LG using our candidate that we just drew. To do this, we'll call our LG function again, where mu is now going to be equal to mu candidate. Again, n will equal n, and y bar will be y bar. We now have the log of G evaluated for the candidate draw. We now need it for the log of G evaluated at the last value. But we already have that. It's LG now. So we are now ready to calculate alpha, the acceptance ratio. Of course, we've done this on the log scale, so let's call this log alpha. And it equals LG evaluated at the candidate minus LG, the current LG, LG now. This is the log of alpha, so to get the real alpha, we just need to exponentiate it. Now that we've calculated alpha, we're ready to move on to step C here. So the first thing we're going to do is draw from the uniform distribution. We'll save it in the variable called u. Our unif1. That takes a draw from the uniform distribution between 0 and 1. Then, if u is less than alpha, that gives us an event that happens with probability alpha. Then we're going to do the following. With probability alpha, we're going to accept the candidate. In other words, mu now, the current iteration of mu, will become mu candidate. We also want to keep track of how often we are accepting the candidates. So let's add 1 to the acceptance count. Since we accepted the candidate, we need to update LG now to be LG evaluated at the candidate. Finally, within this loop, we need to collect to save our results. So let's put this in mu out. This is the vector that we initialized at the beginning of the function. So the ith entry of mu out is going to get mu now. Finally, we need to determine what our function is going to return at the end. What we need are our samples from the Metropolis-Hastings sampler, so we need to output mu out, and it would be helpful also to output our final acceptance count. We can have a function return multiple outputs through a list. So the last line of the function will include a list where we're going to output two things. Mu, which will be our vector, mu.out. That contains all of our samples from the Metropolis-Hastings sampler. And then we'll return the accept rate. So it'll be our acceptance count, ACCPT. That counts how many acceptances we had, divided by the number of iterations. That gives us the acceptance rate. This completes our function for the Metropolis Hastings sampler. Now we're ready to set up the problem. I have copied here a vector of the data values, and we've called it y. So what we need is to calculate y bar, which is the sample mean of y. We also need to run y so that the values are saved in our R session. And now we can run this line to calculate y bar, the mean of y. We also need n, which is the length of y. We'll run that, and just to check it, it is 10. And as part of our analysis, let's just look at a histogram of these data points. So we'll do a histogram of y, where again we want the frequency to be false, so that we're looking, instead of counts, we're looking at probabilities. And we want the x-axis to be between the values of -1 and 3, just so that we have enough view on both sides of the data. So let's run this histogram. Here's what the data look like. Let's also add the individual data points. We can do that with the points function, where we add the y vector. And we want, on the y-axis, we want these to appear on 0, so that they appear along the x-axis. So we're going to repeat 0 n times for our y coordinates. And we'll actually just run this. So that adds the actual data points, so we can see where they are. We can also add y bar, the sample mean, to see where that's located. Well, again, we'll use points, and this time y bar and 0. And to distinguish it from the data points, let's use PCH19. That creates a filled circle. So when I run this, it adds y bar, the sample mean, so we can see where the sample mean of our data are. Let's add the plot of our prior distribution for the mean to see how it compares with our data. We can do that with the curve function, where we're going to use the density of a t distribution, dt, for generic x variable, which we haven't defined. It's just the x-axis in the plot. And our t distribution has degree of freedom 1. By default, it already has location 0 and scale 1. To distinguish it from the histogram, let's give it a different line type, LTY equals 2. That will cause it to be a dashed line. And then, of course, add equals true, so that it adds this plot on top of the previous one. Let's run this curve. Here's our prior distribution for mu. As you can see, there's a little bit of a discrepancy between our prior for mu and what the data says mu should be. The prior has most of its probability mass in this region here, near 0. However, the data suggest that the mean is up here near 1. We expect that the posterior distribution for mu will have a mean as a compromise, somewhere between 0 and 1. We're now ready to run the sampler that we've just coded up. I've already entered the LG function into the R session, but we still need to load the Metropolis Hastings function. So I'm going to press Command Return to enter that function into the console. And now we have the data, we have y bar, and we have n. So let's move down here and start sampling. We'll collect our posterior samples in a variable that we'll call post, referring to posterior. It will be the result of calling our Metropolis hastings function, where we need to give it these 6 arguments: n, which we've defined, y bar, which is the sample mean of the data, n iter, which is the number of iterations. We've decided we want to do 1,000 iterations of our sampler. There's also a shorthand for this, which we can do 1e3. That's 10 to the 3rd power. Let's initialize mu at 0. We'll use candidate generating standard deviation equal to 3. Before we start sampling, let's set the random generator seed so that we can reproduce our results if we need to. So first thing we'll run is set.seed, and then we'll run our Metropolis hastings function using the parameters that we gave it. If we've saved some object and we're curious what's inside of it, we can use the str function in R, and put the object in there to find out what's in the object. So the structure of post is a list, just like we had our function output. It's a list containing 1,000 iterations of our mu variable, and it tells us our acceptance rate, which in our case for this run was about 12%. To help us explore posterior distributions, we're going to use the coda package in R. So let's load the coda package. This R session does not currently have coda installed. So first we're going to need to install the package. Install packages, and we'll install coda. So we'll run that line. When it installs a package, it asks us which cran mirror we want to download the package from. We're in California, so let's select California here. Great. So hopefully now library coda will work for us. Let's run this line. Perfect, it worked. Now that we've loaded the coda library, we can use the trace plot function, which I'll describe in just a moment. The trace plot function requires that we pass it an MCMC object. Right now, post is only a list, so let's change post into an MCMC object by typing as.mcmc, that's also a function, post. Specifically, we want to look at the trace plot of mu. So this is the mu vector in the post, our list of post right here. Let's run this line and see what happens. Here's our trace plot. So this is called a trace plot because it shows the history of our Markov chain, and it gives us some basic feedback about whether the chain has reached the stationary distribution. It appears that our proposal step size, in this case, was a little bit too large because we had an acceptance rate below 23%. It was more like 12%, I think, in our case. Yeah, here it is. It was 12%. You can see that in the trace plot. As the sampler was moving along, for example, in these early iterations, mu got stuck at a single value for quite a long time. It happened again over here. So in other words, our Markov chain is not moving around as much as we would like it to. We want to increase the acceptance rate. To change the acceptance rate, we need to rerun the sampler with a different candidate standard deviation. Usually, if we increase the variability in the distribution that creates the candidates, that will decrease the acceptance rate. We want to increase the acceptance rate, so we want a smaller standard deviation. Let's reduce it to, say, 0.05. Let's make it really small and see what happens. So if we run the Metropolis hastings function and reassign it to post, it'll overwrite our old samples, but that's okay. We still want to initialize mu at 0, and we'll still run it for 1,000 iterations. Let's run this line of code, and let's look at the structure of post again. So we have 1,000 samples, but this time the acceptance rate was 94, almost 95%. If we look at the trace plot for this chain, we see the opposite behavior. Notice that the step sizes, because the candidate generating function had a small variance, the step sizes are small, and so the chain wanders. Here the step sizes are too small. It's going to take the chain a long time to explore the posterior distribution. We can see that because the acceptance rate for our random walk is too high. The first candidate standard deviation we tried was 3. We overcorrected by going down to 0.05. So let's try something in between. Let's try 0.9. That's a compromise from the two values. Let's run this and now look at our acceptance rate. Okay, our acceptance rate is down to 0.38. That's probably good. We usually are looking for an acceptance rate between 0.23 and 0.5 when we're working with a random walk Metropolis hastings algorithm. So let's look at the trace plot for this. I'll run the trace plot command. This trace plot looks much better. It's exploring the posterior distribution. It gets stuck every once in a while, but that's okay. It looks pretty good. Now let's see what happens if we change our initial value to something way far away from the truth. So let's try an initial value of mu equal to 30. If we run that and look at the acceptance, we still get 0.38. That's good. And let's look at our trace plot. We'll run this line. Here we can see the effect of using a crazy initial value. We started mu way up here at 30, and it took maybe, almost 100 iterations to find the stationary distribution. It was wandering for quite a long time, and then once it hit the stationary distribution, it bounced around inside the stationary distribution. But it looks like after 100 iterations, we've succeeded. So if we discard or throw away the first 100 or so values, it looks like the rest of the samples do come from the stationary distribution, which is the posterior distribution we wanted. Now let's plot the posterior density against the prior to see how the data updated our belief about mu. The first thing we'll do is get rid of those first 200 iterations while the chain was still exploring. We're going to call this a new object in our list called post, and it'll be mu underscore keep. It'll be the iterations of mu that we want to keep. It'll come from the mu object in our list for post, where we get rid of, we're going to discard iterations 1 through, let's just get rid of the first 100. Okay. So this says we're going to index the mu vector by taking away the first 100 elements. Let's run that line. It saves so that we can look at the structure of post. we now have mu dot keep, or mu underscore keep. So let's plot a density estimate. So it's plot density. A density estimate of our posterior draws for mu. Post, $mu, keep. Let's use the same limits to our x-axis that we did before. So that would be x lim going from -1 to 3. And let's take a look at this plot. Let's run this. So this is a density estimate of the posterior distribution based on the 10 data points. Again, let's compare this to the data and the prior. First, let's draw the prior. Again, we can reuse our old code up here where we drew the prior for the density of a t-distribution with 1 degree of freedom, where add equals true so that it'll write it over the same plot. Let's run this line. So here is our prior distribution for mu, and then based on the data, here's our posterior distribution for mu. Let's also add the sample mean. So this is where the data said mu should be. This is where the prior said mu should be. The posterior distribution does look like a compromise between the prior distribution and the data. These results we've obtained are encouraging, but they are preliminary. We still need to investigate a little more formally whether our Markov chain has actually converged to the stationary distribution, and we're going to explore this in a future lesson. Creating posterior samples using a Metropolis Hastings algorithm can be time-consuming and require a lot of fine-tuning, like we did with our candidate standard deviation here. The good news is that we can rely on software to do most of the work for us. So in the next couple of videos, we're going to introduce a program that will make posterior sampling easy. There are several software packages available that will handle the details of MCMC for us. We've provided a supplementary document to this lesson which gives an outline, a brief outline of the different options available to you. The package we will use in this course is Jags, which stands for Just Another Gibbs Sampler, written by Martin Plummer. The program is free, and it runs on Mac OS, Windows, and Linux. Better yet, the program can be run using R from the rjags or r2jags packages. In Jags, we can specify models and run MCMC samplers with just a few lines of code. Jags does the rest for us, so we can focus more on the statistical modeling aspect and less on the implementation. It makes powerful Bayesian machinery available to us so we can fit a wide variety of statistical models relatively easily. The starting place for Jags users is this website, mcmcjags.sourceforge.net. At this site, you can find news about the features of the latest release of Jags, links to program documentation, as well as instructions for installation. The documentation for Jags is particularly important to us. It is available under the Files page right here. We'll open that up. Under the Manuals folder. We're going to use the latest version of Jags, so we'll look at 4 here. And we'll download the Jags user manual. We've already downloaded it, so let's take a look at the Jags user manual. The user manual has a lot of useful information, including how to run models, different modules available, the functions available to us in the Jags language, as well as probability distributions. Chapters 5 and 6 will be especially important to us as we model. Let's take a look at Chapter 6 in distributions. Page 29. This chapter documents all of the statistical probability distributions that we can use in Jags. We will refer back to this often because it shows us the functions that correspond with the different distributions and how they're parameterized. For example, notice that in Jags, the normal distribution is parameterized differently than it is in R. We need to keep that in mind while we're modeling. Let's go back to the web page and start from the beginning again. Under the Files page, again down here, we'll find the Jags folder. This is where we can download and install the latest version of Jags, in this case 4. From here you can select your operating system and follow the directions to download and install Jags. Once Jags is installed, we can immediately run it from R using the rjags package. The next segment will show how this is done. There are 4 steps to implementing a model in Jags through R. The first step is to specify the model. The next step is to set up the model. The third step is to run the MCMC sampler. And finally, the 4th step is post-processing. We'll demonstrate all 4 of these here. Let's do this using our running example, where we have data representing the percentage change in total personnel from last year to this year in 10 companies. In this model, we used a normal likelihood with a known fixed variance and a t-distribution for the prior on the unknown mean. The first step is to specify the model. If we haven't done it already, we first need to load the rjags package. This requires that rjags has previously been installed, which you can do with this line of code up here. Once the library is loaded, we specify the hierarchical structure of the model. Let's remind ourselves what this model looks like. We have a normal likelihood for the data, which are independent, with mean mu and variance 1. Our prior on the mean is a t-distribution with location 0, scale 1, and degrees of freedom 1. We can write out the hierarchical form of the model into Jags through a variable that we're going to call mod string. This will be a model where we use curly braces to encapsulate the model itself. And for the likelihood portion, we're going to use a for loop. For I in 1 to n, suppose n is the length of our data. Inside this loop, we'll say y I, the ith observation, follows a normal distribution. The syntax for that in Jags is d norm, just like it is in R, with mean mu, and precision 1 divided by the variance. This is how the normal distribution differs between Jags and R. In Jags, this is the precision, which is the reciprocal of the variance. That completes the likelihood, so now let's put in the prior for mu. Mu is going to follow a t-distribution. The density for that in Jags is dt. And just to be careful, let's check the user manual to see how the t-distribution is parameterized in Jags. The first argument it accepts is mu, which is the location parameter. The second parameter it accepts is tau. Here, if you were going to look at the t-distribution in R, you would notice this parameter is down here near k. That would be the scale parameter. This is 1 over the scale parameter, or the inverse scale parameter. Finally, k refers to the degrees of freedom in the t-distribution. So the three parameters we need are location 0, inverse scale 1, and degrees of freedom 1. The degrees of freedom is an integer, so I'll leave it as an integer. Remember that the only parameter we didn't know that we're trying to estimate is mu. We are assuming we know sigma squared and it is fixed. So let's tell Jags the value of sigma squared. This completes our specification of the model. Jags requires that we write models as strings, as we've indicated here, so we need to put this model inside of quotation marks. This is what a model looks like in Jags. The second step is to set up the model. First, we'll enter the data, and we'll save n as the length of y. Before Jags can run this model, we need to tell it what the data are, what the parameters are, and provide initial values for those parameters. The data that we'll pass to Jags we'll call a variable data Jags. It needs to be a list where we name the variables the same name that we give them in the model specification. So y is our data, y, and n is the n we just saved here. We also need to tell Jags what the parameters are. We'll save that in a variable called params. Our only parameter in this case is mu. But if we wanted to add other parameters, like the variance, it could be placed in a vector like this. But we're only using mu. To give Jags initial values, we need to write a function. Let's call that function inits. The function doesn't take any arguments, but it creates a variable called inits and places that into a list where we create a value for each parameter in the model. Our only parameter is mu. We put it in quotation marks and we provide an initial value. Let's just use 0 as we did before. There are actually multiple ways to specify initial values in Jags. They can be explicitly set at values you tell it, like we've done here, or they could be random. We could replace this number here with a function call to generate a random initial value for mu. Finally, we're going to compile the model itself using the jags.model function from the rjags package. The first argument for jags.model is the model string. This is usually placed in a separate text file, but because we're going to enter that directly into the R console, instead we're going to create a text connection and give it our model string. The second argument is the data, which we've called data_jags. And next, it'll take the initial values. Before we run this, let's set the random number generator seed so that we can reproduce our results. Let's use 50 there. We haven't entered anything into the R console yet, so let's go ahead and do that. First, the model string. Then we'll set the seed, and we'll enter all the model setup pieces. Finally, let's assign the model. Running Jags.model will initialize the model, which can sometimes take a few moments. We're now ready to take our next step, which is to run the MCMC sampler. There are two very important functions for this step. The first function is the update function, where we give it the model, and we tell it how many iterations we want it to update, let's say 500. This function, when we run it, runs the MCMC sampler for 500 iterations without saving the samples anywhere. This gives the Markov chain some time to find the stationary distribution. The next function is the coda samples function. This is where we'll simulate a Markov chain and keep our simulations. Coda.samples function, where we give it the model, which is the mod that we initialized right here. We need to tell it the variable names, which in our case we named params. It was this variable up here. We need to tell it how many MCMC iterations to run. Let's do 1,000. We will not provide initial values for this run because this chain has already been running for 500 iterations. This will simply continue where the chain left off when we last ran it. Let's run this sampler for the 1,000 iterations. The fourth and final step is post-processing. We won't get into many details here, but we will do lots of post-processing later in the course. This is where we evaluate the Markov chains we've simulated to determine if they're suitable for inference, and then we can use them for inference. The coda package will be especially useful to us here. Let's load the coda package. And let's first look at a trace plot from our model. Let's run the plot there. And it gives us both a trace plot and a density estimate for mu. So this is our posterior distribution for mu, similar to the one we obtained earlier using our random walk Metropolis hastings sampler. We can also look at a summary from our model. The summary tells us which iterations of the chain we're using and gives us some other statistics related to our Markov chain. It also gives us some information about the parameters we've been estimating, that we've been simulating with the chain. For example, our estimated posterior mean for mu is 0.91, with a standard deviation of 0.31. We will discuss post-processing further, including convergence diagnostics, in a coming lesson. So far, we've demonstrated MCMC for just one single parameter. What happens if we seek the posterior distribution of multiple parameters, and that posterior distribution doesn't have a standard form? One option is to perform Metropolis hastings by sampling candidates for all the parameters at once and accepting or rejecting all of those candidates together. While this is possible, it can get complicated. Another, simpler option is to sample the parameters one at a time. As a simple example, suppose we have a joint posterior distribution for two parameters, theta and phi, given our data y. And let's suppose we only know this up to proportionality. We're missing the normalizing constant. What we've calculated is the function g of theta and phi. If we knew the value of phi, then we could just draw a candidate for theta and use this g function to compute our Metropolis hastings ratio and possibly accept the candidate. Before moving on to the next iteration, if we don't know the value of phi, then we could perform a similar update for it. We would draw a candidate for phi using some proposal distribution, and again use this g function where we plug in the value of theta to compute our Metropolis-Hastings ratio. We pretend we know the value of theta by substituting in its current value or current iteration from the Markov chain. Once we've drawn for both theta and phi, that completes one iteration, and we begin the next iteration by drawing a new theta. In other words, we're just going back and forth, updating the parameters one at a time, plugging in the current value of the other parameter into the g function. This idea of one-at-a-time updates is used in what we call Gibbs sampling. It also produces a stationary Markov chain whose stationary distribution is the target or posterior distribution. If you recall, this is the namesake of Jags, which is just another Gibbs sampler. Before describing the full Gibbs sampling algorithm, there's one more thing we can do. Again, using the chain rule of probability, we know that the joint posterior distribution of theta and phi can be factored. First into the marginal posterior distribution of phi times the full conditional distribution of theta given phi and the data. Notice that the only difference between this full joint posterior distribution and this full conditional distribution here is multiplication by a factor that does not involve theta at all. Since this g function, when viewed as a function of theta, is proportional to both the full posterior and this full conditional for theta, we might as well have replaced g with this distribution when we performed the update for theta. This distribution of theta given everything else is called the full conditional distribution for theta. Why would we use it instead of g? In some cases, the full conditional distribution is a standard distribution that we know how to sample. If that happens, we no longer need to draw a candidate and decide whether to accept it. In fact, if we treat the full conditional distribution as a candidate proposal distribution, the resulting Metropolis-Hastings acceptance probability becomes exactly 1. Gibbs samplers require a little bit more work up front because you need to find the full conditional distribution for each parameter. The good news is that all full conditional distributions have the same starting point, the full posterior distribution. So using the example above, we have that the full conditional distribution for theta given phi and y will be proportional to the full joint posterior distribution of theta and phi given y, which is also proportional to this g function up above. Here we would simply treat phi as a known constant number. Likewise, the other full conditional will be phi given theta and y, which again will be proportional to the full joint posterior distribution, or this g function here. We always start with the full posterior distribution. Thus, the process of finding full conditional distributions is the same as finding the posterior distribution of each parameter and pretending that all the other parameters are known constants. The idea of Gibbs sampling is that we can update multiple parameters by sampling just one parameter at a time and cycling through all parameters and then repeating. To perform the update for one particular parameter, we substitute in the current values of all the other parameters. So let's call this our Gibbs sampling algorithm. Here's the algorithm. Let's suppose we have the joint posterior distribution for two parameters, phi and theta, like we do here. if we can find the distribution for each of the parameters given all the other parameters and data, the full conditional distributions, then we'll take turns sampling the distributions. The first step in the Gibbs sampler will be just like the first step in Metropolis Hastings, where we initialize. So we'll start with a draw for theta naught and phi naught. The next step is to iterate. So for I in 1 up to m, we're going to repeat the following. The first thing we'll do is using the previous iteration's draw for phi, so phi I minus 1, we're going to draw theta I from its full conditional by plugging in the old value of phi. Then, once we've completed this draw for this draw for theta I, we're going to use it. So using theta I, the most recent draw for theta, we're going to complete a draw for phi I, using its full conditional distribution. And we're going to condition on theta I. Together, these two steps complete one cycle of the Gibbs sampler, and they produce a pair. We'll get a theta I, phi I pair. That completes one iteration of the MCMC sampler. If there are more than 2 parameters, we can handle that also. One Gibbs cycle would include an update for each of the parameters. In the following segments, we're going to provide a concrete example of finding full conditional distributions and constructing a Gibbs sampler. Let's return to the example at the end of lesson 2 where we have a normal likelihood with unknown mean and unknown variance. To remind ourselves, let's write the model. The response for individual I, given mu and sigma squared, is independent and identically distributed normal with mean mu and variance sigma squared for observations I being 1 up to n. We're also going to assume independent priors. A normal prior for mu with these hyperparameters and an inverse gamma prior for sigma squared with these hyperparameters. In this case, we chose a normal prior for mu because when sigma squared is a known constant, the normal distribution is the conjugate prior for mu. Likewise, in the case where mu is known, the inverse gamma is a conjugate prior for sigma squared. This will give us convenient full conditional distributions in a Gibbs sampler. Let's first work out the form of the full posterior distribution. When we begin analyzing data, the Jags software will complete this step for us. However, I believe it's extremely valuable for us to see and understand how this works. The joint posterior distribution for mu and sigma squared, given all the data, is going to be proportional to the joint distribution of everything, which starts with our likelihood, the joint distribution of the data, given the parameters, times those respective priors. So let's write out what these densities look like. First, the likelihood. Because we assumed that they're independent, we're going to write their densities as a product of normal densities for each individual y, given those two parameters. Then we have the prior for mu, which is a normal density for mu, given those hyperparameters. And finally, a density for sigma squared, this inverse gamma, given its hyperparameters here. I'm going to keep writing these steps, but so that you don't have to write and watch the math happen in real time, we're going to skip forward. Okay, I've now done a little bit of math to complete these next two lines. All I did was replace these densities for these distributions with their actual densities. So we have the likelihood piece right here, the normal distribution for mu right here, and the inverse gamma distribution for sigma squared right here. We could also include an indicator function that sigma squared has to be greater than 0, but we know that's true. To get from this line to this line, we remember that we're only working up to proportionality anyway, so we don't need the multiplying constants that don't involve mu or sigma squared here. So I was able to remove these 1 over 2 pi pieces right here. Those are just a multiplicative constant, but I did have to keep the sigma squareds because this is a function of sigma squared. I brought in this exponential piece that contains both mu and sigma squared, bringing the product inside the exponent. Then in the normal prior right here, this piece doesn't contain any mu or sigma squared, so that can drop out when we make it proportional. And this normalizing constant for the inverse gamma distribution also does not contain a sigma squared or a mu, so it can be dropped as well. So this is the function we're going to work with. I've now moved this distribution that we just derived, the joint distribution of mu and sigma squared up to proportionality, up here to the top. From here, it's easy to continue on to find the two full conditional distributions that we need. The first one we'll look at is mu, assuming sigma squared is a known constant, in which case it becomes a constant and is absorbed into the normalizing constant. So we're going to work on the full conditional distribution of mu given sigma squared, pretending it's a constant number, and all of the data. This will be proportional to our full joint posterior distribution of mu and sigma squared given all the data, like this. So we need to take the pieces from this full joint posterior distribution that involve mu only, because now sigma squared is a constant. So we can drop this piece and keep this piece in the likelihood. This piece also has a mu, so we need to keep it. And none of the rest of these contain mu. They're all multiplied by this distribution, so we don't need to keep any of these pieces here. This is all we need. Again, I'm going to skip forward so we don't have to watch all of the math in real time. I've now completed these next two steps where we did a little bit more algebra. In this step, we combined the two exponents into one, and in the final step, we recognized that this piece right here is proportional to a normal density with this mean and this variance. There are a lot of intermediate calculations required right here, but they're all provided in the supplementary material from the previous course. This is just the conjugate update for a normal mean when the variance is known. So, given the data and sigma squared, mu follows this normal distribution. Now let's look at sigma squared, and we'll assume that mu is known. So we're going to look at the full conditional distribution of sigma squared given mu and all of the data. Again, that is proportional to our full joint posterior So we're going to take the pieces from this expression that involve sigma squared. And now mu is thought of as being a constant. So we're going to keep this first piece, of course. And this one as well, it contains a sigma squared. This piece right here contains the hyperparameter for mu, but no actual sigma squared parameter is observed there. So we skip that one. That gets absorbed into the normalizing constant. And we keep this one, which involves sigma squared. And the last piece. Again, I'll do a couple more steps on this piece right here. Let's examine these last two steps. Here I combined these two sigma squared expressions right here, since they were being multiplied by each other. And I combined the two exponential pieces right here. If you look at this expression right here, it turns out this is, except for a normalizing constant, the density of an inverse gamma distribution. So this, in fact, is proportional to an inverse gamma density for sigma squared with an updated shape parameter and an updated scale parameter. These two distributions provide the basis of a Gibbs sampler to simulate from a Markov chain whose stationary distribution is the full posterior distribution for mu and sigma squared. We simply alternate draws between these two parameters using the most recent draw of one parameter to update the other. We're now going to do this in R in the next segment. To implement the Gibbs sampler we have just described, let's return to our running example where the data are the percent change in total personnel from last year to this year for 10 companies. We're still going to use the normal likelihood. Up until now, we have fixed the variance, the variance of the growth between companies, sigma squared, at 1. Now we're going to relax that assumption. We will not assume we know sigma squared. We're going to estimate it like we do for mu, the mean. Instead of a t prior from earlier, we're going to use the conditionally conjugate priors, normal for the mean mu and inverse gamma for the variance, sigma squared. The first step is going to be to write functions in R that simulate from the full conditional distributions we derived in the previous segment. Here is the full conditional update for the mean mu, and here is the full conditional update for the variance sigma squared. We need to write functions to simulate from these in R. We'll call the first one update mu, and the second one we'll call update sigma squared. I've now written these two functions in R. The first one, update mu, needs arguments n, y bar, the value of the current sigma squared, and then the prior hyperparameters for mu. I first calculate this variance, and then I calculate this mean, which uses this variance in the denominator, and finally take a draw from a normal distribution with the correct mean and variance. In the update for sigma squared, we need n, the full data vector, all of the y values, the current value of mu, and the hyperparameters for the prior on sigma squared. In the first 3 lines, we perform the calculations described by this formula, and in the 4th line, we draw from a gamma distribution. Because R does not create draws from the inverse gamma distribution, we have to do it manually. This is done by first drawing from a gamma distribution and then taking the reciprocal. The output of this function will be the reciprocal of the drawn gamma, which will be a draw from an inverse gamma distribution. Now that we have functions that draw from these full conditionals, we are ready to write a function that performs Gibbs sampling. Let's call that function Gibbs. We'll take 4 arguments, the data vector y, the number of iterations we want to sample for, initial values for the parameters, and a list containing the prior hyperparameters. We'll call that prior. Since y bar and n get used frequently, let's calculate those at the beginning of the function. This function is going to output 2 variables, a vector for the draws of mu, let's call that mu out. It'll be a vector that has length n iter. And we'll also have sigma squared out, which will also be a vector with n iter entries. The Gibbs sampler will update mu and sigma squared by trading off, sampling back and forth given the current value of the other parameter. We need to initialize one of the variables to get this started. Let's start with mu. That will be from the initial value of mu. That comes from the argument to the function. Now we're ready to create the Gibbs sampler. This will be a loop. Since we started with the current draw for mu, let's update sigma squared first in this loop. To update it, we need to take a draw from the full conditional distribution. That is, we need to evaluate this function that we created here. The arguments are the data length, the data themselves, the current value of mu now, which we saved up here, and then the hyperparameters. These hyperparameters are saved in our object called prior. It's going to be a list. So we're going to access the new sub-zero element or object in the prior with the $sign. Prior, $, new sub-zero. The same goes for our other hyperparameter, beta sub-zero, which will also come from our list of prior hyperparameters. Now that we've updated sigma squared, we're going to go back and update mu again using the draw from the full conditional that we wrote up here. We will use sigma squared now as the value for sigma squared in this update. And again, the prior hyperparameters will come from the prior list. We're still in iteration I. We've now updated both sigma squared and mu, so let's save them. sigma squared out, where we fill in the ith iteration, or the ith element of this vector, it will be sigma squared now. The same goes for mu. The ith iteration, or ith element of mu, will get mu now. The loop will now go through this sequence repeatedly, where we take a draw for sigma squared, then given the value of sigma squared, we take a draw for mu, and then given the value of mu, we take a draw for sigma squared. We collect the results and repeat this process for n iterations, and finally we'll need to output our results. We can combine two vectors into a matrix using the cbind function in R. We'll give it mu out and call it mu, and sigma squared will be our sig squared out. Cbind refers to column bind, so we're going to have a matrix of two columns with n iter rows. This completes our Gibbs function. Let's read all of these functions into our R session. Now that we have functions to perform Gibbs sampling, we're ready to set up the problem. I've begun a new script where I've collected the data, created a variable y bar which calculates the sample mean of the data, as well as n, the sample size. The next step will be to create the prior. The Gibbs sampling function accepts the prior as a list, so let's create it as a list. Now, to help us remember, here is the model we're fitting. The prior for mu is normal with these hyperparameters, and the prior for sigma squared is inverse gamma with these hyperparameters. Let's start with the prior for mu. First, we need to give it mu sub 0, the prior mean on mu. Let's say this is 0. We also need a variance for this prior, sigma squared sub 0, which we can interpret as our prior confidence in this initial prior mean. We're going to set it to 1 so that this prior is similar to the t prior that we used in an earlier example. We also need to create the prior hyperparameters for sigma squared, nu sub 0, and beta sub 0. If we choose these hyperparameters carefully, they are interpretable as a prior guess for sigma squared, as well as a prior effective sample size to go with that guess. The prior effective sample size, which we'll call n sub 0, is 2 times this nu sub 0 parameter. So in other words, the new parameter will be the prior sample size divided by 2. We're also going to create an initial guess for sigma squared. Let's call it S2 sub 0. The relationship between beta sub 0 and these two numbers is the following. It is the prior sample size times the prior guess divided by 2. This particular parameterization of the inverse gamma distribution is called the scaled inverse chi-square distribution, where the two parameters are n sub 0 and S2 sub 0. We are now free to enter our prior effective sample size. Let's say it's 2 in this case. In other words, there are 10 data points, and there are 2 effective data points in the prior. And we'll say our prior guess for sigma squared will be 1. Once we specify these two numbers, the parameters for our inverse gamma distribution right here are automatically determined. Let's read these lines into our R session. And before we run our Gibbs sampler, let's take a look at the histogram of the data with our prior for mu, like we did in the earlier example with a t prior. This should look familiar. It's very similar to the t prior we had before, but now this prior for mu is a normal distribution, centered at 0. If you'll recall, the data mean was about 1. So we expect our posterior mean to be somewhere between 0 and 1. Let's go ahead and run this Gibbs sampler. Before we start, we'll always set the random number generator seed. We'll use 53 and run that line. And we need to create the variables that we're going to pass to our Gibbs function. Those are the init. So we'll create init as a list, and init $mu, our initial value for mu, let's just start it out at 0 and run that line. I think we have all of the arguments ready for the Gibbs function now. So we're going to call our Gibbs function. We're just going to copy and paste it so we can remember the arguments. So we'll call Gibbs. And for the y, we'll give it the data y. We have to select the number of iterations. Let's do 1,000 like we've been doing before. We'll give it the initial values saved in our list called init. And we'll give it the prior hyperparameters saved in our list called prior. Now let's run our Gibbs sampler by running the Gibbs function. Press Command Return. That ran the sampler for 1,000 iterations, except we forgot to save it in an object. So let's run it again and save it as post. We'll set the seed again so that we get the same answer, and save the object as post. There we go. Let's look at the head of post, which will show us the first several iterations of this Gibbs sampler. We run that line. We can see the first iteration, this was the value of mu and this was the value of sigma squared, and so on down. We can also look at the tail of post. Those were the last few iterations. To analyze this posterior output, let's use the Coda package. We need to load the Coda library. And we can plot the posterior distributions as an MCMC object. Let's run that line. We're given a trace plot for mu, a density estimate of the posterior distribution that comes from our Markov chain, a trace plot for sigma squared, and a density estimate for that posterior. Additionally, let's look at a summary as.mcmc for our post. We run that line, and we get the summary for our Markov chain. We can see here we had two parameters that we were sampling in the chain, mu, which has a posterior mean about 0.90. That's similar to our result from earlier. And the posterior mean for sigma squared is about 0.92 or 0.93. As we had with the Metropolis Hastings example, these chains appear to have converged. In the next lesson, we'll show you how to make that determination. In the last two lessons, we've demonstrated ways you can simulate a Markov chain whose stationary distribution is the target distribution. Usually our target distribution is the posterior distribution for the parameters we're trying to estimate. Before using simulated chains to obtain Monte Carlo estimates, we should first ask ourselves the following question. Has our simulated Markov chain converged to its stationary distribution yet? Unfortunately, this is a difficult question to answer, but we can do several things to investigate. Throughout this lesson, we're going to focus less on the code and more on the plots. Our first visual tool for assessing chains, and one that you've already seen in previous examples, is the trace plot. Here's an example of a trace plot. A trace plot shows the history of a parameter value across iterations of the chain. Here we have iterations across the x-axis. It shows you precisely where the chain has been exploring. First, let's talk about what a chain should look like. Here is an example of a chain that has most likely converged. If the chain is stationary, it should not be showing any long-term trends. The average value for the chain should be roughly flat, and it should not be wandering, as we'll show in the next example. It appears that this trace plot is tracing the same distribution. It looks like it's approximately a normal distribution across iterations. Let's look at an example of a chain that is wandering. In this example, the step size of the random walk sampler is too small, and so it takes many iterations for the chain to traverse across the distribution. We're seeing long-term trends here. For example, if we were going to estimate the mean using only the first 200 iterations, we would get a very different answer than if we were to estimate the mean using iterations 600 through 800. If this is the case, you will need to run the chain for many, many more iterations, as we see here. It turns out this is the exact same chain that we were just looking at, except it's on a much larger time scale. Instead of a few hundred iterations, we are looking at about 100,000 iterations. On this larger time scale, it appears that we have converged. One major difference between the two chains we've looked at is the level of autocorrelation in each. Autocorrelation is a number between -1 and +1, which measures how linearly dependent the current value of the chain is to past values, called lags. We will provide more details about autocorrelation in a supplementary document. We can see and inspect autocorrelation using the autocorrelation plot in the CODA package. So let's first load the CODA package. And to look at the autocorrelation plot, we're going to use the autocor.plot function. Let's look first at the autocorrelation in our good example that had converged. This diagnostic calculates the autocorrelation against different lags. For example, at the 0th lag, a value in the chain has perfect autocorrelation with itself, a correlation of 1. With the first lag, a value of the chain has a correlation a little higher than 0.5. And as we go further along the chain, the values become less correlated. We can also look at the values of the autocorrelation themselves with autocor.diag. We run that, and we look at those values. So associated with lag 1, we have an autocorrelation of about 0.61. Now let's look at the autocorrelation in the example where the chain had too small of a step size, and run that. Here we can see some pretty extreme autocorrelation persisting for many lags. Even out past 30 lags, we have autocorrelation which appears to be higher than 0.5. That is, a value in the chain has a higher than 0.5 correlation with a value 30 steps behind it. Autocorrelation is important because it tells us how much information is available in the Markov chain. Sampling 1,000 iterations from a highly correlated Markov chain yields less information about the stationary distribution than we would obtain from 1,000 samples independently drawn from the stationary distribution. To illustrate this phenomenon, let's pretend you want to find the most popular movie in your town. Would you get more information if you A, randomly sampled 20 people from the town, or B, if you conveniently asked 20 of your friends? Chances are that your 20 friends' movie preferences are correlated because they might have similar interests. If you conducted such a convenient sampling scheme, you would probably have to sample many more opinions to get the same quality of information available from a truly random sample of 20 people in the town. Autocorrelation is a major component in calculating Monte Carlo effective sample size in your chain. The Monte Carlo effective sample size is how many independent samples from the stationary distribution you would have to draw to have equivalent information in your Markov chain. Essentially, it is the sample size that we chose for our Monte Carlo estimation. Let's look again at this chain that has really high autocorrelation. First, let's look at the structure of the object. We had a very high candidate acceptance rate because it took many steps to go across the distribution. And we had 100,000 samples. Now let's calculate the effective sample size of this chain. The effective sample size function is in the CODA package, and the function is called effective size. We need to give it an MCMC object. And this is a pretty dramatic difference. Although we simulated 100,000 samples, the effective sample size of this chain is only 373, approximately. Let's look at a long-range autocorrelation plot. Of the chain with 100,000 samples at a really long lag. Let's go out to 500 lags. This plot shows us that you have to go all the way out to about 400 lags, or even further than 400 lags, before autocorrelation drops to 0. In other words, values in the chain have to be about 400 steps apart from each other before they're no longer autocorrelated with each other. What would happen then if we kept only 1 out of every 400 iterations? Let's do this. We'll create a thin interval of 400, run that, and we're going to create an index. It'll be a sequence starting at 400, going to 100,000, and we'll keep every 400th number. Let's take a look at what this thin index gave us. This gives us the address of each sample that we're going to keep. To remind ourselves, let's create a trace plot of the original chain. And we're actually going to want to do two plots in the same plot here. So we can control the plotting parameters in R using par. And if we want to have multiple plots per frame, we can use the mfrow command, where the first number we give it is the number of rows of plots. We want 2 rows of plots. And the second number is the number of columns of plots. We'll want 1. So it creates a new window for us where we're going to fill in the trace plots. So the first is the trace plot of the original chain with all 100,000 iterations. Now I'm going to copy this line, paste it, and we're only going to look at the samples that we kept after thinning. So we'll index this by the thinning index and run that trace plot. Next, we'll calculate the autocorrelation for this thinned out chain. We want the autocor plot. Look at that. The autocorrelation has essentially disappeared if we've thinned the chain out to every 400 iterations. What's the effective sample size? We'll give it the thinned chain and calculate the effective sample size. It's 250. How many actual samples are there? We can look at the length of our thinning index sequence, 250. So the effective sample size in this chain is the same as the actual sample size because the values are approximately uncorrelated. To remind ourselves, let's look at the effective sample size of the original chain that had 100,000 iterations. It was about 373, fairly close to the length of our thinned chain. We've now discussed 2 different interpretations of the effective sample size. The effective sample size can be thought of as how many independent samples you would need to get the same information, or you could think of it as the length of chain you would have left over if you removed iterations or thinned the chain until you got rid of the autocorrelation. Now, let's compare the effective sample size of this highly autocorrelated chain with 100,000 iterations to the effective sample size of our good chain, the one that was mixing well, but only had 4,000 iterations. The first chain we looked at, which had good convergence properties, has an effective sample size of nearly 1,000 out of 4,000, whereas the chain with high autocorrelation had a sample size, an effective sample size of 373 out of 100,000 samples. Clearly, autocorrelation makes a big difference in how much information you get out of your Markov chain. It is usually a good idea to check the Monte Carlo effective sample size of your chain when doing MCMC. If all you seek is a posterior mean estimate, then an effective sample size of a few hundred to a few thousand should be good enough. However, if you want to create something like a 95% posterior interval, you're going to need more iterations. You may need many thousands of effective samples to produce a reliable estimate of those outer edges of the distribution. The number you need can quickly be calculated using the Raftery and Lewis diagnostic. That is also available in the CODA package using the Raftery.diag function. Here we're calculating the Raftery and Lewis diagnostic for that first good chain. This diagnostic tells us that if we want to be 95% confident that we are estimating the 0.025 quantile of the distribution to an accuracy of 0.005, then we're going to need this many iterations in our chain. The number next to it here, 3,746, is the number of independent samples we would need from a chain that had 0 autocorrelation. With the autocorrelation in this chain, we would need to generate a little more than 12,000 samples to get this degree of accuracy in creating probability intervals. The dependence factor increases with autocorrelation in the chain. It tells us how many more iterations we would need with this particular chain over an independent sample. In this case, we need about 3 times as many samples to get the same amount of information. To learn more about the Raftery and Lewis diagnostic, we can always check the documentation in the CODA package. To access that, type question mark and then the name of the function. This opens the documentation page for the diagnostic. We can read a little bit about the underlying theory. We can learn more about which arguments we can change in the function to get different information. And we also have references to the original papers that these diagnostics are based off of. Just to review, the Raftery-Lewis diagnostic gives us the sample size that we would need for our Markov chain if we want to create reliable posterior intervals. We've seen in previous examples how the initial value of the chain can affect how quickly the chain converges. If our initial value is far from the bulk of the posterior distribution, then it may take a while for the chain to travel there, as we saw in this example, where the posterior mean is close to 1, but we started the chain way out here at 10. It took a long time for the chain to wander to the right area and start exploring that posterior distribution. Clearly, the first 100 or so iterations do not reflect draws from the stationary distribution, so they should be discarded before we use this chain for Monte Carlo estimates. This is called the burn-in period. You should always discard early iterations that do not appear to be coming from the stationary distribution. Even if the chain appears to have converged early on, it is a safer practice to discard an initial burn-in. If we want to be more confident that we have converged to the true stationary distribution, we can simulate multiple chains, each with a different starting value. Let's run that simulation, where post 1 has a specific starting value, post 2 has a different starting value, and so forth down to posterior 5. I'm going to combine all of these chains into one MCMC object using the MCMC list function. Now let's look at the trace plot for this multi-chain simulation. We started each of these chains at very different initial values, but as you can see, as we progress through the iterations, after about 100, maybe 200 iterations, these chains have all converged to the same location. This increases our confidence that what we have found is in fact the stationary distribution that we're looking for. Trace plots provide an informal diagnostic for the convergence of our chains. We can back up these visual results with the Gelman and Rubin diagnostic. This diagnostic requires that we fit multiple chains. It calculates the variability within chains and compares that to the variability between the chains. First, we need to combine the chains all into one object here with the MCMC.list function. And we'll start a new script and call the diagnostic. It's part of the CODA package, and it's called Gelman.diag for that object that we just created. Again, the diagnostic compares the variability within the chains to the variability between the chains. If all chains have converged to the stationary distribution, the variability between the chains should be relatively small, and this potential scale reduction factor, which is the statistic computed by this diagnostic, should be a small number close to 1. If values are much higher than 1, then we would conclude that the chains have not yet converged. We can also create a plot to go with this diagnostic. It's called Gelman.plot for our combined chains. And it shows us how the shrinkage factor changes as we add iterations to the chain. From this plot, we can see that if we only used the first 50 iterations, then the potential scale reduction factor, or the shrink factor, would be close to 10, indicating that the chains have not converged. But once we're past about 300 iterations, the shrink factor is essentially 1, indicating that by then we have probably reached convergence. Of course, we shouldn't stop sampling as soon as we reach convergence. Instead, this is where we should begin saving our samples for Monte Carlo estimation. To get more information on these diagnostics, we can type $Gelman.diag to access the documentation for this function. Again, if we want to learn more about the Gelman and Rubin convergence diagnostic, this would be the place to start. It describes the diagnostic, describes the function, talks a little bit about the theory underlying this diagnostic, and gives us the sources. If we are reasonably confident that our Markov chain has converged, then we can go ahead and treat it as though it were a Monte Carlo sample from the posterior distribution, albeit with a smaller effective sample size. That means that we can use the techniques from Lesson 3 to calculate posterior quantities, like the posterior mean and the posterior intervals, from the samples directly. Let's return to the first example where we have the chain that appeared to have converged. To remind ourselves, let's look at the trace plot for it again. We have 4,000 iterations of a chain that appears that it has already converged. But to be safe, let's discard the first 1,000 iterations as burn-in. So the number of burn-in iterations, n burn, will be 1,000. Let's read that in. And let's create a set of samples that we want to keep. We'll add this onto our list for post 0 and call it mu keep. It will come from the original post 0 mu's, but now we're going to discard the first 1,000 iterations, 1 through n burn. Let's look at the structure now of post 0. And now we have the samples of mu that we're going to keep. There are 3,000 of these samples. Since we're confident that this has reached the stationary distribution, we can be confident in our Monte Carlo estimates. So let's look at the summary of this object of mu keep. We've seen this before. It provides a brief summary of our inferences for the mean mu, that parameter we've been estimating. It has mean close to 0.9, as we have seen in previous examples, standard deviation 0.3, and has these different quantiles. For example, the 0.025 quantile is this number, and the 0.975 quantile is this number. So if we wanted to create a posterior interval for mu, we could say that the posterior probability that mu is between this number and this number is 0.95. We can also compute posterior probabilities of different hypotheses. For example, if we want to know the posterior probability that mu is greater than 1, we'll just take the mean of an indicator and we're going to count how many of these samples are greater than 1. Our posterior probability is about 0.35 that mu is greater than 1. We discussed linear regression briefly in the previous course, and we fit a few models with non-informative priors. Here we'll provide a brief review, demonstrate fitting linear regression models in Jags, and discuss a few practical skills that are helpful when fitting linear models in general. This is not meant to be a comprehensive treatment of linear models, which you can find in numerous courses and textbooks. Linear regression is perhaps the simplest way to relate a continuous response variable to multiple explanatory variables. This may arise from observing several variables together and investigating which variables correlate with the response variable, or it could arise from conducting an experiment where we carefully assign values of explanatory variables to randomly selected subjects and try to establish a cause and effect relationship. A linear regression model has the following form. The response, y, for observation I, will be equal to this linear form of the other variables. We have an intercept, beta naught, and then a coefficient beta 1 for the first x variable, and so forth for up to k variables. So this would be the ith value of xk. This describes the mean, and then we would also add an error individual term for observation I. We would assume that the epsilons are IID from a normal distribution, mean 0, variance sigma squared for observations 1 up to n. Equivalently, we could write this model for yi directly as yi given all of the x values for individual I, all of the beta coefficients and sigma squared would be independently distributed, not identically distributed because the mean changes for each observation, but independent from a normal with the same mean, beta naught plus beta 1 x1I up for all of our k variables, and constant variance sigma squared. Again, k is the number of predictor variables. This yields the following graphical model structure. We'll start with a plate for all of our different y variables. So yi, which is random and observed for I equals 1 up to n. We also observe the x variables. So we have x1i, x2i, all the way up to xki. And I'm going to draw squares around these ones instead of circles to indicate that they're not random variables. We're always conditioning on the x's. So they'll just be constants. Of course, the yi's depend on the values of the x's, and the yi's will also depend on the values of these parameters. So we have beta naught, beta 1, up to beta k, and of course, sigma squared. And the yi's depend on all of these. So this would be the graphical model representation. The terms of a linear model are always linearly related because of the structure of the model. But the model does not have to be linear necessarily in the x-y relationship. For example, it may be that y is related linearly to x squared instead of x. Hence, we could transform the x and y variables to get new x's and new y's, but we would still have a linear model. However, in that case, if we transform the variables, we must be careful about how this changes the final interpretation of the results. The basic interpretation of the beta coefficients is this. While holding all other x variables constant, if x1, for example, increases by 1, then the mean of y is expected to increase by beta 1. That is, beta 1 describes how the mean of y changes with changes in x1 while accounting for all the other x variables. That's true for all of the x variables. Note that we're going to assume that the y's are independent of each other given the x's and that they have the same variance. These are strong assumptions that are not always met, and there are many statistical models to address that. We'll look at some hierarchical methods in the coming lessons. Of course, we need to complete the model with prior distributions. So we might say beta naught comes from its prior. Beta 1 would come from its prior, and so forth for all the betas, and sigma squared would come from its prior. The most common choice for prior on the betas is a normal distribution, or we could do a multivariate normal for all of the betas at once. This is conditionally conjugate and allows us to do Gibbs sampling. If we want to be non-informative, we can choose normal priors with very large variance, which are practically flat for realistic values of beta. The non-informative priors used in the last class are equivalent to using normal priors with infinite variance. We can also use the conditionally conjugate inverse gamma prior for sigma squared that we're familiar with. Another common prior for the betas is the double exponential, or the Laplace prior, or Laplace distribution. The Laplace prior has this density, 1/2 e to the negative absolute value of beta. And the density looks like this. It's called double exponential because it looks like the exponential distribution, except it's been reflected over the y-axis. It has a sharp peak at x equals 0, or beta equals 0 in this case, which can be useful if we want to do variable selection among our x's, because it'll favor values near 0 for these betas. This is related to the popular regression technique known as the lasso. As an example of linear regression, we'll look at the Linehart data from the car package in R. Let's first load this package, library car. And to access a data set that comes with a package, we can use the data function and tell it which data set we want. It's the Linehart data set. And before we look at the data, let's learn a little bit about it from the documentation through $Linehart. If we run that line of code, it brings up the documentation page for these data. The Linehart data set contains data on infant mortality for 105 nations of the world around the year 1970. It contains 4 variables: per capita income in US dollars, infant mortality rate per 1,000 live births, a factor or categorical variable indicating which region of the world this country is located, and finally, whether this country exports oil as an indicator variable. If we want to learn more about the data set, we can also look to these different sources or references. Now that we know a little bit about this data set, let's explore it. First, I'm going to look at the head of the data set, the first few lines, where we see these 4 different variables: income, infant mortality rate, region, and whether the country exports oil, for the first several countries in this data set. We can also look at the structure of the data set to see what types of variables these all are. STR, Leinhart. And here we can see that income is an integer variable, infant is numeric, a floating point numeric, region is a factor or categorical variable with 4 levels, and oil is a factor variable with 2 levels, no and yes. To investigate the marginal relationships between each of these 4 variables, we can plot each of the scatter plots using pairs. So we say pairs, Leinhart, which creates scatter plots for every pair of variables together. For example, this plot is the scatter plot between infant mortality rate and income, where infant mortality rate is on the x-axis and income is on the y-axis. The same goes for categorical variables. And you can see that there are 2 versions of the same plot. This one is between infant and income, and this one is also between infant and income with the axes reversed. Instead of modeling all these variables at once, let's start with a simple linear regression model that relates infant mortality to per capita income. So let's do a plot for that one as well. We're going to plot infant mortality against income, where our data set is Leinhart. As you look at this scatter plot, you might be asking yourself, is a linear model actually appropriate here as a model between income and infant mortality? This relationship certainly doesn't look linear. In fact, both of these variables are extremely right skewed. To see that, let's look at a histogram of each one individually. We'll do a hist of the infant variable, and immediately you can see how right skewed it is. And now let's look at a histogram for income. Again, that one is very right skewed. Most values are very small, and then they scatter across large values. The short answer is no. A linear regression is not appropriate for these variables. However, we did notice that these variables are positive valued and very strongly right skewed. That is a hint that we could try looking at this on the log scale. So let's recreate these plots now with variables that are transformed. So let's look at Leinhart, and we're going to save a new variable. Let's call it log infant. It's going to be the log of Leinhart infant mortality rate. We'll run that, and let's create another variable that's just like it for the income variable. And we'll run that. Now let's look at the relationship between log income and log infant. We'll plot log infant against log income, where the data are still Leinhart. I would say that a linear model is much more appropriate choice now. You can imagine fitting a line through these data points. Let's start a new section and call it modeling. Remember that the reference Bayesian analysis with a non-informative prior or a flat prior on the coefficients in a linear model is available directly in R using the LM function. Let's fit one of those and call it L mod for linear model. LM, where we use the same syntax as we did to plot these variables. Log infant will be our response variable against log income, where the data is line art. We can run this linear model and look at a summary of the results. Under our non-informative flat prior, here are the estimates, the posterior mean estimates for the coefficients. These estimates are very large relative to their standard error, or in this case, standard deviation of the posterior distribution, and so they appear to be very statistically significant. Residual standard error gives us an estimate of the leftover variance after fitting the model. And the R-squared statistics tell us how much of the variability is explained by the linear model, in this case, about half. Also, don't miss this crucial line. It tells us that 4 of the observations in the data set were deleted. They were not used in the model because they contained missing values. There are statistical methods for dealing with missing values, but we're not going to discuss them in this course. So we're going to follow the example of the linear model function, and we're going to delete the observations that have missing values before we perform analysis. So what we can do here is save a new data set. We'll call it DAT, and it will come from the Linehart data set where we omit missing values. To do this in R, we use na.omit, and we give it the data set. Let's look at the original data set really fast, just so we can see which countries it was that we omitted. If we run Linehart, we see that there are missing values for Nepal. There are missing values for Laos, for Haiti, and for Iran. Those 4 countries will not be included in our analysis. Let's recreate this model now using Jags. First, we'll need to load the RJags library. And we'll specify the hierarchical form of the model. Let's call this mod 1. There will be several different models, so let's number this one. And we're going to start with the model string. The syntax for this in Jags is to say model with curly braces and fill in the different pieces. Let's start with the likelihood. For I in 1 through n, the length of the data, observation yi will come from a normal distribution, d norm, where the mean is mu sub I. We'll specify what that is in a moment. And precision, we'll call it PREC for now. Now we need to add the linear model part of this. Mu sub I is linear, where we have coefficient 1 plus coefficient 2 times the log income, the ith value of the log income. So yi comes from this normal distribution with mean mu I, and the mean comes from our linear model on log income. We now need to give a prior for these coefficients. We'll start another loop for j in 1 to 2, because they're two coefficients. Beta j will come from a normal distribution, d norm, with, let's say, mean 0 and a variance 1 million. We'll make it pretty large so that this prior is close to the non-informative prior model we fit earlier. Remember, we have to enter it as a precision for the normal distribution, so this will be 1 divided by the variance, 1.0, times 10 to the 6th power. We'll use an inverse gamma distribution on the variance of the normal distribution for the observations. An inverse gamma on the variance implies a gamma prior on the precision, which is the reciprocal of the variance. So let's put the prior directly on the precision. Precision will come from a gamma distribution. And remember, it's very important to check the Jags documentation, the Jags manual, under the chapter on distributions to remind ourselves how Jags parameterizes these distributions. In this case, it is the same as with R. The first parameter for the gamma distribution is a shape, and the second parameter is a rate. Let's use the same trick we did before, where we parameterize the prior in terms of a prior sample size and a prior guess. We'll use a prior sample size of 5, and recall we have to divide it by 2 to turn it into the gamma parameter. And then we have to do the prior sample size again, times our prior guess for the variance, let's say it's 10, and divide that also by 2. A gamma prior on the precision using this shape and this rate parameter is equivalent to an inverse gamma prior on the variance with this shape parameter and this as the scale parameter. Instead of precision, we'll probably be interested in the variance, which is equal to 1 over the precision. Notice we didn't assign a distribution here. Because we gave a prior to the precision, that implies a prior for sigma squared, the inverse gamma we've been talking about. So instead of a distribution here, we give it an equals. This is a deterministic relationship between the precision and the variance. Usually when we're modeling, the most interpretable quantity is the standard deviation instead of the variance. So let's monitor the standard deviation, which is just the square root of the variance. This completes the model, where this section tells us the likelihood of the data. This section gives us the priors for the coefficients, and down here we have the prior for the leftover or the unaccounted for variance. Jags requires that we put this in a string, so I'll put these between quotation marks. And now we need to set up the model. First, let's set the random seed. And we'll tell it what the data are. So data for model 1 that'll go into Jags needs to be a list where we named our variable y in the model, so we have to give it y down here. Y equals dat, we're using our modified data set where we removed missing values. Dat $ log infant is our response variable. N is the number of rows in the dat data set. And we also created a variable here called log income. So we need to give it the exact same name down here, log income, we'll get dat $log income. That's how we specified it in the data set. The parameters that we want to monitor for model 1 are the two coefficients, beta 1 and beta 2, and since they were specified and indexed together as a vector, I can just call it B. We have our choice if we want to monitor the precision, the variance, or the standard deviation from the likelihood. Let's just look at the standard deviation. We can give the model initial values, inits 1, and this goes in as a function that creates a list. We'll give an initial value for the beta coefficients. There are two of them, so let's draw two random normals. So drawing two random normals with mean, let's say 0, and variance or standard deviation 100. For our initial value on the precision, let's draw from a gamma distribution. We only need one draw, and let's just give it shape 1 and rate 1. That's actually an exponential distribution. So now that we've specified the data, told it which parameters we want to monitor, and given initial values for the different parameters, we can specify the model itself. Jags.model, where we create a text connection with mod1 string, mod1 underscore string that we just specified. The data is data1 underscore Jags that we just created. It's data1 Jags. We'll use the initial values from our function inits1. And let's say we want to run 3 different chains. That's another option to write into this Jags.model function. We want it to run 3 separate chains. In each chain, it'll initialize the chain with these random draws. So we'll have different starting values for each chain. We'll initialize the model by running all of this code. Initialization was essentially instant. And now that the model is initialized, let's give it a little bit of a burn-in period by updating the model for, let's say, 1,000 iterations. So it ran the model for 1,000 iterations, but it didn't keep the samples. Once we have the burn-in period run, let's create our actual posterior simulation that we're going to keep for model inference. Mod1 sim is what we'll name it. It will come from coda samples. We're going to create coda samples from the model. Model 1, where the variable names are the parameters that we created. And we'll run this for, let's say, 5,000 iterations. We'll run this line to run the model. And since we ran 3 different chains, sometimes it's useful to combine them into one chain. So we'll call that mod1 csim for combined simulation. And we're going to do this by stacking the matrices that contain the simulations themselves. Inside mod1.sim, the simulations are stored as matrices. To do this, we need to use the do.call function in R and rbind. Remember, we used cbind earlier to combine matrices along the columns. Now we're going to stack the matrices vertically by combining them on the rows using mod1 sim, and run that line. Before we check the inferences from our model, we should perform convergence diagnostics for the Markov chains. I'll start another section here and call it convergence. Now, we'll start with trace plots. So we'll plot mod1 underscore sim. This produces the different trace plots, where the different colors are the 3 different chains that we ran. We see no long-term trends in these trace plots, so they look pretty good. Next, let's take a look at the Gelman and Rubin diagnostic. Gelman.diag of mod1 sim. And we see that the potential scale reduction factors for the 3 different parameters is very close to 1, indicating that we probably have converged. Let's also look at the autocorrelation. We see very high autocorrelation with the initial lags in the intercept term as well as our second beta term for the slope. This prompts us especially to check our effective sample size. Recall, we ran the chain for 5,000 iterations for 3 different chains. So we should have about 15,000 samples. Out of those 15,000 samples, our effective sample size for beta 1, or the intercept, is only 350. This one is only 360, and this one is about 14,000. So the sigma parameter mixed very well. Our coefficients, not so much. These effective sample sizes are still okay if all we're interested in is the posterior mean for these 2 parameters. But if we want to create something like a 95% posterior probability interval, we want to have more effective samples, so we would want to run the chains for longer. Next, let's look at a posterior summary from this model. We can see that we used the first 1,000 samples as a burn-in, and then we saved the next 5,000 samples. We ran 3 chains, and here are the resulting estimates of the parameters. They're very similar to what we got from the reference analysis where we used a flat prior, because the priors for these coefficients in the Jags model had a very large variance. So the reference analysis was called L-mod. Let's compare. The estimated mean from this model was about 7.1 or 7.2, and here the intercept term was estimated at about 7.1 in the reference analysis. The slope between the log income and the log infant mortality rate was estimated to be about negative 0.52 in this model and about negative 0.51 in the reference analysis. The estimates are very close. The standard error estimate for the residuals, which is the estimate for sigma in the reference analysis, was about 0.69. In our model, however, in Jags, we estimated it to be about 0.97. This is because we used a prior guess that the variance was 10. In other words, that the standard deviation was a little higher than 3. And we used an equivalent sample size of 5 for that prior. If that is our true belief about the variance ahead of time, then this would be our answer for our posterior. But if we're less confident in our prior, it might make sense to lower the prior effective sample size in this prior. Remember that if we interpret the results from these models, we have to keep in mind that we modeled the log of infant mortality versus the log of income. So this negative correlation here is on the log scale. The last thing we'll do in this segment is check the residuals. Residuals are defined as the difference between the response, the actual observation, and the model's prediction for each value. Residuals are extremely important in linear modeling, since residuals can reveal violations of the assumptions we made to specify the model. In particular, we are looking for any sign that the model is not linear, that it is not normally distributed, or that the observations are not independent from each other, at least conditionally on the explanatory variables. First, let's look at what would have happened if we fit the reference linear model to the untransformed variables. That was, if we fit the linear model to infant mortality rate versus income, not on the log scale. Remember, when we plotted these relationships, it didn't look like a linear model was a good idea here. Let's plot the residuals for L mod 0, which will give us residuals on the y-axis and index on the x-axis. The index refers to which row of the data set it came from. If the data points were not independent from each other, we might see a pattern in this plot. There doesn't appear to be much of a pattern here, so it's at least somewhat reasonable to assume that these data are independent. Another very important look at the residuals is if we plot the prediction of the model, which we can create with the predict function, L mod 0, on the x-axis and the residuals on the y-axis. Again, in this plot, we don't want to see any patterns. We want to see essentially randomness, which is not the case in this plot. First of all, we can see a downward trend as the values of the prediction from the model get higher, the residuals get smaller. And our assumption that the residual variance is the same for all observations appears to be wildly incorrect in this case. For all of these predicted values down here, the variance in the residuals is quite small, but for large predicted values, we have large variance. Finally, we can check the assumption of normality using the QQ norm plot on the residuals. This plot shows the theoretical quantiles, or percentiles, of an actual normal distribution on the x-axis with the sample quantiles of the residuals on the y-axis. If the residuals actually came from a normal distribution, the points on this plot would essentially follow a straight line. In this case, we have a curvature going up that increases and gets more extreme at the high values. This indicates that the residuals have a distribution that is right skewed and not normal. These plots that we've looked at so far are a bad example. They show us what the residual plots should not look like. Now, let's return to our model fit to the log transformed variables. This time, we'll use our residuals from our Bayesian model that we fit in Jags. Predictions from Bayesian models come as posterior predictive distributions. So in reality, with a Bayesian model, all residuals, or each residual, would have its own distribution. We're going to simplify things a little bit and look at the residuals that come only from predictions based on the posterior means. First, we need to create the design matrix, the matrix that contains the explanatory variables. We will do that by C-binding, that is combining columns. First, of the term that goes with the intercept, we will repeat the number 1 n times, where n comes from data1 underscore Jags. We saved this variable earlier. There are 101 observations. So this rep will create a vector of 101 ones. The second column of this X matrix is data1 underscore Jags log income. We can look at the head of X. This looks correct. And we're going to base our predictions on the posterior means of the parameters. Let's save that in a variable called PM for posterior means, params from model 1. And it'll be the column means of our combined simulation. That is the simulation of all 3 chains combined into one matrix. We named that earlier CSIM. We'll run that and take a look at the values, PM params 1. So these are the posterior mean estimates for the parameters. Next, we need to get a predicted value for each of the observations from the model. We'll call that y hat from model 1. This would be the intercept times a 1 plus the slope times the value of log income. In matrix notation, we can do that using our X matrix, doing matrix multiplication, and then supplying our posterior means for the 2 coefficients, PM params 1, and we're giving it just the first 2 values for those coefficients that look like this. If we run that, we get the predicted values in the form of a matrix. Let's turn it into a vector by rerunning this and putting it inside the drop function. The drop function gets rid of the matrix structure and turns this into just a vector. Now we have a vector of predicted values from the model. The residual is defined as the actual data, data 1 Jags, where we take out y. Those are the values. And we're going to subtract our predicted values based on the posterior means. We'll run that. And let's plot these again against the index. This already looks much better than before. Again, we don't see any patterns or trends here. So this plot looks good. Let's also plot the predicted values on the x-axis against the residuals. Again, this one looks pretty good. We don't see any trends or patterns in the mean of these residuals. They approximately have a mean of 0. There are two slight concerns here. One is that the variance appears to increase as you go from small predicted values to large predicted values. And we see two very strong outliers. We'll address these in a moment. First, let's look at the QQ norm plot for the residuals. And remember, if the residuals are approximately coming from a normal distribution, then this plot would have a linear form between the points. That seems reasonable in this case, except for our two outliers that we identified earlier. Let's find out which countries those outliers are associated with. We'll get the row names from our data set, just DAT. First of all, let's take a look at that. If we do the row names from DAT, we get all of the names of the countries. We want to order these names of countries by the size of their residual. So we're going to index it with the order function. We're going to order this by resid1, the value in resid1, and we want it to be a decreasing ordering. We don't want to see all of the countries, so let's do the head function on this. We'll run this, and we'll see these are the first 5 countries that have the largest residuals. The two biggest residuals appear to be Saudi Arabia and Libya. When outliers appear in your analysis, it is a good idea to double check that they are not just data errors in your data entry. If the values are correct, you may reconsider whether these data points really are representative of the data you were trying to model. If you conclude that they're not, for example, they were recorded in different years or they just don't belong, you may be able to justify dropping these data points from the data set. If you conclude that the outliers are part of the data and should not be removed, we have several modeling options to accommodate them, and that's what we'll address in the next segment. In the previous segment, we saw two outliers in the model relating the log of infant mortality to the log of income. Here, we're going to discuss the options available to you if you decide that these outliers really do belong in the data set. You can't just delete them. The first approach is to look for additional covariates or explanatory variables that may be able to explain the outliers. For example, there could be a number of variables that provide information about infant mortality above and beyond what income provides as an explanation. Looking back at our data, there are two variables we haven't used yet. The first one is region, and the second is oil. The oil variable indicates oil exporting countries. Both Saudi Arabia and Libya are oil exporting countries, so perhaps this might explain part of the anomaly. We've already coded up and run Model 1, where log income was the only explanatory variable. Here now is Model 2, where we include the indicator variable is oil, meaning is this an oil exporting country, along with a new coefficient for that term. We've added that coefficient as well to our prior, and we've kept the same prior on our observation variance. To run Model 2, we need to modify the data that we send to the model to include the is_oil indicator. To create that indicator, we need to transform the original data, which is in terms of yes and no. We want ones to represent yes and zeros to represent no. So this says, as.numeric, turn the true or false statement into a number for whether dat $oil is a yes. If we run that, we get a set of ones and zeros. Here is the batch of oil exporting countries right here. Everything else in the model setup is the same, except now we're going to draw 3 initial values for our beta vector, and we'll run mod 2 with the new data and the new initial values. We'll run 1,000 iterations of burn-in and run our samples to be saved. Let's go ahead and run all of this code. First, we'll run our Jags library, and then run model 2. Every time you run a new model, you should always check the convergence diagnostics for the chain you just ran. We're going to skip that in the interest of time here, but I will report that the chains look okay here. Let's take a look at the posterior summary from our chains. It looks like not much has changed since Model 1. The intercept is a similar number. The effect related to income has not changed much. And we see a positive relationship between oil production and the log of infant mortality. Because these data are merely observational, we can't say that oil production causes an increase in infant mortality. Indeed, that most certainly is not true. We can say that they are positively correlated. Now let's check the residuals. We'll follow the same steps we did for Model 1, where we create the design matrix. We'll call it X2 in this case, where we've now added the is_oil indicator. So we'll run that line and take a look at the top of X2. So now we have a third column for the oil indicator. We'll collect our posterior means for the parameters, as well as the predicted values based on those posterior means. And finally, we'll calculate the residuals as the difference between the value and the prediction. Now let's look at the residuals. We also want to compare these residuals to the residuals from Model 1. So let's put both of these plots on the same screen with par MF row. We want 2 rows of plots and 1 column of plots. Start an empty plot, and we'll fill it first with the residuals from the new model, and then the residuals from the old model. It looks like we do have an improvement. The residuals in the new model are closer to the bulk of the data than the residuals were in the old model, where they're much further away. The standard deviation of the residuals in the second model here is 0.64. The strongest outlier up here is more than 2 away from the mean, which means it's more than 3 standard deviations, 3 times 0.64 away from the mean. So 3 standard deviations is still quite an extreme outlier. So although we've seen improvement, these outliers are pretty far away still. We might consider adding the other covariate region, but instead let's look at another option when we are faced with strong outliers. That option is to change the distribution we use for the likelihood. The normal distribution, or the normal likelihood, has thin tails. Almost all of the probability in a normal distribution is concentrated within the first few standard deviations of the mean. This does not accommodate outliers well. Consequently, models with a normal likelihood might be overly influenced by outliers. Remember, the t-distribution is similar to the normal distribution. Here's a plot with the PDF of the normal in black and the PDF of a t-distribution with 1 degree of freedom in red. The t-distribution is similar to the normal distribution, but it has thicker tails, which are better at accommodating outliers. The t-model might look something like this. We're not going to run this model, but we're going to step through it and talk about it a little bit. Notice that the t-distribution, which we're using as our likelihood here, has 3 parameters: a location. In Jags, tau is an inverse scale parameter and a degrees of freedom parameter. The smaller the degrees of freedom, the heavier the tails of the t-distribution. We might fix the degrees of freedom to some number like we did in this plot, or we can assign it a prior distribution. That's what we've done here. The degrees of freedom has to be a positive number, so we'll give it an exponential prior. The inverse scale, or the tau parameter, behaves similarly to the precision parameter in the normal model. It is not exactly the same as the precision parameter, but it's close, so we'll give it the same d gamma prior that we used before. The inverse scale is related to the standard deviation of the errors by this equation here. Finally, we're going to relate the location parameter with our linear model form right here. As a side note, we should be aware that this prior that the t-distribution does not have a mean and a variance if the degrees of freedom is less than 2. That can happen under this model. If we wanted to force the model, the likelihood, to have a mean and a variance, we could increase the degrees of freedom by 2 by adding a new variable. Let's call it nu. And then the degrees of freedom would simply be nu plus 2.0. This would guarantee that the degrees of freedom is greater than 2. Again, we're not going to fit this model. We'll leave it up to you. We have now proposed 3 different models. How do we compare their performance on our data? In the previous course, we discussed estimating parameters in models using the maximum likelihood method. We can choose between competing models using a similar idea. We will use a quantity known as the deviance information criterion, often referred to as the DIC, which essentially calculates the posterior mean of the log likelihood and adds a penalty for model complexity. Let's calculate the DIC for our first 2 linear models. The first one was our simple linear regression. To calculate this, we'll use the dic.samples function, and we'll give it our first model, mod 1. And this samples from a posterior distribution, so we need to give it a specified number of iterations, and we can run it. Before we interpret these results, let's also run the DIC for model 2, where we added oil as another explanatory variable. Let's run those samples as well. The first number in the output, called mean deviance, is the Monte Carlo estimated posterior mean deviance. Deviance equals -2 times the log likelihood plus a constant that's irrelevant for comparing models, so we're not going to worry about it. Because of that -2 factor, a smaller deviance means a higher likelihood. Next, we are given a penalty term for the complexity of our model. This penalty is necessary because we can always increase the likelihood of the model by making it more complex to fit the data exactly. We don't want to do this because models that are overfit usually generalize poorly. This penalty is roughly equal to the effective number of parameters in your model. You can see this here. In the first model, we had a variance parameter and 2 coefficients for a total of 3 parameters, close to the 2.8 we got here. In model 2, we added one more coefficient, one more parameter than the previous model, which we can see reflected in the penalty. We add these two quantities, the mean deviance and the penalty term, to get the penalized deviance, the third term. This is the estimated DIC. A better fitting model has a lower DIC value. In this case, the DIC is lower for the second model than it is for the first model. So the DIC would select model 2 over model 1. The gains we receive in deviance by adding the is_oil covariate outweigh the penalty for adding that extra parameter to our model. The final DIC calculation for the second model is lower than the first, so we're going to prefer this second model. We encourage you to explore different model specifications and compare their fit to the data using DIC. Wikipedia has a good introduction to the DIC, and you can also find out more details about the Jags implementation through the rjags package documentation. If we type in $DIC samples, we can get that information. You might want to try fitting the model 3 with the t likelihood. Calculate its DIC to see how it compares with the other two models. Anova is used when we have categorical explanatory variables so that the observations belong to groups. It stands for analysis of variance, where we compare the variability of responses within groups to the variability of responses between groups. If the variability between groups is large relative to the variability within the groups, we conclude that there is a grouping effect. Categorical explanatory variables are often referred to as factor variables. Factors can have two categories or levels, for example, low and high or true and false, or they could have many levels. They often result from experiments where we carefully assign values of explanatory variables to randomly selected subjects and look for a cause and effect relationship. There can be one or many factors in an experiment. For example, if we were going to conduct an online marketing experiment, we might experiment with two factors of website design. Let's say these factors are sound and font size. We might use two levels with sound. For example, having music or having no music. And for the font size factor, we might do something like small, medium, and large. This 2x3 design would result in a total of 6 treatment combinations. For example, we could do a website with music and small font, or no music and large. There are 6 possible ways to do that. Let's write down the model with one explanatory variable that has G, capital G levels. That would be yi given a variable that tells us which group individual I belongs to, all of the means for each group, and sigma squared would be independently distributed normal, where the mean is mu, the mu that corresponds to the group of subject I, and of course, variance sigma squared. This G variable right here is just a group indicator, so it would be a member of one of this set, one of these numbers right here, from 1 up to G. So for individual I, if Gi is 2, that means that Yi is a member of group 2. And of course we have our observations 1 up to n. Alternatively, we can write the mean in terms of an intercept representing a baseline group, and then effects for each of the G minus 1 other groups. So we could write an alternative model. Alternative model formulation would be to set the expected value right here of Yi would be equal to beta naught plus beta 1 x1I, like we had before, up to beta capital G minus 1 times x G minus 1I. Here, the x variables are what are called dummy variables. They're indicators that the group of individual I, in this case, is 1. This x here would be an indicator variable that the group of individual I is G minus 1. That is, at most, one of these x's will be turned on or have a value 1. Otherwise, if we're in group capital G, the last group, the only parameter active is this one here. So beta naught corresponds to the mean of group G. Again, these x's here are what are called dummy variables. They indicate the membership of the observation into group K. This formulation right here shows how Anova is related to linear regression. This formulation is also the default in R. These two formulations for the mean are equivalent, and both of them have capital G parameters for the mean. If we had more than capital G parameters, the parameters would no longer be uniquely identified, since infinite combinations of parameter values would result in the same mean. We must be careful not to over-parameterize. Again, the assumption of constant variance across all groups might be too restrictive for your data. If that's the case, you might also consider having multiple sigma squared parameters for different groups. We're now going to consider the model where we have two factors. Let's call the factors A and B. They might correspond to sound being A and font size being B from our website design experiment that we discussed earlier. One option for a model is analogous to the first model we used for one factor, where we have a different mean for each treatment combination. This is called the cell means model. So if we have factor A, which in this case would be sound, we have 2 levels. And for factor B, which could be represented by font size, would have 3 levels. So this might be representing small, medium, and large. In this model formulation, we need a different mean for each one of these combinations. So mu 1 sub 1 would represent the mean for this group with music and small font size. We can fill in the rest of these. So each of these means corresponds to a treatment group. It is written, the model itself is written, the same as before, except that mu now has 2 indexes, one for each factor. With 6 treatment groups, we can have at most 6 parameters describing the means. However, we might get away with fewer parameters. For example, we could use the following additive model. This model, which has only 4 parameters instead of 6, would be appropriate if we believe there are no interactions. Let's write this model out really quick. The expected value for yi would be equal to a baseline mean plus, we'll say, alpha 2 times the indicator that the level of factor A, which we'll call little a for individual I, is 2. In other words, this is an indicator that individual I is in level 2 of factor A. Then we could have a beta 2 times an indicator that the level for individual I of factor B is equal to 2, plus beta 3 times an indicator that BI equals 3. This mu here represents the mean for this group right here. And then, if they're in a different group, for example, of factor A, we would add alpha 2, which represents the effect of going from this group to this group. Same thing goes for factor B. If we want to move from level 1 of factor B up to level 2, we would add this coefficient here. It's an adjustment to the mean. I mentioned earlier that this additive model would be appropriate if we had no interaction between the variables. Or, in other words, if we believe that going from level 1 to level 2 of factor A has the same effect on the mean regardless of whether we're in level 1, 2, or 3 of factor B. If the effect of factor A on the response changes between levels of factor B, then we would need more parameters to describe how that mean changes, for example, with this cell means model. This phenomenon is called interaction between the factors. In the coming segments, we'll look at an example of a one-way Anova model. We'll work with a two-way Anova in the honors section. As an example of a one-way Anova model, we'll look at the plant growth data in R. All we need to do to extract the data is use the data function on plant growth, and then we can immediately look at the documentation to learn a little bit about this data set. The plant growth data contains results from an experiment to compare yields, that is, measured by plant weight, for plants that were grown under a control and 2 different treatment conditions. There are 30 experiments, and there are 2 variables. The first variable is the weight of the plant, and the second is the group to which that plant was assigned. It's either control, treatment 1, or treatment 2. You can check this source for more information. Let's take a look at the plant growth data. As we said, the first column contains the weights of the plants. The second column tells us which group that plant was in. Because the explanatory variable group is a factor and is not continuous, we're going to choose to visualize the data with box plots rather than with scatter plots. So we'll create a box plot of the weight against group. using the plant growth data. Here are the box plots. The box plots summarize the distribution of the data for each of the three groups, control, treatment 1, and treatment 2. For example, this line tells us the median of yield for the control group is a little bit higher than 5, and most of the distribution is located between 4.5 and 5.5. It appears that treatment 2 has the highest mean yield, but it might be questionable whether each group has the same variance. We're going to assume that is the case in our modeling. Again, let's begin modeling with a reference analysis using the non-informative flat prior for a linear model in R. We'll call it L mod, which is a linear model of weight versus our factor variable group, and of course the data are plant growth. We'll run this linear model and create a summary for it. And here we get the posterior mean estimates for the three parameters governing the mean. The first group, the intercept, refers to the control group, and it is the mean yield for the control group, about 5. These next two parameters give us the modification to this original mean to obtain the mean for treatment group 1. So the mean for treatment group 1 would be about 4.6, and the mean for treatment group 2 would be about 5.5. We're adding to the baseline. With Anova models, you can also calculate the Anova table. So we'll do Anova for this linear model, run that, which gives us the analysis of variance table. It indicates to us the results of a statistical test for each factor variable, whether that factor variable significantly contributes to the variability in the data. It does this by calculating the variability between the factors versus the variability within the factors. If this is a large ratio, then we would say that the factor variable does significantly contribute to the variability in the data. In this case, it gives a p-value of 0.016, which is marginally significant. Let's now fit a Bayesian model in Jags. The model we'll use now is the cell means model, where each group gets its own mean. The model string, which I've already included here, starts with a likelihood, as usual, where yi comes from a normal distribution, where mu I has another index. First, to know which mu is active for the ith person, we need to extract a group number. Group I will evaluate to a number, group 1, 2, or 3, which will tell us which mu to use for the ith person. We'll use a constant variance, or in this case, precision. And for each of the three cell means, we'll use a fairly non-informative normal prior. In our prior for the variance, we'll use an inverse gamma with 5 observations as our effective prior sample size and a prior guess on the variance of 1. That would be an inverse gamma prior on the variance, which translates to a gamma prior on the precision. Instead of monitoring the precision, let's monitor the standard deviation of the observations using this calculation. Below, we have the standard setup for a Jags model. First, let's look at the structure of the plant growth data set, where the first variable, the weight of the plants, is a numeric variable, and the second, the group, is a factor with 3 levels. When we put that data into Jags through data Jags, we need to turn that group indicator into a numeric variable. So we'll say as.numeric plant growth group. Let's see what that looks like. It translates the 3 factors, control, treatment 1, and treatment 2, into numbers, where 1 represents control, 2 represents treatment 1, and group 3 represents treatment 2. This is the group variable that will go right here in our model. We're going to monitor mu and sigma. We can give it initial values, which are optional. We could just omit the initial values, and the Jags model would create initial values for us. We'll run 1,000 iterations of burn-in. We'll run our 3 chains for 5,000 iterations to save those samples, and then again, we'll combine those samples at the end. Let's run this model. First, we need to load the rjags library. And then we'll run the models. Before we use the model, let's check our convergence diagnostics. First, we'll start with our trace plots. And in this case, they look really good. Then we'll check our Gelman and Rubin statistics. The potential scale reduction factors are all essentially 1. The autocorrelation is definitely not a big problem here. So we would imagine that the effective sample size will be large, close to the actual size of the chain, which is true. So now that we're confident in our Monte Carlo simulation from the posterior, let's calculate the posterior mean for the parameters. We'll do that using the column means based on the combined simulations where they're all in one matrix. Let's take a look at these posterior means. And really quickly, let's compare those to the coefficient estimates that we got from the non-informative reference analysis. These results look pretty consistent. The mu estimates for the control group are similar between the 2 models. The cell mean for treatment 1, which you obtain by adding these 2 numbers, is very close to the treatment mean for group 2, estimated in our Jags model. And the treatment mean for treatment 2 is also very similar. If you add 0.49 to 0.50, you get essentially this number right here. So these 2 models are very consistent. Let's use these posterior means of the parameters to compute residuals. The first thing we need are predictions for each observation. Call that y hat. And it'll be based on the posterior means for these parameters for the first 3 means. And we want to index these by their group indicator. So that comes from data Jags, the group variable. Let's just remind ourselves what's in the group variable. This tells us that observation 1 was in group 1, observation 11 was in group 2, observation 12 was in group 2, and so forth. So what this line of code will do is that the prediction for observation 1 will be the posterior mean for the mu of group 1 because of this index. The prediction for observation 10 will be mu 1. The prediction for observation 11 will be mu 2, and so forth. Let's see if that's true. We'll run that and take a look at y hat. And we can see the first 10 observations are predicted to have mean mu equal to the first group's mean. This is true also for groups 2 and 3. Once we have the predicted values, we can calculate the residuals as the difference between the data and the predicted values. Let's plot those residuals against their index or observation number. And I don't see any patterns here. This looks pretty good. Next, we'll create a residual plot where the x-axis contains the predicted values. Not surprisingly, there are only 3 sets of predictions because there are 3 groups. But one thing that really stands out is that the variance for this group, the residual variance, is much higher than the residual variance for this group. As we mentioned earlier, it might be appropriate to have a separate variance parameter for each group, just like we had a separate mu parameter for each group. We'll let you do that as an exercise. Let's now look at a summary of our posterior distributions. Summary of mod sim, which gives us the posterior means for the parameters, which we've already seen, as well as the posterior standard deviations. Also, we have quantiles from the posterior distributions. For example, if we wanted to create a 95% posterior probability interval for mu1 associated with the control group, it could be between this number and this number. If we wanted to create a highest posterior density interval, an HPD interval, which we discussed in the previous course, it really is just what the name implies. It's the interval associated with the highest values of posterior density. We can use the HPD interval function from the CODA package and give it our mod CSIM for our combined simulations, which were all in one matrix. Let's run that and get a 95% HPD interval for each of the parameters. Usually the HPD interval is slightly smaller than the interval using equal tails. We can also give it another argument. If we want to change the posterior probability associated with the interval, we can change it to, say, for example, 0.9, and we would get 90% posterior probability intervals. Now suppose that in this experiment, we are interested to know if one of the treatments increases the mean yield from the plants. It is clear from our posterior summaries that treatment 1 does not increase plant yield over the control group, but treatment 2 might increase it. One major advantage of having a Bayesian model with Monte Carlo samples from the posterior is that it is easy to calculate posterior probabilities of hypotheses like this. So, if we want to find out whether treatment 2 produces a larger yield than the control group, let's create an indicator variable from our combined simulations. Column 3 refers to mu3. We want to see if mu3 is greater than CSIM mu1. This will give us, for each sample in our Monte Carlo simulation, whether the draw for mu3 was larger than the draw for mu1. If we take the average of that, that gives us the posterior probability. Really fast, let's just double check. Mod CSIM, look at the head of this posterior simulation to make sure we have the right columns. Column 1 is mu1, column 3 is mu3. So let's calculate this posterior probability. It's about 0.94, a very high posterior probability that the mean yield is greater for treatment group 2 than for the control group. Now suppose that treatment 2 would be costly to put into production, and in order to be worthwhile, this treatment must increase the mean yield by at least 10%. What is the posterior probability that the increase is at least that? Well, we can easily do this with posterior samples again. And we need mu3 to be at least 10% larger than mu1. So it needs to be at least as big as 1.1 times mu1. The posterior probability for this hypothesis is about 0.48. In other words, we have about 50-50 odds that adopting treatment 2 will increase the mean yield of the plants by at least 10%. It might be tempting to look at a lot of comparisons or test many hypotheses like these, but we must warn you that this could yield unreliable or non-reproducible results. Back when we discussed the statistical modeling cycle, we said that it is best not to search your results for interesting hypotheses, because if there are many hypotheses, some will appear to show effects or associations simply due to chance. Results are most reliable when we determine a relatively small number of hypotheses that we're interested in beforehand. Then we collect the data and then statistically evaluate the evidence for them. Linear regression is used when we have a continuous response variable and several explanatory variables, or covariates. But what if the response variable is binary, 0 or 1? We could still fit a linear regression model. That might look something like this. Here I've written the x-axis for the explanatory variable, and the response variable is here, y, on the y-axis. It can only take values of 0 and 1. So if we were to draw a linear regression through these points, it might look something like that. As you can see, only two very specific values of x will cause a prediction of 0 or 1. Not to mention, if we were to draw a residual plot from this regression right here, it would certainly not appear to be very normally distributed. Instead of using a normal likelihood, it is more appropriate to use a Bernoulli likelihood here. That is, the response yi given phi I would be independent from a Bernoulli distribution phi I, where phi I is the probability of success for observation I. In this case, phi I is also the expected value of yi. But we still need to relate this phi I to our explanatory variable x. Remember, in linear regression, we had the expected value of yi was equal to directly to the linear form in the x's, like this. One option in this model would be to model phi directly with this linear form. But there's one problem. Because phi represents a probability, it needs to lie between 0 and 1. To keep this linear form right here between 0 and 1, we would need to place some pretty odd restrictions on the beta coefficients. Instead, we'll use what is called a link function that relates the linear form of the restricted parameter, in our case phi, without any restrictions on the betas. To do this, we could use the odds, which is defined as phi over 1 minus phi. Odds can take on any value greater than 0, so we're less restricted, but not totally unrestricted. So now let's take the log of the odds. This quantity is called the logit link, or logistic link. It can now take on any real number, positive or negative, so it can be related to our linear form without any restrictions. That is, the logit of phi I, which is equal to the log of the odds, will be equal to this linear form here. So this is the piece that relates the x to the success probability. If we do a little bit of algebra, we can recover the expression for the expected value of yi. That is, from this, we can get the expected value of yi, which is phi. So we just need to solve this equation here for phi, which will be the e to the beta naught plus beta 1 x1I over 1 plus the same thing. If we divide the numerator and the denominator by the numerator, we get this form. This form is a little bit more computationally convenient. This process right here is called inverting the link function to get an expression for the expected value of y. Now, if we were to plot expected value of y as a function of x over here, it might look something like this, where the expected value now stays between 0 and 1. This is logistic regression using the logistic link. If the beta coefficient for x, for the covariate x, is positive, it means that an increase in the value of x corresponds to an increase in the probability that y is 1. So the curve would look like this. If the coefficient is negative, that is, beta is negative, that means that an increase in x would correspond to a decrease in the probability that y is equal to 1. So it's just a negative version of that dotted curve. There are other possible link functions, but we're just going to focus on this one. Of course, we can add more x variables like we did with multiple regression, and some or all of those x variables could be categorical, like we had with Anova. For an example of logistic regression, we're going to use the urine data set from the boot package in R. First, we'll need to load the boot package. And if it is not already installed, you'll have to do that as well. After loading the package, we can load the data, which is called urine. These data contain 7 characteristics of 79 urine specimens. The goal of the analysis is to determine if certain physical characteristics of the urine are related to the formation of calcium oxalate crystals. Our 7 variables are, first, R, which is an indicator of the presence of a calcium oxalate crystal. So the value of R will be 0 or 1. And our explanatory variables, or covariates, are the specific gravity, the pH reading, this is for acidity, the osmolarity, conductivity, the urea concentration, and finally the calcium concentration. For more information about these data, see the following source. Let's see what the data look like. We'll take the head of the urine data set. We can see that calcium oxalate crystals were not observed in the first 6 specimens. And we have values for the 6 other explanatory variables. Notice that we have missing values in this data set. So, before we conduct analysis, let's remove those missing values. Dat is the data set that we're going to use. We went from 79 rows down to 77 rows. Now, let's look at a pairwise scatter plot for each of the 7 variables using pairs on our data set. One thing that stands out is that several of these variables are strongly correlated with one another. For example, the specific gravity and the osmolarity appear to have a very close linear relationship, as you can see in this scatter plot. Collinearity between x variables or explanatory variables in linear regression models can cause trouble for statistical inference. 2 correlated variables will compete for the ability to predict the response variable, leading to unstable estimation. This is not a problem for prediction of the response. So if prediction is our only goal of the analysis, then it's not a problem. But if our objective is to discover how the variables relate to the response, we should avoid collinearity. Because the primary goal of this analysis is to determine which variables are related to the presence of calcium oxalate crystals, we will have to deal with the collinearity between the predictors. This problem of determining which variables relate to the response is often called variable selection. We have already seen one way to do this. We could fit several models that include different sets of variables and see which one of those models has the best deviance information criterion value. Another way to do this is to use a linear model where the priors for the linear coefficients favors values near 0. Values near 0 on the coefficients indicate weak relationships. This way, the burden of establishing an association between the variables lies with the data. If there is not a strong signal, we assume that it does not exist, because the prior favors that scenario. Rather than tailoring a specific prior for each individual beta coefficient based on the scale of its covariate x, it is customary to subtract the mean and divide by the standard deviation for each variable. It's easy to do this in R. We can create the design matrix X by scaling the data. We want to omit the first column because the first column contains our response variable. So we want the next 6 columns. We want to scale those by centering them. So center equals true. And we also want to scale them, dividing by the standard deviation. This only makes sense to do for variables that are continuous. If we have categorical variables, we should exclude them from this centering and scaling exercise. Let's run the X. Oops, I called it data instead of dat. Let's rerun that and take a look at the first several values. We can see that the values for these x variables have changed so that the column means for x are all close to 0. For example, negative 9.8 times 10 to the negative 15 power. That's very close to 0. And that is the case with all of these column means. We can also calculate the column standard deviations using the apply function. Apply, where we want to apply this function, standard deviation, to the columns, which is the second index of the dimensions of x. The rows are index 1 and the columns are index 2. So let's calculate the column standard deviations of x, and they're all 1. Now that the explanatory variables are covariates, are centered and scaled, let's talk about that special prior, which will favor coefficients near 0. The prior we're going to use is the double exponential, also referred to as the Laplace prior. Here we have the standard normal PDF as a dashed line, and the PDF of the double exponential distribution as a solid line. As the name implies, the double exponential distribution looks like an exponential distribution with tails extending in the positive direction as well as in the negative direction, whereas the exponential only went in the positive direction. We also have a sharp peak at 0. We can read more about the double exponential distribution in the Jags documentation, or the Jags manual under distributions. Next, let's set up and talk about this model in Jags. Here's the model string. It looks pretty similar to the linear regressions we used earlier, except with some important modifications. In the likelihood portion of the model, we can see that y sub I, the ith observation, now comes from a Bernoulli distribution, d Bern, rather than a d norm, where the probability of success for observing a 1 for the ith observation is probability sub I, or p sub I. Instead of modeling p sub I directly, in logistic regression we're going to model the logit of p. The logit of p gets the linear model portion, where we have a parameter for the intercept, and now we have a beta coefficient for each of the 6 individual variables. We'll place a fairly non-informative prior on the intercept. It'll be a normal prior with variance 25 or standard deviation 5. That's fairly non-informative in a logistic regression model, where values as high as 2 or 3 can get you very close to probability 1, and values of negative 2 or 3 can get you very close to probability 0. Next, we will create our prior for the individual beta terms. Beta j will get a ddx, or a double exponential prior, with location parameter 0 and this value for the inverse scale parameter. As we've noted, this value for the inverse scale gives us a double exponential distribution with variance 1. The rest of these lines should look familiar to you, so let's go ahead and run them. We won't do all of the convergence diagnostics right now, but let's look at least at the trace plots. Let's run that. These trace plots look like they might have some high autocorrelation, but they don't look too bad. We'll have to click return to get the next plots for the remaining betas and for the intercept. These trace plots look okay. Before we move on, let's also calculate the DIC for this model. Instead of a numerical summary of our posterior distribution, let's take a look at a visual summary. Let's create the marginal posterior density plots for our 6 beta coefficients. To display these all on the same page, we'll use par mf row, where we want 3 rows and 2 columns in our plots. Now we'll use the dense plot function on our combined simulations, mod 1 csim, and we want the first 6 columns, which contain the 6 beta variables. We also want these to be displayed on an identical x-axis, so let's give it limits for that x-axis. X-lim will go from -3 to +3. To remind ourselves which beta goes with which variable, let's take the column names from x. So beta 1 is the specific gravity, beta 2 is the pH, acidity, and so forth. Let's generate these plots. The first thing we're looking for in these plots is evidence that the different coefficients, the betas, are different from 0. It is clear that the coefficients for gravity, which is beta 1, conductivity, which is beta 4 here, and calcium concentration, which is beta 6 here, all three of these betas are significantly away from 0. Notice that the coefficient for osmolarity, the beta 3, the posterior distribution here looks like our double exponential prior, and it is almost centered on 0 still. So we're going to conclude that osmolarity is not a strong predictor of calcium oxalate crystals. The same goes for pH up here. Urea concentration, or beta 5 over here, looks like it's a borderline case. However, if we refer back to our pairwise scatter plots, we see that urea concentration is highly correlated with specific gravity, and so we're going to remove this variable. That is, we're going to create another model where we keep the coefficients for gravity, conductivity, and calcium concentration only. Here is that model string for the next model. We've removed the variables that were not significantly away from 0 and retained the coefficient for gravity, a coefficient for conductivity, and a coefficient for calcium. We've also switched from the double exponential prior to a fairly non-informative normal prior on these coefficients. Let's now run this model. We get a warning message that Jags did not use the three variables pH, osmolarity, and urea, which is not surprising to us. It won't affect our analysis. I'll skip ahead and run the remaining code for this model. We need to run the burn-in period, the posterior samples, and the DIC calculation for this model. I'll leave it up to you to check the convergence diagnostics here. Now that we have DIC for both models 1 and 2, why don't we compare the two? We'll run DIC1 and DIC2. And we can see immediately that the first model has more of a penalty because there are more parameters in that model. And interestingly, the first model has the lower DIC of the two, although they're pretty close. It's also important to note that we did change the prior between the two models, and generally we should not use DIC to choose between priors. So in this case, we may not be making a fair comparison. Nevertheless, let's check our results from the second model. Oops, that was a summary of the model object itself. What we want is a summary of the model simulations. There we go. So we can see that with a positive coefficient, the specific gravity is associated with an increase in the probability of observing crystals. With a negative coefficient, the conductivity is associated with a decrease in the probability of observing oxalate crystals. And with a positive coefficient here, we conclude that calcium concentration is associated with an increase in probability of calcium oxalate crystals. Each of these estimates are several posterior standard deviations away from zero, so we would say they are significant contributors to the probability of calcium oxalate crystals. Are these the same conclusions we reached from the first model? Let's look at the combined simulation and just look at the point estimates. Remember, specific gravity was the first coefficient, 1.63, pretty similar here. The fourth coefficient was conductivity, had a negative effect, which we see in both models. And finally, calcium concentration was the sixth variable. It was estimated at 1.62. Here it was estimated at 1.88. Although the numbers are a little different, the two models essentially yield the same conclusions. There are more modeling options available in this scenario, perhaps including transformations of variables, different priors, or interactions between the predictors. But we'll leave it to you to see if you can improve this model. In a logistic regression model, how do we turn parameter estimates into model predictions? The key is the form of the model. Remember that the likelihood is Bernoulli, which gives us a 1 with probability p. We modeled the logit transformation of p as a linear model of the predictors, which we showed in the first segment of this lesson leads to an exponential form for the expected value, or p. It's this exponential form right here. So, if we have the coefficients and the predictor values, we can plug them into this equation to get an estimate of the probability that the response is 1. We're going to use the second model. So let's extract the posterior means of the coefficients. From the combined simulation, and look at the values of those. The posterior mean of the intercept was about negative 0.15. Because we centered and scaled all of the covariates, values of 0 for each of the predictor variables corresponds to their average values. Therefore, if we use this last model, then our point estimate for the probability of calcium oxalate crystals when the specific gravity, conductivity, and calcium concentration are at their average values, that gives us zeros for the x's here. Then our predicted value for the probability of calcium oxalate crystals will involve only the intercept. Let's code that up. It'll be 1 divided by 1 plus an exponential of negative 0.15, which is positive 0.15. This means that if we use our posterior mean point estimates, we estimate that the probability of observing crystals at the average values of these three predictors is about 0.46. Now let's suppose we want to make a prediction for a new specimen whose value of specific gravity is at the average, whose value of conductivity is 1 standard deviation below the mean, and whose value of calcium concentration is 1 standard deviation above the mean. We can just modify this calculation right here. The intercept doesn't change, minus the coefficient for the first beta, 1.42, times the value that we'll use. We were using the average, so that'll be 0. Conductivity was one standard deviation below the mean. We'll first add its coefficient, minus a negative 1.35 or 36 is the coefficient for that one. And we're going to be doing one standard deviation below the mean. So that'll be the value for that x. And finally, we want calcium concentration one standard deviation above the mean. We start with the coefficient, 1.88, times the value of the corresponding x, which was one standard deviation above the mean. And we'll run that. It gives us a probability of almost 0.96 of observing calcium oxalate crystals. Remember, the model was fit to standardized values of the predictor variables. And so we need to use the standardized values of these predictor variables when making predictions from the model. If we want to make predictions in terms of the original x variable values, we have two options. The first option is, for each x variable, we can subtract the mean and divide by the standard deviation for that variable in the original data set used to fit the model. Or we can refit the model without centering and scaling the covariates. So far, we have calculated predicted probabilities of observing crystals for hypothetical predictor values only. We can use the same ideas to make predictions for each of the original data points from the data set. This is similar to what we did to calculate residuals in our earlier linear models. First, we'll take the X matrix, the design matrix, and matrix multiply it with the posterior means of the coefficients. Let's create that variable. We'll call it PMXB for posterior mean of X beta. And it will be PM coefficient. We want the intercept first. Then to the intercept, we're going to add our design matrix, which we've already calculated, and retain only columns 1, 4, and 6 for those three variables we used in the model. And matrix multiply that with PM coefficients 1 through 3. Before we run this, let's make sure we know what each piece is doing. So the first piece here is the intercept. Then we're going to take the values of the predictors, the first three, or these three columns, for specific gravity, conductivity, and calcium concentration. And we're going to matrix multiply it with the posterior means of the coefficients, which we calculated up here. The matrix multiplication does the following. For observation 2, right here, we'll multiply the specific gravity value with its coefficient, the conductivity value with its coefficient, and the calcium with its coefficient, and we'll add those three numbers together to get an X beta for observation 2. Then the same thing will be repeated for observation 3 all the way down through the end of the data set. So let's go ahead and run that. And it gives us those values for each of the observations. Now we need to turn this into a prediction for the probability using this inverse transformation. We've already calculated the betas times the x variables, so we need to finish calculating the rest of this expression. P hat will be our predicted probability. It'll be 1.0 divided by 1.0 plus an exponential function of -1 times our PM x beta that we just calculated. Please make sure, if you have any doubts, to carefully go through this expression and verify that it is in fact calculating this number, where it's extended for 3 covariates. Let's run that and look at the first few values. These are the resulting predicted probability of observing crystals for each of the observations in the data set. We can get a rough idea of how successful the model is by plotting these predicted values against the actual outcome. We'll plot y hat against the response variable. We used p hat, not y hat. Of course, the response variable could take on values of only 0 and 1, and it's kind of hard to see what's going on here. So let's rerun this plot by adding some jitter to the 1s and 0s. Recall, they're still 1s and 0s, but now they've been spread out a little bit so that we can see them better. Along the y-axis, we have the actual response, 1 or 0, and along the x-axis, the predicted probability that it would be a 1. We can see that this model did okay. For observations that have high values of predicted probability of observing a 1, many of them really were 1s. And down here, observations that had low probability were often 0s. Suppose we choose a cutoff for these predicted probabilities. For example, let's select 0.5 as our cutoff. If the model tells us that the probability is higher than 0.5, we're going to classify the observation as a 1. And if it is less than 0.5 on the left here, we're going to classify it as a 0. We can tabulate these classifications against the truth to see how well the model predicts the original data. We'll create a table based on a cutoff of 0.5 using the table function, where the first argument is whether or not the predicted probability is greater than 0.5, and then we want to know whether the response was actually 0 or 1. Let's run that table. Take a look at the values. So the false values here are observations where p hat was less than 0.5, and here they were larger than 0.5. These observations were correctly classified because their true value was 1, and these observations were correctly classified because their value was 0. That is, the correct 1 classifications are the points in this region, and the correct 0 classifications are the points in this region. To calculate our correct classification rate, let's take a sum of the diagonal of that table. Those are the correct classifications. And we'll divide by the sum of the overall table. This gives us a correct classification rate of about 0.76 or 0.77. Not too bad, but not great. Now suppose that it is considered really bad to predict that there will be no calcium oxalate crystal when in fact there is one. We might then choose to lower our threshold for classifying the data points as 1s. Let's say we move that threshold back over this direction to 0.3, and we'll call that our cutoff. That is, if the model says that the probability is greater than 0.3, we'll classify it as having a calcium oxalate crystal. Let's recalculate that. Tab 0.3. So if it's greater than 0.3, we'll classify it as having a crystal. Let's run those. As you can see, we have reduced the incidence of false negatives, where we said there would not be a crystal, but in fact there was one. Previously there were 12, now there are only 7. Let's check the success rate of our classification here for this cutoff value. It looks like we gave up a little bit of predictive accuracy to increase our chances of detecting a true positive and to reduce our chances of a false negative. We could repeat this exercise for many thresholds between 0 and 1, different cutoff points here. And for each one, we could calculate our error rates. This is equivalent to calculating what is called the ROC, or Receiving Operating Characteristics curve, which are often used to evaluate classification techniques like logistic regression. These classification tables, which we have calculated, are all in sample. They were predicting for the same data that were used to fit the model. We could get a better, less biased, and more accurate assessment of how well our models perform if we calculated these tables for data that were not used to fit the model. For example, before we fit the model, we could withhold a set of randomly selected test data points and then use the model fit to the rest of the training data to make predictions for our test set.